Hi everyone, my name is Aria, and I work alongside Whitroy as an electrical tutor. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 3000, 2018. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for EWRB exam. What this audiobook does is take the key ideas from the standard and explain them in simple, spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real installations. So think of this as a learning companion, not a replacement for the actual standard. Alright, let's get started. Today we are starting our audiobook for ASNZS 3000, 2018. This is the Australian and New Zealand wiring rules. In this session, we will look at the preface and explain what the standard is trying to do in a simple and easy way. This standard is made of two main parts, and they are published together as one document. Part 1 sets out the essential safety elements. These are the minimum safety requirements for any electrical installation. Part 1 also gives regulators in Australia and New Zealand another way to write their electrical safety rules, so they do not have to rely only on the old system based on ASNZS 3000. Part 1 has a number of aims. It can be used by itself in regulation, or used together with Part 2. It is written to be complete, so people do not need to move between Part 1 and Part 2 when reading it. It focuses on the safety outcomes we need to achieve, rather than prescribing every work method. The detailed work methods are in Part 2. Part 1 also creates the enforcement link to Part 2. If someone does not follow a work method written in Part 2, then they are not meeting the safety requirements of Part 1, unless they use another method that still gives the same level of safety. Part 1 also confirms the deemed to comply status of Part 2. If an installation is done following Part 2, then it is taken as complying with the safety requirements of Part 1. Part 1 also keeps the standard aligned with international rules, such as IEC 60364 for low-voltage installations. It also provides a way for designers or installers to propose alternative methods when the job needs something different from the standard approach. Now let's look at Part 2. Part 2 sets out the practical installation methods that are accepted as meeting the essential safety outcomes of Part 1. Part 2 can also be adopted directly into regulation, depending on how each regulator chooses to use it. Part 2 builds on all the requirements of Part 1 and adds extra requirements and recommendations to make compliance clearer. It also brings back useful requirements and examples from earlier editions, showing typical solutions that work well and meet safety expectations. Part 2 focuses on common, practical, and cost-effective methods that achieve safety without being overly conservative or complicated. It also uses more figures and examples to explain areas that people often find difficult, such as alternative overcurrent device locations, IP ratings, and access to switchboards. That completes the preface. In the next lesson, we will move into the first clause of the standard and continue building this audiobook step by step. Clause 1.1 is the scope. This standard sets out the requirements for the design, construction, and verification of electrical installations. It also covers the selection and installation of electrical equipment that forms part of an electrical installation. These requirements are here to protect people, animals, and property from electric shock, fire hazards, and physical injury. They apply when the installation is used with reasonable care and used for the purpose it was designed for. The standard also gives guidance so the installation works properly for its intended purpose, and so it can handle foreseeable issues such as temporary loss of supply. Now we move to Clause 1.2, which is the application of the standard. This standard can be used through legislation in each state and territory in Australia and in New Zealand, where the laws relate to electrical safety. It can also be used together with any extra legal requirements, exemptions, or restrictions. The main use of this standard is for electrical installations in any type of building or land that is supplied by electricity consumers. However, the standard may also be referenced in other areas of legislation that involve electrical installations, such as safety of workplaces. For example, work health and safety laws and related codes may require electrical installations to meet certain conditions. Safe design and construction of buildings. This may include national building codes, such as the National Construction Code, and in New Zealand the NZBC. It also links to other reference standards that support building safety. Electricity generation, transmission, and distribution systems. Safe connection to electricity distribution systems. For example, service rules or conditions set by local electricity distributors. Qualifications of electricity workers. Part 1 of this standard gives a way to accept design and installation practices that may not be covered by the methods in Part 2, which includes sections 2 to 8. This is only meant to be used when the change from the normal Part 2 method is significant. Part 2 still has a certain amount of flexibility built into it. Clause 1.3 refers to documents used by this standard. Appendix A contains the full list of reference documents. Now we are moving into Clause 1.4, which is the definitions section of ASNZS 3000, 2018. This part explains how certain words are used in the standard, and it helps us understand the rules correctly. Clause 1.4.1 is the application of definitions. Throughout this standard, the definitions listed from Clause 1.4.2 to Clause 1.4.134 apply. If a term is defined in a particular place in the standard, then that definition applies for that specific section. These definitions apply to both parts of the standard. If the context does not require a special meaning, or the word is not specifically defined, then the common, everyday meaning is used. When the standard talks about voltage and current without any other description, it is talking about RMS values. Clause 1.4.2 is the definition of accessible. This means something can be reached for inspection, maintenance, or repair, but it does not include having to take apart parts of the building in a destructive way. Clause 1.4.3 is accessible, readily. This means it can be reached quickly, without climbing over things or removing obstructions, and without needing a movable ladder. It also means the item must not be more than 2.0 meters above the ground, the floor, or the platform. Clause 1.4.4 is accessory. This includes devices such as switches, fuses, plugs, socket outlets, lamp holders, adapters or ceiling roses that are part of wiring, fittings, luminaires, switchboards, or appliances. It does not include the lamps, the luminaires, the appliances, or the switchboards themselves. Clause 1.4.5 is active, also called active conductor. An active conductor is any conductor that is at a different potential from the neutral or the earthed conductor. In a system where there is no neutral or no earthed conductor, every conductor is treated as an active conductor. Clause 1.4.6 is adjacent. This means next to, or touching, without obstruction, and within arm's reach. Clause 1.4.7 is aerial conductor. This is any stranded conductor, including aerial bundled conductors, that is supported by insulators or purpose-made fittings above the ground, and is directly exposed to the weather. Clause 1.4.8 is alteration. This means a change to part or parts of an electrical installation. Repairs are not alterations. Repairs have their own definition in Clause 1.4.101. Clause 1.4.9 is appliance. This is any device, other than a lamp, where electricity is turned into heat, motion, light, or some other form of energy, or where the electrical properties are changed. Clause 1.4.10 is appliance, fixed. This is an appliance that is fastened to something, or secured in a fixed location. Clause 1.4.11 is appliance, handheld. This is a portable appliance designed to be held in the hand during normal use, with the motor, if it has one, forming part of the appliance. Clause 1.4.12 is appliance, portable. This is an appliance that can be moved while it is operating, or one that can be moved easily from one place to another even when it is connected to the supply. Clause 1.4.13 is appliance, stationary. This is either a fixed appliance or an appliance that weighs more than 18 kilograms and does not have a carrying handle. Clause 1.4.14 is arc fault detection device. This is a device that detects arcing faults within the installation wiring or the plug and lead connection of electrical equipment. When an arc fault is detected, the device disconnects the circuit. Clause 1.4.15 is area, hazardous. This is an area where an explosive atmosphere is present, or may be present, in amounts that require special precautions in the design, installation, and use of equipment. Clause 1.4.16 is arm's reach. This is the zone a person can reach by extending their arm from any point where they normally stand or move. It means the distance a person can reach by hand in any direction, without using tools or a ladder. Clause 1.4.17 is authority, regulatory. This is the government agency responsible for the relevant legislation and how it is applied. Clause 1.4.18 is authorized person. This means the person in charge of the premises, or a competent person appointed or selected by that person, to carry out certain duties on the premises. Clause 1.4.19 is available, readily. This means something can be reached for inspection, maintenance, or repairs without having to dismantle structural parts, cupboards, benches, or similar items. Clause 1.4.20 is barrier. This is something that provides basic protection from access. Basic insulation and basic protection are explained later in the standard. Clause 1.4.21 is cable. A cable is either a single cable core, or two or more cable cores laid up together, and it may or may not have fillings, reinforcement, or protective covering around it. Clause 1.4.22 is cable, armored. This is a cable that has a wrapping of metal, usually tapes or wires, and the purpose is to give mechanical protection. Clause 1.4.23 is cable core. This is the conductor along with its insulation, but it does not include any mechanical protective covering. Clause 1.4.24 is cable, flexible. A flexible cable is a cable where the conductors, the insulation, and their overall covering are designed to provide flexibility. Clause 1.4.25 is cable, mineral insulated metal sheath, sometimes called MIMS. This is a cable where the insulation is compressed powdered mineral inside a solid drawn metal sheath. The cable may be single-core or multi-core. Clause 1.4.26 is cable, neutral screened. This is a cable with one or more cores laid together with or without fillers, surrounded by a concentric wire outer conductor, and then further protected with an insulating sheath. Clause 1.4.27 is cable, sheathed. This is simply a cable with a core or cores covered by a sheath. Clause 1.4.28 is ceiling, suspended. A suspended ceiling, according to AS/NZS 2785, is a ceiling system that hangs down from the floor or roof above. It does not include a nailed timber ceiling following AS/NZS 2589 or timber building standards. Clause 1.4.29 is circuit. A circuit includes live conductors, protective conductors if they are present, a protective device, and the associated switchgear, control gear, and accessories. Clause 1.4.30 is circuit breaker. A circuit breaker is a switch that opens a circuit automatically when certain conditions happen, such as an overcurrent, an undervoltage, or some other external control. Clause 1.4.31 is Class 1 equipment. This is equipment where protection from electric shock does not rely only on basic insulation. It also has another layer of safety because accessible conductive parts are connected to the protective earthing conductor. This ensures that if the basic insulation fails, those parts cannot become live. Clause 1.4.32 is Class 2 equipment. This is equipment where protection from electric shock does not rely only on basic insulation, but includes extra measures such as double insulation or reinforced insulation. There is no need for earthing or installation conditions to provide the protection. Class 2 equipment may include equipment made with durable, Continuous insulation that surrounds all metal parts, except for small parts such as screws or nameplates. Or equipment made with a continuous metal enclosure where double insulation is used throughout, except for parts where double insulation cannot be practically done. There are also types that combine these two methods. Clause 1.4.33 is Class 3 equipment. This is equipment where protection from electric shock relies on supply at SELV levels, and the equipment never generates voltages higher than SELV. If the equipment contains circuits above SELV, but those circuits are isolated and meet other safety rules, they are not considered part of the Class 3 equipment. Clause 1.4.34 is competent person. This is someone who has the knowledge and skill to perform the required task correctly. This knowledge and skill may come from training, qualification, experience, or a combination of these. Clause 1.4.35 is conductor. A conductor is a wire or other material suitable for carrying current. It does not include metallic parts that are only used to enclose electrical energy or provide structural support. Clause 1.4.36 is conductor, bare. This is a conductor without covering or insulation. Clause 1.4.37 is consumer mains. These are the conductors between the point of supply and the main switchboard. Clause 1.4.38 is contact, direct. This means touching a conductor or a conductive part that is live in normal service. Clause 1.4.39 is contact, indirect. This is touching a conductive part that is not normally live, but has become live because of a fault, such as insulation failure or some other fault condition. Clause 1.4.40 is cord, flexible. A flexible cord is a flexible cable where no wire is larger than 0.31 mm in diameter, and no conductor is larger than 4 square millimeters. A flexible cord must also have no more than 5 cores. Clause 1.4.41 is current, fault. This is current that flows because of an insulation failure or because insulation has been bridged or broken down. Clause 1.4.42 is current, overload. This is an overcurrent that happens in a circuit that is otherwise electrically sound. Clause 1.4.43 is current, short circuit. This is a fault current that results from a fault of very low impedance between live conductors under normal operating conditions. The fault path may include the path from the active to the neutral conductor. This is also known as the prospective short circuit current or the bolted fault. Unless stated otherwise, this value is the three-phase RMS value at the relevant point in the installation. Clause 1.4.44 is damp situation. This is a situation where moisture is present all the time or appears from time to time in a way that would reduce the effectiveness or safety of an electrical installation that meets the standard for ordinary conditions. Clause 1.4.45 is de-energized. This means separated from all sources of supply, but not necessarily isolated, earth, or out of commission. Clause 1.4.46 is distribution board. This is a switchboard that is not the main switchboard. The definition links to distributor, electricity in Clause 1.4.57. Domestic electrical installation in Clause 1.4.53. Double insulation in Clause 1.4.73. Clause 1.4.47 is earth. This means connected to the general mass of Earth, and when it is relevant, also connected to the supply neutral as required by the standard. Clause 1.4.48 is Earth's situation. This is a situation where there is a reasonable chance that a person might touch exposed conductive parts while also touching Earth or some other conducting medium that allows a circuit to be completed to Earth. The following cases are considered Earth situations. Item A. Within 2.5 meters in any direction from a conductive floor, such as concrete, tile, or brickwork, or from a permanently damp surface, or from metallic conduit, pipe, or cable sheath, or any other conductive material on which a person may stand. Item B. External to a building. However, a piece of equipment mounted more than 2.5 meters above the ground and away from exposed conductive parts that are in contact with Earth is not considered to be in an Earth situation. Item C. within 2.5 meters of the ground, floor, or platform in rooms that contain socket outlets, where the earthing terminals are earth, and where there is a reasonable chance that someone could make contact at the same time with any exposed conductive part of electrical equipment or any exposed conductive part of an appliance connected to any socket outlet. Item D. All parts of a bathroom, a laundry, a lavatory, a toilet, or a kitchen. Clause 1.4.49 is earth fault loop impedance. This is the impedance of the earth fault current loop, meaning the active to earth loop, starting and ending at the point of the earth fault. The earth fault current loop includes the earthing conductor and the protective earthing conductor. Clause 1.4.50 is electrical equipment. This includes wiring systems, switchgear, control gear, accessories, appliances, luminaires and fittings used for purposes such as generation, conversion, storage, transmission, distribution, or use of electrical energy. Clause 1.4.51 is electrical fault. This is an electrical failure, defect, or flaw in equipment or wiring, or any condition that results in an unintentional loss, reduction or increase of current or voltage, or where voltage exceeds the maximum rated value. Clause 1.4.52 is electrical installation. This is electrical equipment installed to convey, control, measure, or use electricity. It includes equipment supplied from a distributor's system or from a private generating system. It normally starts at the point of supply and ends at the point where fixed wiring stops, or at a plug or socket outlet used to connect appliances. Clause 1.4.53 is electrical installation domestic. This refers to an electrical installation in a private dwelling, or the part of an electrical installation that serves only a flat or living unit. Clause 1.4.54 is electrical installation multiple. This is an installation that includes a number of domestic electrical installations, or a number of non-domestic installations, or any combination of domestic and non-domestic installations. Clause 1.4.55 is electrical installation residential. This is an electrical installation, or part of an installation, that is associated with a living unit or units. Clause 1.4.56 is electric vehicle, often shortened to EV. This is any vehicle powered by an electric motor that draws power from a rechargeable storage battery, and that can be used on public or private roads. This includes plug-in hybrid electric vehicles, where the motor draws some or all of its energy from onboard batteries. Clause 1.4.57 is electricity distributor. This is any person or organization that supplies electricity from a distribution system to one or more electrical installations. It includes a distributor, a supply authority, a network operator, a local network service provider, an electricity retailer, or an electricity entity, depending on the jurisdiction. Clause 1.4.58 is enclosure. An enclosure is a part that provides an appropriate degree of protection for equipment against external influences and against accidental contact with live parts. Clause 1.4.59 is energized. This means connected to a source of electrical supply. A piece of equipment or wiring that is energized has voltage present. Clause 1.4.60 is equipotential bonding. This is the use of electrical connections to bring exposed conductive parts or extraneous conductive parts to the same, or nearly the same, potential. It is not intended to carry current during normal service, but it helps reduce the risk of electric shock under fault conditions. Clause 1.4.61 is explosive atmosphere. This is a mixture under normal atmospheric conditions where flammable substances such as gas, vapor, dust, fibers, or flyings are present, and can ignite and sustain an explosion. This definition follows AS/NZS 60079. Clause 1.4.62 is exposed conductive part. This is a conductive part of electrical equipment that Item A can be touched with the standard test finger as specified in AS/NZS 3100, and Item B is not a live part, but may become live if basic insulation fails. There are exceptions where the term does not apply. These include conductive parts inside an enclosure where a key or tool is needed to open it. Conductive parts inside equipment that cannot be touched in normal use or during normal movement of the equipment. Conductive parts that are separated from live parts by double insulation or by conductive parts that are already earthed. Clause 1.4.63 is extraneous conductive part. This is a conductive part that is not part of the electrical installation, but that can be at the electrical potential of the local earth. Examples include metal water or gas pipes, heating system pipes, metal building components, steel-framed structures, reinforced concrete floors or walls, tiled surface coverings, conductive fittings in bathrooms, and metal pipes. Clause 1.4.64 is fault current limiter. This is a device, designed or selected, to open a circuit in order to limit the instantaneous fault current. Clause 1.4.65 is fire mode. This refers to a specific mode of operation in building systems that is triggered when a fire alarm activates. It changes the behavior of equipment or systems to suit emergency conditions. Clause 1.4.66 is functional earthing, often shortened to FE. This is an earthing arrangement provided to ensure correct operation of electrical equipment, or to allow reliable and proper functioning of electrical installations. Clean or low-noise earths used for electrical equipment may also be considered functional earthing. Clause 1.4.67 is functional unit. This is a part of a switchboard assembly that includes all the electrical and mechanical elements needed to perform one complete function. Conductors connected externally, such as auxiliary cables, are not considered part of the functional unit. Clause 1.4.68 is fuse. A fuse is a device that protects a circuit from excessive current by melting its fuse element and opening the circuit. A fuse includes all the parts that form the protective device. Clause 1.4.69 is informative. This means the content is for information and guidance only. It is not a mandatory requirement. Clause 1.4.70 is ingress protection classification, also called IP classification. This is the degree of protection provided by an enclosure, following AS 60529. Clause 1.4.71 is installation coupler. This is a connecting device, following AS/NZS 61535, that consists of an installation socket and an installation plug. It is designed for permanent connection and is not intended to be engaged or disengaged under load. Clause 1.4.72 is insulated. Insulated means separated from adjacent conducting material by a non-conducting substance or airspace that provides resistance to current flow or prevents dangerous discharge. It is used to avoid shock or dangerous leakage of current. Clause 1.4.73 is insulation system. This is a system of insulation around live parts. It may consist of one or more layers that cannot be tested separately as basic or supplementary insulation. Clause 1.4.74 is isolated. This means separated from all possible sources of electrical energy and made incapable of being energized unintentionally. Clause 1.4.75 is isolation, also called isolating function. This is a function intended to cut off supply to the whole installation, or to a section of it, by separating it from every source of electrical energy for safety reasons. Clause 1.4.76 is lamp. A lamp is a bulb, a tube, or similar item that produces light from electricity. Clause 1.4.77 is lift. A lift is an apparatus attached to a building or structure, where a car or platform travels between vertical guides to raise or lower people. It does not include hoists, dumbwaiters, escalators, or travelators. Clause 1.4.78 is live. Live means energized, or subject to hazardous induced or capacitive voltages. Clause 1.4.79 is live part. A live part is a conductor or conductive part that is energized in normal use. This includes neutral conductors and conductive parts connected to a neutral conductor. There are exceptions. The following are not considered live parts. Earthing conductors. The MEN connection and the neutral bar or link at that point. A neutral bar or link in a switchboard that has no MEN connection when the active supply has been isolated. The sheath of an MIMS cable and associated fittings used as a combined protective earth and neutral conductor in an earth sheath return system. Supports and enclosures associated with unprotected consumers mains that are earthed according to Clause 5.5.3.5. A submain neutral conductor or final subcircuit neutral conductor where the active supply to that submain or subcircuit has been isolated. Clause 1.4.80 is luminaire, also called light fitting. A luminaire is a complete lighting assembly designed to distribute or filter light from one or more lamps. It includes components such as shades, diffusers, starters, and ballasts. It includes the means of connecting to supply, wiring, and support. A lighting component not incorporated into the assembly is not considered a luminaire. Clause 1.4.81 is main earthing conductor. This is the conductor that connects the main earthing connection or bar to the earth electrode, or to the earthing system of the electrical supply. Clause 1.4.82 is main switch. This is a switch whose primary function is to isolate the electrical installation from the supply. It may also meet regulatory requirements if it is labeled properly. Clause 1.4.83 is multiple earthed neutral, also called MEN system. This is an earthing system where parts of an installation that need to be earthed are connected to the general mass of earth and also connected to the neutral conductor of the supply or the PEN conductor. Within the installation, the protective earthing conductor is separated from the neutral conductor. Clause 1.4.84 is neutral, also called neutral conductor or mid-wire. This is the conductor of a multi-wire or three-wire system that is maintained at an intermediate and stable potential relative to the active conductors. It is the conductor connected to earth at the origin of the supply. Clause 1.4.85 is neutral earth system. This is a system in which the protective earth and neutral conductors from the transformer or generator to the installation are not connected together anywhere except at the transformer or generator. Clause 1.4.86 is normative. Normative means the item is a required part of the standard and must be met to claim compliance. Clause 1.4.87 is obstacle. An obstacle is a part that prevents accidental direct contact, but does not prevent intentional direct contact. Clause 1.4.88 is outbuilding, individual. This is a structure containing a switchboard that is separated by an area of land from the structure that contains the switchboard supplying it. Clause 1.4.89 is outbuilding, combined. This means two or more structures installed or built on the same foundation, or sharing conductive metal roofing or conductive metal frames. These structures have more than one electrical supply and are separated by an area of land from another structure that contains the switchboard from which those electrical supplies are taken. Clause 1.4.90 is overcurrent. This is any current that exceeds the rated value of electrical equipment. For conductors, the rated value is their current carrying capacity. Clause 1.4.91 is plug. A plug is a device made to insert into a socket outlet, a cord extension socket, or an adapter. It allows a detachable connection between the accessory and the flexible cord or cable. Clause 1.4.92 is point-in wiring. This is a termination of installation wiring that is intended for connecting electricity-consuming equipment. Clause 1.4.93 is point of attachment. This is the point where aerial conductors of a service line, or aerial consumer mains, are attached to the consumer's building or structure. Clause 1.4.94 is point of entry. This is the point where the consumer mains or the underground service cable enters a building or structure. Clause 1.4.95 is point of supply. This is the junction of the consumer mains with either item A, the conductors of an electricity distribution system, or item B, the output terminals of an electricity generating system on the premises. Clause 1.4.96 is protected extra low voltage, also written as PELV. This is an extra low voltage system that is not electrically separated from earth, but still meets all the requirements of SELV. Clause 1.4.97 is protection, basic. This means protection against dangers that come from direct contact with live parts of the installation. Clause 1.4.98 is protection, fault. This means protection from dangers that arise from indirect contact. This is when someone touches an exposed conductive part that is not normally live, but has become live due to a fault such as insulation failure or some other issue. Clause 1.4.99 is protective earth neutral, also called PEN. This is where the neutral and protective earth functions are combined in one single conductor. Clause 1.4.100 is protective earthing conductor. This is an earthing conductor, other than the main earthing conductor, that is intended to carry earth fault currents or to connect parts of the installation to the earthing system so they are safely earthed. It links to terms such as a CD, readily accessible, readily available, regulatory authority, and reinforced insulation. Clause 1.4.101 is repair. This is work done to restore the electrical installation to a safe and sound condition after damage or deterioration has occurred. Clause 1.4.102 is residual current device, also known as a CD. An ACD is a device that disconnects the supply to protected circuits, socket outlets, or equipment when it detects a current flowing to earth that exceeds a set value. Clause 1.4.103 is ripple-free DC. This applies to sinusoidal ripple voltage where the ripple content does not exceed 10% RMS. Clause 1.4.104 is safety service. A safety service is a system or component that operates during an emergency and is mainly associated with helping people evacuate a building, supporting firefighting operations, or providing fire suppression. Examples include fire detection systems, smoke control systems, evacuation systems, and emergency lifts. Clause 1.4.105 is separated extra low voltage, also called SELV. This is an extra low voltage system that is electrically separated from earth and from other systems so that a single fault cannot give rise to an electric shock. Clause 1.4.106 is service protective device. This is a fuse or circuit breaker installed as required by the electricity distributor for interrupting the supply to a consumer's electrical installation from the supply main. Clause 1.4.107 is shall. Shall indicates a mandatory requirement. Clause 1.4.108 is should. Should indicates a recommendation. Clause 1.4.109 is socket, cord extension. This is a device made to attach to a flexible cord. It has contacts that allow a detachable connection with the pins of a plug. Clause 1.4.110 is socket outlet. This is a device fixed or suspended at a point and having contacts that make a detachable connection with a plug. A cord extension socket attached to a flexible cord that is permanently connected to installation wiring is also considered a socket outlet. Clause 1.4.111 is socket outlet, multiple combination. This is a socket outlet with two or more sets of contacts that allow detachable connections with two or more plugs. Clause 1.4.112 is socket residual current device, or SRCD. An SRCD may be a fixed socket outlet that includes an integral RCD. Or it may be a separate RCD installed next to the socket outlet. An SRCD may or may not have overcurrent protection. Some SRCDs also allow RCD protection for downstream socket outlets. Clause 1.4.113 is soft wiring. Soft wiring is wiring that uses installation couplers installed as part of a subcircuit or as part of a submain system within an installation. Clause 1.4.114 is source of supply. This refers to the generator, converter, transformer, or a group of generators or transformers that are connected to supply mains and that provide electrical energy to an installation. Clause 1.4.115 is subcircuit, final. A final subcircuit is a circuit that starts at a switchboard and supplies only consuming devices or points. Its origin is considered to be at the neutral bar or link, or at the load terminals of the circuit protective devices provided for the circuit. The circuit ends at the supply terminals of the consuming devices or points. Clause 1.4.116 is submains. A submain is a circuit that starts at a switchboard and supplies another switchboard. Its origin is also taken to be the neutral bar or link, or the load terminals of the circuit protective devices provided within the switchboard that feeds the submains. Its termination is taken to be the supply terminals of the other switchboard. Clause 1.4.117 is substation. A substation is an assembly of electrical equipment in one place that is used for converting or transforming electrical energy or for connecting two or more circuits. Measurement transformers and protection transformers are not considered transformers for this definition. Clause 1.4.118 is supply alternative. This is a supply system intended to keep part or all of an installation functioning if the normal supply is interrupted. Clause 1.4.119 is supply normal. This is the source of supply that the installation is normally supplied from under normal operating conditions. The normal supply is usually from a distribution network but may come from a generator. Clause 1.4.120 is supply supplementary. This is a supply system intended to operate together with the normal supply. Clause 1.4.121 is switchboard. A switchboard is an assembly of circuit protective devices, switchgear, instruments, or connecting devices, arranged for distribution and control of one or more submains or final subcircuits, or a combination of both. Clause 1.4.122 is switchboard, main. The main switchboard is the switchboard from which the supply to the whole electrical installation is controlled. Clause 1.4.123 is switchgear. This is equipment used for controlling the distribution of electrical energy, or for controlling or protecting circuits, machines, transformers, or other equipment. Clause 1.4.124 is touch current. This is electric current that passes through a human or animal body when the body touches one or more accessible parts of electrical equipment or an installation, under normal or fault conditions. Clause 1.4.125 is touch voltage. This is the voltage that appears between parts that are accessible at the same time. The term is used only in connection with fault protection. Clause 1.4.126 is track system. A track system is an enclosed wiring system where conductors are spaced or supported on insulating material within a channel, and where plug-in facilities exist along its length. This definition does not apply to busbar trunking systems that comply with ASNZS 61439.6. Clause 1.4.127 is trunking, cable. Cable trunking is a ductile trough used to house and protect electrical cables and conductors. Clause 1.4.128 is voltage. Voltage is the difference in potential between conductors or between conductors and earth. It includes Item A. Extra low voltage, which does not exceed 50 volts AC or 120 volts ripple-free DC. Item B. Low voltage, which is more than extra low voltage, but not more than 1000 volts AC or 1500 volts DC. Item C. High voltage, which is any voltage above low voltage. Clause 1.4.129 is wiring, catenary. This is a wiring system where a cable or cables are attached at intervals to a supporting wire that is suspended between 2 points. Clause 1.4.130 is wiring enclosure. This is a pipe, tube, duct, conduit, or cable trunking that is fixed or supported in place to house or protect sheathed or unsheathed cables. Clause 1.4.131 is wiring, equipment. This includes all wiring of an appliance or electrical equipment that provides supply terminals for connection to an installation. Clause 1.4.132 is wiring, installation. This is wiring whose cables are fixed or supported in place following the requirements of the standard. Clause 1.4.133 is wiring systems. A wiring system is an assembly of one or more conductors, cables or busbars, along with the parts needed to secure and protect them, including mechanical protection if required. Clause 1.4.134 is wiring, underground. This is a system of wiring where cables are buried directly in the earth or carried in an enclosure below ground level, and installed according to the requirements of the standard. That brings us to the end of Clause 1.4, which is the complete definitions section. From here, the standard moves into the more detailed rules of electrical installation practice, and we now have all the terminology needed to understand the rest of ASNZS 3000, 2018 clearly and confidently. Clause 1.5, Fundamental Principles. Clause 1.5 explains the core safety principles of ASNZS 3000. These principles guide the whole standard. They set out what we must achieve to keep people, livestock, and property safe from the dangers that can arise from electrical installations. Clause 1.5.1, Protection against dangers and damage. Clause 1.5.1 tells us that an electrical installation must protect against three main types of risk. The first risk is shock current. Shock current is the current that can flow through a person or an animal when they touch parts that are live in normal service, which is called direct contact, or touch parts that only become live under fault conditions, which is called indirect contact. Either situation can lead to serious harm, so the installation must be arranged to protect against both types. The second risk is excessive temperatures. Excessive temperatures can cause fires, burns, or other damage. People, equipment, and nearby materials must be protected from heat produced by electrical equipment, whether the heat comes from normal operation, fault conditions, or thermal radiation. The standard highlights three effects we must prevent: combustion or degradation of materials, risk of burns, and any reduction in the safe function of equipment. The third risk is explosive atmospheres. In areas where explosive gases or dust might be present, equipment must provide protection against the ignition of those gases or dusts. The installation must be suitable for the specific hazardous environment. Clause 1.5.2, Control and Isolation. Clause 1.5.2 explains that every electrical installation must include control and isolation devices. These devices must prevent or remove hazards so the installation can be used safely and can be maintained safely. Control devices must be arranged so that they do not interfere with the operation of any other equipment, and they must not be affected by other equipment accidentally. An isolation device must be able to disconnect all active conductors, and depending on the situation, may also need to operate in a neutral conductor. This isolation must remove the supply from all external sources. The standard reminds us that a device used for isolation must not interrupt an earthing conductor, or a combined protective earth and neutral conductor. Clause 1.5.3, Protection against electric shock. Clause 1.5.3 covers the key requirement. The installation must protect people and animals from shock current that may arise from contact with live parts under normal conditions, or with parts that only become live under fault conditions. Live parts must not be accessible without the use of a tool or a key under normal conditions or under a single fault condition. Clauses 1.5.4, 1.5.5, 1.5.6, and 1.5.7 explain the detailed requirements for basic protection and fault protection, and how these apply in different environments, including damp situations. Clause 1.5.3.2, Methods of protection. Protection is provided in different ways depending on the situation. Under normal conditions, protection is usually provided by basic protective provisions. Under fault conditions, protection is provided by fault protective provisions. Enhanced protection, such as extra low voltage or reinforced insulation, can provide both basic and fault protection under all conditions. A method of protection must be either an appropriate combination of basic and fault protection, or an enhanced method that provides both. Some locations need additional protection because of environmental influences or special installation conditions. Different methods of protection used on the same installation must not interfere with each other. Failure of one method must not compromise another. Clause 1.5.4, Basic protection. This part of the standard explains how we protect people from touching live parts during normal service. So, in simple terms, this is all about stopping accidental contact with live electrical components that are energized during day-to-day operation. Clause 1.5.4.1 General. Protection must be provided wherever there is any danger from touching live parts. These are the parts of an installation that are normally energized, and the protection has to make sure people, livestock, and property stay safe under normal conditions. Clause 1.5.4.2 Methods of protection. Basic protection can be achieved by one or more of the following methods. Method 1. Insulation. Covers live parts completely with electrical insulation that can withstand mechanical and environmental stresses, and the insulation must only be removable by destruction. Method 2. Barriers or enclosures. Live parts are placed behind barriers or inside enclosures that meet certain degrees of protection, such as IP2X, IP2XB, or IP4X for horizontal surfaces. The idea is simple: you should not be able to touch live parts unintentionally. Method 3. Obstacles. Obstacles prevent accidental contact with live parts. They are not designed to stop deliberate actions, but they help prevent an accidental bump or touch. Method 4. Placing out of reach. Live parts are positioned far enough away that a person cannot reach them from a normally occupied position. Remember, RCDs are not recognized as a sole means of basic protection. They can support these methods, but they cannot replace them. Clause 1.5.4.3 Protection by insulation. All live parts have to be fully covered with insulation strong enough to withstand stress in normal service. This insulation must comply with the relevant standard for the equipment. Manufacturers will already provide the correct type of insulation, so for commercial equipment, we simply follow the manufacturer's requirements. Paints and varnishes on their own do not count as proper insulation unless they are part of a certified system. Clause 1.5.4.4 Protection by barriers or enclosures. Live parts must be inside something that gives a defined degree of protection. For example, IP2X or IP2XB, meaning a finger cannot reach the live parts. IP4X for horizontal top surfaces people can touch easily. The barrier or enclosure must suit the environment and be strong enough to prevent distortion or damage that could expose live parts. Removal of barriers or covers should not be possible without using a tool or a key, except in controlled conditions. If barriers are removed, interlocking devices or intermediate barriers may be required to automatically keep people away from live parts. Clause 1.5.4.5 Protection by obstacles. Obstacles are used only where access is restricted to competent persons or people under supervision of a competent person. Obstacles can prevent accidental contact with live parts, but they are not intended to stop intentional contact. Examples are mesh guards, rails, or screens that block casual access. Obstacles may be removable without a key or tool, but they must be secured so they cannot be accidentally displaced. Clause 1.5.4.6 Protection by placing out of reach. This method relies on ensuring the live parts are positioned far enough away that a person cannot physically reach them from a normal working or standing position. It can only be used where access is restricted to competent persons or people under supervision. Simultaneously accessible live parts of different voltages must not be within arm's reach. Arm's reach means a radius of 2.5 meters from where a person is standing or can move within the space, including vertical reach. If obstacles or working conditions change the normal reach area, then distances must be increased to keep live parts safely out of reach. Clause 1.5.5 Fault protection. In this clause, we talk about what happens when a fault makes metal parts become live. If that happens, a person touching the metal could get a shock, so the standard requires us to put protection in place. The idea is very simple: if a fault can make something dangerous, the installation must have a method that keeps people safe. Every part of the installation must use a method that suits the equipment and the surrounding conditions. Clause 1.5.5.1 General. This clause explains the purpose. Whenever there is a chance that exposed metal might become live because of a fault, we must have protection. The method we choose depends on the environment and the equipment, but the goal is always the same: prevent electric shock under fault conditions. Clause 1.5.5.2 Methods of protection. There are several ways to protect people when a fault happens. The most common way is to automatically disconnect the supply. This means if a fault occurs, the protective device trips fast enough so the fault cannot hurt anyone. Another way is to use Class 2 equipment, or equipment with reinforced insulation. This means the live parts are designed so they cannot be touched, even if something goes wrong inside the equipment. A third method is electrical separation. This is normally done with a transformer that separates the output from earth, so there is no shock path if a single fault happens. The last method is limiting the fault current. In other words, if the design ensures the fault current is too small to be dangerous, then the risk of shock is very low. But in everyday electrical installations, automatic disconnection is by far the method we use the most. Clause 1.5.5.3, Protection by automatic disconnection of supply. This clause goes deeper into how automatic disconnection works. The main idea is that if a fault happens, the touch voltage rises on exposed metal parts. We need to limit that voltage and we need to cut off the power quickly. To do this, all exposed metal parts are bonded together and connected to earth. This keeps the metal at the same voltage, which reduces the shock risk. Next, a protective device, like a circuit breaker, a fuse, or an RCD, must disconnect the circuit fast enough. If the touch voltage becomes unsafe, the device automatically trips and removes the supply. For this to work properly, the earth fault loop impedance must be low. That means the fault current must be high enough to operate the protective device within the required time. The standard also gives maximum disconnection times. For example, some circuits must disconnect within 0.4 seconds, especially socket outlets and handheld equipment. Other circuits, like fixed equipment, are allowed up to 5 seconds. Sometimes extra bonding is needed if there is metalwork around the area, just to make sure the protective device can operate within the correct time. Clause 1.5.5.4 explains that one way to protect people from dangerous voltages is to use Class 2 equipment, or equipment with equivalent insulation. This simply means the equipment has double insulation, or reinforced insulation, so even if one layer fails, another layer still keeps you safe. Sometimes total insulation is built into switchgear, and sometimes extra insulation is added during installation. The key idea is that strong insulation stops fault voltage from reaching metal parts a person can touch. If extra insulation is added on site, it must be fitted properly. There should not be any metal screws or bolts that break through that insulation. Any covers or lids that can be opened without tools must still keep live parts safely behind an insulating barrier that meets the correct IP rating. Clause 1.5.5.5 is about electrical separation. Electrical separation means using an isolated transformer to supply one individual circuit. Because the active and neutral are not connected to earth anywhere, there is no return path through earth if a person touches one live part. This reduces the risk of electric shock. But this only works if the separated circuit stays completely isolated. It cannot be earthed, bonded, or connected to any other circuit. Clause 1.5.6 introduces extra protection by the use of RCD devices. RCDs are not allowed to be the only method of basic protection, but they are very useful as extra protection on top of insulation and barriers. Clause 1.5.6.1 says that an RCD can support basic protection, but it cannot replace the normal basic protection such as insulation. It is simply an extra safety layer. Clause 1.5.6.2 explains that RCDs are acceptable for fault protection. If a fault causes current to flow to earth, the RCD detects the imbalance and switches off the supply quickly. This reduces the chance of electric shock in a fault situation. Clause 1.5.6.3 explains where RCDs must be installed. They are required for socket outlets, lighting points, handheld equipment, and many wiring systems. They are also required for heating cables, equipment used in damp areas, and several special installations covered by ASNZS 3001, 3002, 3003, 3004, 3102, and 4249. The message is simple. Where the risk of electric shock is higher, an RCD must be used. The purpose of the RCD is to disconnect the supply fast enough to prevent serious harm. Clause 1.5.7, Basic and fault protection by use of extra low voltage. This clause explains how SELV systems, or PELV systems, can be used to provide both basic protection and fault protection, but only when certain conditions are met. First, the nominal voltage must never exceed the limits for extra low voltage. That means no more than 50 volts AC, or 120 volts ripple-free DC, even if the supply is arranged in different ways. Second, all circuits must be electrically separated from each other, and separated from any higher voltage circuits. Third, live parts of SELV circuits must never be connected to earth, or connected to protective earthing conductors, or to live parts from any other circuit. Fourth, for PELV circuits, live parts must be protected against direct contact. This can be done by barriers or by insulation, unless the voltage is extremely low. In dry areas, this limit is 25 volts AC or 60 volts ripple-free DC. Where a person may have a larger contact area with the body, such as wet or conductive locations, the voltage limit is 6 volts AC or 15 volts ripple-free DC. Clause 1.5.8, Protection against thermal effects in normal service. This clause deals with preventing fires caused by heat from electrical equipment. Electrical installations must be arranged so that high temperatures, electric arcs, or other heating effects cannot ignite flammable materials. Equipment must be installed so its temperature characteristics, during normal use, do not create risk to people, to livestock, or to property. Heat produced in normal service must not cause damage to the equipment itself, or to adjacent materials, or to any other installation. If heat is expected, adequate ventilation must be provided to keep temperatures within safe limits. The standard reminds us that temperature can affect the performance and lifespan of electrical equipment, so installation choices must take this into account. Clause 1.5.9, Protection against overcurrent. This clause explains that protection must be provided to prevent injury or damage from excessive current. Overcurrent can create dangerous temperatures or mechanical stress in conductors and equipment. Protection may be provided by one of two methods. 1. Automatic disconnection of supply before the overcurrent reaches a dangerous level. 2. Limiting the overcurrent to a safe value and safe duration. Clause 1.5.10, Protection against earth fault currents. Any earthing conductor, and any other part of the system that must carry an earth fault current, must be capable of carrying that current without being damaged. This ensures the protective device can operate safely during an earth fault. Clause 1.5.11, Protection against abnormal voltages. This clause covers protection against harmful effects of abnormal voltages. These can come from several sources: faults between live parts of circuits supplied at different voltages, induced voltages in unused conductors, or harmful influences between different circuits and installations. Clause 1.5.11.1, General. Protection must be provided for any harmful effects of abnormal voltages that may arise from faults between circuits of different voltages, voltages induced or occurring in unused conductors, or harmful influences occurring between different installations or between electrical and non-electrical systems. Clause 1.5.11.2, Circuits operating at different voltages. This clause explains that protection must be provided to prevent injury or property damage if a fault occurs between live parts of circuits that operate at different voltages. Two methods may be used. The first method is segregation, keeping the circuits physically separated from each other so a fault cannot jump between them. The second method is installing devices that protect against overvoltage. These devices help limit or prevent dangerous voltages if a fault occurs between the circuits. Clause 1.5.11.3, Voltage disturbances and electromagnetic influences. This clause states that protection against damage from overvoltage caused by events such as lightning, or caused by switching operations, is not a requirement of this standard. However, it points readers to guidance in Clause 2.7 in Appendix F, which explain how to manage surge protection if it is needed. Even though surge protection is not mandatory here, it may still be required in other standards or for sensitive equipment. Clause 1.5.11.4 Voltage in unused conductors. This clause explains that unused or disconnected conductors can still develop dangerous voltages. For example, an unused conductor running beside a high-voltage cable can pick up induced voltage, even if it is not connected at either end. To prevent injury or property damage, any disconnected, redundant, or unused conductor that remains installed must be terminated and protected at both ends in the same way as a live conductor. The key idea is that unused conductors must never be left floating, because they can still become energized due to induction or other effects. Clause 1.5.11.5 Different circuits and installations. This clause explains that protection must be provided against harmful influence between different types of circuits or different installations. This includes 4 situations. First, influence between 2 separate electrical installations. Second, influence between different circuits within the same installation. Third, influence between electrical circuits and non-electrical systems. And fourth, influence between the electrical installation and the structure of the building or the land that the installation is mounted on. There are also notes reminding us that telecommunications cables near high-voltage systems must follow the requirements of other standards, and that AS/NZS 3800 gives additional guidance on managing electrical interference between circuits, including for data and communication systems. Clause 1.5.12 Protection against the spread of fire. This clause explains that electrical installations must not start a fire, and must not help a fire to spread. Electrical equipment must be selected, installed, and protected so that it does not block escape routes, does not produce smoke or gases that obstruct people, does not add fuel to a fire, and does not reach temperatures that could ignite nearby materials. It also must not interfere with people escaping from a structure. Clause 1.5.13 Protection against injury from mechanical movement. This clause deals with moving parts of electrically driven equipment. Protection must be provided wherever maintenance work could expose someone to injury, or where emergency stopping may be needed to prevent harm. This protection can include devices that disconnect or isolate equipment to remove the mechanical danger. Clause 1.5.14 Protection against external influences. Here the standard explains that all parts of an electrical installation must be protected against the conditions they may face in normal service. This includes mechanical damage, weather, water, dust, corrosive chemicals, vibration, animals, temperature, explosive atmospheres, and other environmental factors. The installation must be able to withstand these conditions without becoming unsafe. Clause 1.6.1 General. An electrical installation must be designed to keep people, animals, and property safe. It must work properly for its intended use. It must connect and operate safely with the electricity supply it is attached to, and it must not create problems for the distribution system. It must allow safe operation, safe inspection, safe testing, and safe maintenance. And it must reduce inconvenience if a fault happens. Clause 1.6.2 Supply characteristics. When planning or designing an installation, we must know the important details of the electricity supply. We need to know whether the supply is alternating current or direct current. We need to know how many conductors are provided, including phase, neutral, and protective earth for an AC supply. We need to know the voltage and the tolerance. For New Zealand, the nominal low voltage supply is 230/400 volts, plus 6% and minus 6%. We need to know the frequency, the maximum current available, and the possible short-circuit current. We also need to know what protection measures are present in the supply system, such as the main earthing system. And finally, we must understand any limits on equipment use, including harmonic levels and other characteristics that might affect the design. Clause 1.6.3 Maximum demand. The maximum demand of an installation must be determined. This means working out how much electrical load the installation will need, where the load is located, and how the load may change depending on how the installation is used. Clause 1.6.4 Utilization voltage. The installation must be designed so that the voltage at the appliances and equipment is suitable for their proper operation. This includes considering voltage drop. Clause 1.6.5 Circuit arrangement. Circuits must be arranged to reduce danger and reduce inconvenience when a fault occurs. They must also allow safe operation, inspection, testing, and maintenance. Clause 1.7.1 General. Electrical equipment must be selected and installed so that it operates safely and reliably under normal conditions. It must not create danger from shock, fire, overheating, or other reasonably expected conditions such as overload or external influences. And the equipment must be installed according to both the requirements of this standard and the manufacturer's instructions. Clause 1.7.2 Installation work practice. Electrical equipment must be installed using safe and sound work practices. This includes choosing equipment that is strong enough, durable enough, and suitable for the environment. Installation instructions must be followed. Safe access and working space must be provided. Fixings and supports must be strong and reliable. Installation wiring must be clearly identified. Active, neutral, earth, protective earth, and equipotential bonding conductors must be shown correctly. Green or green and yellow are only for earthing and bonding conductors. Live conductors must not use green or green-yellow. Socket polarity must match the product specification and be consistent across the installation. Semi-enclosed rewirable fuses must not be installed. Condensation control must be considered where required. And equipment must be installed in a way that keeps its IP rating. Clause 1.7.3 Equipment selection. Electrical equipment is considered suitable if it meets the safety requirements in ASNZS 3820, or if it complies with the appropriate Australian, New Zealand, or international standard that applies to that type of equipment. Clause 1.7.4 Damp situations. Electrical equipment used in damp or wet locations must be suitable for the environment, must provide extra protection against shock, and must protect against damage caused by moisture or high humidity. Clause 1.8 Verification. Before an electrical installation, or any alteration or repair, is placed into service, it must be inspected and tested as far as practicable to confirm that it meets the requirements of ASNZS 3000. The inspection must avoid danger to people and avoid damage to property. If the work is an extension or alteration, it must also be checked to confirm that it does not reduce the safety of the existing installation. The correct connection of conductors to control and protective devices must be verified. Clause 1.9 Means of compliance. This clause explains the different ways an installation can show it meets the safety principles in Part 1. It tells us when we can rely on Part 2, when other standards may apply, and how changes or special designs must be handled. Clause 1.9.1 Compliance with Part 2 of this standard. If an installation follows all the rules in Part 2, then it is considered to automatically meet the safety principles in Part 1. That is the default pathway. In New Zealand, this does not apply to domestic installations. Clause 1.9.2 Compliance with other standards. Some installations need to follow extra standards that apply to their specific type of equipment or environment. This clause simply reminds the designer to check which additional documents are required. Clause 1.9.3 Alterations and repairs. When you change or fix an installation, the new work must not make anything less safe. You cannot leave any part carrying more current or voltage than the standard allows, and you cannot create conditions that break the rules. Repairs should use materials and methods that were acceptable for the original installation, but they must still meet today's safety expectations. Clause 1.9.4 Compliance by specific design and installation. Sometimes an installation cannot follow Part 2 step by step. In those cases, a specially designed solution may be used, as long as it still achieves the same level of safety required by Part 1. Clause 1.9.4.1 Use of a Part 1 design. A special design is acceptable only if it clearly provides a safe outcome. The installation must still protect people from shock, fire, and other hazards, even though the design does not follow Part 2 exactly. Clause 1.9.4.2 Acknowledgement by the owner or operator. If a design does not follow Part 2, the owner must formally acknowledge this so everyone understands the approach and the safety decisions taken. Clause 1.9.4.3 Documentation by the designer. The designer must record the reasons for not using Part 2, the checks needed to make sure the installation is safe, and any special instructions. This documentation shows how the design meets the aims of Part 1. Clause 1.9.4.4 Verification. Before the installation is used, all parts covered by the special design must be tested and inspected to confirm they actually meet the required safety level. Clause 1.9.4.5 Competency requirements of designers. Anyone creating a design that departs from Part 2 must be competent and able to understand the risks involved. Clause 1.9.4.6 Identification. Any switchboard connected to a special Part 1 design must have a clear and permanent label stating that the installation uses a Part 1 solution under ASNZS 3000. This ensures future workers know exactly what type of design they are dealing with. We have now reached the end of Part 1 of ASNZS 3000. This section has laid out the fundamental principles that guide every electrical installation, the purpose, the scope, the definitions, the protective measures, and the essential requirements for design, selection, installation, and verification. Part 1 gives us the framework. It explains why we do things a certain way, what risks we must manage, and how safety, reliability, and compliance are built into every decision. From understanding shock current and external influences, to selecting the right equipment, to ensuring installations are inspected and tested before use, these principles support everything we do in the field. As we move into Part 2 and the standard, the focus shifts from principles to detailed rules and technical requirements. Part 2 shows us how to apply what we have just learned, turning these safety principles into practical installation methods. Thank you for listening to Part 1 of ASNZS 3000. Let's continue with Part 2, where we look at the specific installation rules that bring these principles to life in real electrical work. Hi everyone, my name is Aria, and I work alongside Whit Roy as an electrical tutor. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 3000, 2018. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for EWRB exam. What this audiobook does is take the key ideas from the standard and explain them in simple, spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real installations. So think of this as a learning companion, not a replacement for the actual standard. All right. Let's get started. Today we're moving into Section 2 of ASNZS 3000. This section is all about protecting people, property, and equipment by designing electrical installations the right way from the very beginning. We look at things like basic protection, fault protection, overcurrent protection, RCD protection, overvoltage, undervoltage, arc fault protection, and how switchboards must be built and installed. I'll explain each clause in simple language so you can understand the purpose behind the rules, not just the words. So let's get into it and make Section 2 easy to learn. Section 2, General Arrangement, Control, and Protection. This section explains the basic rules for choosing and installing switchgear and control gear. The aim is simple: the installation must be safe, reliable, and protected from faults. Clause 2.1, General. Clause 2.1.1, Application. This clause explains why Section 2 exists. It tells us that the switchgear and the control gear in any installation must be chosen and installed so the whole job meets the safety principles from Part 1 of ASNZS 3000. In simple terms, this clause says that the equipment controlling the installation must be suitable, must be safe, and must work properly under normal use. Clause 2.1.2 Selection and Installation. This clause explains what switchgear and control gear must be able to do. It says the equipment must allow us to control, isolate, and safely work on the installation. This includes turning off a whole installation, turning off a single circuit, or turning off one piece of equipment so we can test it, repair it, or check a fault. It also says the equipment must automatically disconnect the supply if something goes wrong. That includes an overload, a short circuit, or too much earth leakage current in the part of the installation being protected. The idea is simple: if there is a dangerous fault, the device must trip before someone gets hurt or the wiring is damaged. The clause also explains that the equipment must protect the installation from voltage problems, such as when the voltage drops too low or rises too high. This is to stop equipment from being damaged by poor supply conditions. The clause then reminds us that the switchgear and the control gear must be grouped properly on switchboards. They must be installed inside suitable enclosures, protected from the environment, and located where people can reach them safely when they need to. Nothing should be buried, hidden, or exposed to harmful conditions. It also says that circuits which affect the reliability of supply need their own clear protection and control. One circuit failing should not automatically shut down other circuits unless there is a good reason. Finally, the clause makes it clear that everything must be installed following ASNZS 3000 and following the instructions from the manufacturer. If the manufacturer says the device must be installed in a certain way, then that is the way it must be installed. No shortcuts, no guessing, and no ignoring the instructions. In this clause, the standard tells us the purpose of Section 2. It sets the minimum requirements for how we select and install switchgear and control gear so the whole installation meets the safety rules in Part 1 of the standard. In short, this clause tells us what this section covers and why it matters for safety. Clause 2.2 Arrangement of electrical installation. Clause 2.2.1 Circuits. Clause 2.2.1.1 General. This clause explains how we should break an installation into circuits. The idea is to create circuits that make sense, are safe, and are easy to manage over the life of the installation. The designer should think about how the equipment works together. Some things need to run in groups, and some things have special needs from the user. The load on each circuit must match the protective devices, so nothing is overloaded. Another key concept is what happens when a circuit fails. If a single circuit trips, we do not want critical equipment to stop, and we want faults to be easy to find. The installation should also let people do maintenance or upgrades without turning off power to everything else. Safety service circuits must be kept separate from normal circuits so safety systems keep working even when something else fails. We usually divide circuits into common groups such as lighting, socket outlets, heating and cooling, motors, control systems, and safety services. This keeps the installation tidy and easy to understand. Clause 2.2.1.2 Origin of submains and final subcircuits. This clause is simple. Every submain and every final subcircuit must start at one switchboard. All the live conductors for that circuit must come from the same place. This keeps circuits clearly identified, easy to isolate, and easy to test. Clause 2.2.1.3 Common neutral. This clause explains when a neutral is needed and how common neutrals can be used safely. Any circuit that needs a neutral for the equipment must include one. Sometimes one neutral can serve more than one circuit, but only if all those circuits come from the same supply and if certain safety rules are met. The common neutral must stay continuous and must not rely on the terminals of switches or equipment. If a final subcircuit shares a neutral, the actives and the neutral must be controlled together using linked devices. The neutral must be clearly marked at the switchboard so people know exactly which actives it belongs to. If an appliance can be supplied from more than one source, All those supplies must have one common isolating switch. This prevents confusion and makes sure the entire appliance can be made safe during work. The clause also reminds us that common neutrals can rise to dangerous voltage if they are disconnected while active conductors from different circuits are still connected, so the design must avoid that situation. The neutral must have enough current carrying capacity to match the associated active conductors. Clause 2.2.1.4 Electric Vehicle Charging Circuits. This clause points us to the appendix for extra rules about electric vehicle charging. In New Zealand, only circuits that directly supply electric vehicle chargers must follow those extra requirements described later in Clause 7.9. Clause 2.2.2 Maximum Demand. This clause explains how to work out the maximum demand of the installation. The idea is that the supply to consumer mains, submains, and final subcircuits must be large enough for the way the installation is laid out and the way the equipment will actually be used. Maximum demand can be worked out in a few different ways, depending on the job. If the real, measured demand ends up higher than the calculated value, then the measured value becomes the true maximum demand. One way to work it out is by calculation. The standard gives guidance on how to calculate maximum demand for different types of installations. The important idea is that different places use electricity differently, so calculations can vary. Another way is by assessment. This is used when the loads are unpredictable, or when the installation is large or complex, or when the building has a special type of use. In these cases, experience and professional judgment may give a better picture of the maximum demand. Another option is measurement. This means recording the highest rate of electricity use over a 30-minute period using a demand meter. This gives a real number based on how the installation actually behaves under load. Another method is limitation. Here, the maximum demand is limited by the rating of a fixed circuit breaker, or by the load setting of an adjustable circuit breaker. For consumer mains and submains, the maximum demand is the sum of the current settings of the devices protecting the final subcircuits and any extra submains. The key idea is that the method chosen must give a realistic and safe value for the installation. Clause 2.2.3 Selection and installation of conductors. This clause simply points us to Section 3, which explains how conductors must be chosen and installed. The idea is that conductor selection always follows the rules in Section 3 of ASNZS 3000. Clause 2.2.4 Operating characteristics of equipment. Clause 2.2.4.1 General. This clause explains that every item of electrical equipment must be selected and installed so it meets the requirements of this section and any other relevant parts of the standard. If a device performs more than one function, each function must meet the rules that apply to it. The idea is that equipment must be suitable and safe for how it is used, not just for what it is labeled as. Clause 2.2.4.2 Voltage. This clause says the equipment must match the nominal voltage of the circuit it is connected to. In simple terms, the voltage rating of the equipment must be correct for the supply. Clause 2.2.4.3 Current. This clause says equipment must be able to handle the normal current of the circuit, including any effects from inductive or capacitive loads or from harmonics. It must also be able to cope with abnormal currents for as long as the protective device allows during faults. The idea is that the equipment should not be damaged during either normal use or expected fault conditions. Clause 2.2.4.4 Frequency. If frequency affects the performance of the equipment, the rated frequency must match the supply frequency. In most cases, this means the equipment must suit 50 Hz. Clause 2.2.4.5 Power. This clause says that the power rating of the equipment must be suitable for the duty it needs to perform. The idea is simple: the equipment must be able to deliver the power required without overheating or failing. Clause 2.2.4.6 Effects on operator or other equipment. This clause explains that the equipment must not cause harm to people or create problems for other equipment when it is used normally. It must not interfere with the supply, and it must not cause dangerous conditions during switching. The note reminds us that some equipment requires trained operators, and this may limit where such equipment can be used. Clause 2.3. Control of electrical installation. Clause 2.3.1. General. This clause explains that every installation must have devices that allow us to prevent or remove hazards. These devices make it safe to operate, repair, and maintain electrically powered equipment. They are extra safety measures, and they work together with the protective devices described later in the standard. The installation must have switching and disconnection devices so that anyone doing work can make the equipment safe. Any device we use for this purpose must be chosen to match the function it needs to perform. The standard groups these functions into four main types. Isolation is the function that fully separates the equipment from the supply. Emergency switching is for situations where the supply must be cut off quickly to remove danger. Mechanical maintenance switching makes equipment safe for physical work. Functional control is everyday switching used to run equipment. If one device performs more than one of these functions, it must still meet the rules for each function it performs. Clause 2.3.2. Common control requirements. Clause 2.3.2.1. General. This clause explains that every circuit must be capable of being isolated from all of its supply conductors. Depending on the system, this may be done by isolating all conductors or by isolating only the conductors that must be disconnected for safety. Where the conditions are suitable, a group of circuits may be isolated by one common switch. This helps when circuits work together or feed one piece of equipment. Any means of isolation must make sure the equipment cannot become live by accident. The isolation device must need a deliberate action to re-energize the equipment. Extra precautions may be used, such as fitted padlocks, warning tags, lockable spaces, or short-term earthing. These measures help prevent someone from accidentally switching the supply back on. If equipment contains live parts from more than one supply, there must be clear notices warning people that different supplies exist. These warnings help anyone working on the equipment identify which circuits must be isolated. The only exception is when an interlocking arrangement guarantees that all circuits are isolated, or when the live parts are safely covered so accidental contact is not possible. Where needed, the installation must also provide a way to discharge stored electrical energy before work is carried out. Clause 2.3.2.1.2. Alternating current systems. This clause explains how isolation works in an AC system. All active conductors in an AC circuit must be able to be isolated by a device designed for isolation. For neutral conductors, the rules depend on how the system is arranged. Normally, we do not isolate the neutral conductor of a consumer main, or a neutral that is also used as a combined protective earthing and neutral conductor. But there are some cases where the neutral may be switched, such as a multi-pole device that switches all poles together, or a device that ensures the neutral cannot remain open when the actives are closed. If a switchboard needs to disconnect all live conductors of a circuit, the device must be designed so the neutral cannot be disconnected or reconnected without the actives being disconnected first and reconnected last. This protects people from unsafe neutral conditions. The safe sequence is simple: disconnect the actives first, then the neutrals. Reconnect the neutrals first, then the actives. Fire pump control circuits follow a special rule which requires the neutral to be switched. And fuses must never be installed in the neutral in accordance with ASNZS 7.5.6.4. An earthing conductor must never be isolated or switched. A combined PEN conductor must also never be isolated or switched. Clause 2.3.2.1.3. Direct current systems. In a DC system, all conductors must be capable of being isolated. The standard points to extra guidance for DC isolation in the appendix. Clause 2.3.2.2. Devices for isolation. Clause 2.3.2.2.1. General. This clause explains what an isolation device must be able to do. A device for isolation must be able to disconnect all active conductors of that circuit. A semiconductor device cannot be used by itself for isolation because it cannot guarantee a safe open state. The isolation device must be able to withstand any impulse voltage that could appear at the point of installation. It must not trick the user into thinking it is off when it is actually on. It must clearly show when the isolating contacts are open. The symbols O for off and I for on are considered acceptable ways to show this. The device must be installed so it cannot operate accidentally, even if hit or knocked. It must be able to disconnect all live conductors of the relevant supply and must be easy to reach. If the device cannot interrupt normal load current, extra measures must prevent it from being operated while load is still flowing. This may include interlocking with a circuit breaker or using warning notices. When the isolation device is a switch, it must be able to stay in the open position. Isolation may be achieved by several types of equipment, including switch disconnectors, multi-pole or single-pole disconnectors, plugs and socket outlets, fuses, links, or special terminals that do not need the conductor removed. Clause 2.3.2.2.2 Identification. This clause explains that all isolation devices must be clearly identified so people know which circuit or equipment they isolate. Identification can be by marking or, when isolating one item, by placing the device where it is obvious. A switch that displays the recognized isolation symbol from the relevant product standard is considered suitable for isolation. The standard also lists the product standards that apply to isolation devices. Clause 2.3.3 Main switches. Clause 2.3.3.1 Introduction. This clause explains the purpose of main switches. A main switch must let people isolate the electricity supply quickly and safely. That includes ordinary users, electrical workers, and emergency services. The idea is that if something goes wrong, or if urgent work is needed, the whole supply or part of the installation can be turned off immediately. Main switches must also allow safety services to keep running during an emergency. The supply to emergency equipment must not be cut off unless absolutely necessary. Clause 2.3.3.2 General. This clause says that every electrical installation must have a main switch, located on the main switchboard, that controls the entire installation. If the installation has more than one supply, then each supply must have its own main switch on the main switchboard. There is an exception for alternative supplies such as generators or solar systems. Those main switches can be located on another switchboard, as long as they meet the product standard that applies to that kind of supply. Any part of the installation that supplies safety services needs its own main switch, separate from the switch that controls the normal installation. This ensures emergency equipment can be kept running when everything else is turned off. Every main switch must meet the same rules as any isolation device. It must be easy to operate, reliable, and clearly identified. The standard also gives a list of equipment that does not need to be controlled by a main switch. This includes consumer mains, metering equipment, certain control systems, voltage sensing equipment, fault current limiters, and surge diverters. These items are normally placed on the supply side of the main switch for safety or operational reasons. Clause 2.3.3.3 Number of main switches. This clause says the number of main switches must be kept as low as possible, because too many switches can make emergency control confusing. Domestic installations must have only one main switch for each separately metered supply, or for each separately controlled portion of the building. If a house contains more than one independent dwelling, each dwelling must have its own main switch. Clause 2.3.3.4 Location and operation. Main switches must be placed where people can reach them easily in an emergency. They must not be mounted too high. The operating handle must be no more than 2 meters above the floor or any safe platform nearby. There is one exception. A main switch does not need to be accessible if the switchboard is on public land and the installation is protected by other safety measures. Examples include telephone cabinets, traffic control equipment, or bus shelters. The operating handle for a main switch must be simple and mechanical. It must use a handle, lever, or push button that gives a clear and solid action. Electronic screens or touch panels cannot be used as the primary means of operating a main switch. They may be used only for remote control, as long as a physical mechanical operator still exists. If a building has more than one occupier, each occupier must have an isolating switch that disconnects only their portion of the installation. The switch must be easy to access from their entrance, and it must meet the same main switch requirements. Clause 2.3.3.5 Identification. A main switch must be clearly marked with the words main switch. It must stand out from the other devices on the switchboard so that anyone can identify it quickly in an emergency. If a switchboard has more than one main switch, each one must show which part of the installation it controls. If operating a main switch turns on or isolates an alternative supply, a notice must clearly show the location of the correct main switch for that supply. Where an installation has multiple supply points, such as a building with more than one incoming feed, each main switchboard must have a notice showing where the other supplies and switchboards are located. Supplementary or alternative supplies must have main switches labeled to show the energy source. Clause 2.3.3.6 Remote Control. This clause explains how remote control of main switches must be done. Any remote control equipment must be clearly identified and must be located in a place suited to how the installation operates. When a remote control device is used, activating it must cause the main switch to isolate the supply to the parts of the installation that need to be disconnected. If the remote system also allows the main switch to be closed again, then extra precautions must be taken. The design must prevent the switch from closing by accident due to a control fault. There must be a way to lock the main switch in the open position. The remote system must not allow the main switch to be overridden or bypassed. Where remote control is used for a general installation, it does not need to be provided separately for safety services. Safety service switches must follow the rules in Clause 7.2. If an electronic touch screen or programmable control system is used for remote control, the main switch must still meet the mechanical operating rules listed earlier. Clause 2.3.4 Additional isolating switches. Clause 2.3.4.1 Electrical installation in an outbuilding. This clause explains when an outbuilding needs to be treated as its own electrical installation. If the outbuilding has a maximum demand of 100 amps or more per phase, and it has its own switchboard, then it must be treated as a separate installation. This means it will need its own isolating switches and its own main switch arrangements. For main switches in an outbuilding, the rule is that the main switch or isolating switch must be installed on the switchboard inside the outbuilding. This gives anyone working in the outbuilding a safe way to isolate the supply without going back to the main building. If the outbuilding is supplied by more than one submain, each submain must have its own main switch. Those switches do not need to be mounted side by side, but there must be a clear notice showing where all the other main switches for that outbuilding are located. This helps anyone working in the outbuilding isolate every supply safely. Clause 2.3.4.2 Submains and final subcircuits greater than 100 amps. If a submain or a final subcircuit has a rating above 100 amps per phase, then it must have its own isolating switch at the switchboard where the circuit starts. This isolating switch must control that circuit only. There is an exception. If fault current limiters or fuses protect small submains that branch off large rising mains, such as in multi-story buildings, the separate isolating switch is not required. Clause 2.3.4.3 Alternative supply. This clause explains that if the installation has an alternative supply, such as a generator or another source installed under Clause 7.3, then an isolating switch must be provided either at the supply source or at a suitable switchboard. This ensures the alternative supply can be safely controlled and isolated. Clause 2.3.4.4 Identification. Any isolating switch required under this clause must be clearly marked so people know which circuits it isolates. Where the isolating device cannot be placed near the equipment it controls, a suitable warning notice must be fixed on the board or enclosure to tell people where the isolator is located. If a switch automatically connects an alternative supply when operated, it must be marked to show its purpose clearly. Clause 2.3.4.5 Appliances and accessories. This clause reminds us that appliances and accessories, including motors, must have proper isolation and switching devices. These devices must follow the rules in the relevant sections of the standard, especially Section 4 and Section 7. Clause 2.3.5, Emergency switching including emergency stopping. Clause 2.3.5.1, General. This clause explains that emergency switching must be provided wherever it might be necessary to quickly control the electricity supply to remove a danger. Emergency switching might be needed to switch off equipment, or in some cases to switch equipment on, depending on how the danger is removed. The emergency switching device must be an isolating device when there is a risk of electric shock. The design of the emergency switching arrangement must not create extra danger or interfere with safely removing the original hazard. The standard gives examples of places where emergency switching is important. This includes machinery, conveyors, groups of machines, pumping systems for flammable liquids, ventilation systems, large buildings, research facilities, boiler rooms, large kitchens and teaching laboratories. Clause 2.3.5.2, Emergency switching devices. An emergency switching device must be able to remove the hazard quickly. It may be a single device that interrupts the incoming supply, or a combination of devices that act together by a single action. The device must be able to break the full load current of the equipment, including stalled motor current where needed. If the device is manually operated, it must interrupt the main circuit directly. If it is operated by a remote control system, it must open when the control coil loses power or another reliable method is used. The device must have a way to latch or hold the switch in the off or stop position, so it cannot restart accidentally. It must not re-energize the equipment automatically. If there is likely to be danger when the equipment restarts, the device must require a manual reset before power can be restored. Plugs and socket outlets must not be used as emergency switching devices. There is one exception. If equipment is supplied from a socket outlet that has its own switch, then that switch may be used for emergency switching. Clause 2.3.5.3, Installation. Emergency switching devices must be installed where they are easy to reach in an emergency. They must be placed so that anyone can operate them quickly if danger occurs. If remote operation is needed, the remote position must also be obvious and easy to reach. Clause 2.3.5.4, Identification. Devices used for emergency switching must be clearly marked so people can recognize them instantly. Handles, levers, or push buttons must be permanently identified and must be colored red with a contrasting background. There is an exception. If a lanyard, chain, or rope is used for remote operation of an emergency stop device, such as above a conveyor, it does not need to be colored red. Clause 2.3.6, Shutting down for mechanical maintenance. Clause 2.3.6.1, General. This clause explains that when electrical equipment has moving parts, heat, or anything that can cause physical injury, we must have a safe way to shut down the supply before doing mechanical maintenance. The danger might come from rotating machinery, conveyors, motors, heating elements, or unexpected mechanical movement. The main idea is simple. Before anyone works on equipment that moves or creates heat, the electricity must be shut off in a way that prevents the equipment from starting unexpectedly. Because of this, the switch used to shut down the supply must be arranged so it cannot be bumped, knocked, or vibrated back into the on position. Locking devices, warning notices, or a lockable enclosure may be used to prevent accidental reconnection. However, if the person doing the maintenance keeps full control of the shutdown switch at all times, then locking facilities are not required. Clause 2.3.6.2, Devices for shutting down. Devices used for shutting down during mechanical maintenance must work by manual operation. They must clearly show when they are in the off position. They must also be designed so they cannot switch back on by accident due to impact or vibration. These devices only need to interrupt the main live conductor that powers the mechanical movement. They do not need to disconnect every conductor. In some cases, the control circuit of a drive may be interrupted instead, but this is only allowed if other safeguards, such as mechanical restraints, prevent movement. If the shutdown switch is located away from the equipment it controls, then it must have a way to be locked in the open position so the equipment cannot restart while someone is working on it. Clause 2.3.6.3 Installation. The device used for shutting down must be installed in the main circuit so it properly removes the supply to the mechanical parts. It must be positioned so that the relevant conductor is safely interrupted. Clause 2.3.6.4 Identification. Any device used for shutting down during mechanical maintenance must be marked clearly so that workers know exactly what it isolates. It must be easy to find and convenient to use in a maintenance situation. Clause 2.3.7 Functional control switching. Clause 2.3.7.1 General. This clause explains functional switching. Functional switching is everyday operational control, turning equipment on or off for normal use, not for safety. Examples include switches, contactors, and solid-state devices used to start or stop equipment as part of regular operation. Each part of a circuit that needs to be controlled separately must have its own functional switching device. A single functional switch can operate several pieces of equipment together if they are intended to run at the same time. Sometimes the switching device may be built into the equipment itself. Clause 2.3.7.2 Functional switching devices. Functional switching devices must be suitable for the heaviest duty they are expected to perform. This includes how often they operate, how much current they carry, and any stresses such as motor loads or lamps with low power factor. Disconnectors, fuses, and links must not be used for functional switching. The device must be properly designed for switching duty. Devices that control low power factor loads, such as motors or fluorescent lighting, must follow the correct rating rules unless the switch is specifically designed for that purpose. For example, some switches are designed under the AC23A category and do not need further derating. Functional switching devices do not need to show the on and off positions, except for appliance switches, which must show the off position. Clause 2.3.7.3 Identification. Functional switching devices normally do not need markings for on or off. The exception is switches on appliances, which must show the off position. Clause 2.3.7.4 Control circuits. Control circuits must be designed and protected so that a fault in the control wiring does not cause dangerous operation of the connected equipment. This includes preventing sudden or unexpected starts due to wiring faults or interference between control circuits and other conductors. The main idea is that control circuits must not create a situation where machinery operates unpredictably. Clause 2.4 Fault protection. Clause 2.4.1 General. This clause explains the recognized methods of protecting people from electric shock caused by a fault. A fault means a dangerous connection between a live part and something that should not be live, such as exposed metalwork. The standard recognizes three main ways to provide fault protection. The first way is automatic disconnection of supply, which is the most common method. The second way is using Class II equipment or equivalent insulation, which provides extra insulation so no exposed metal becomes live. The third way is electrical separation, where one circuit is fully separated from others so a fault cannot produce a dangerous voltage. The standard then explains that the detailed rules for automatic disconnection of supply are found in later clauses. Clause 2.4.2 Protection by automatic disconnection of supply. This clause explains the purpose of automatic disconnection. The idea is to limit the touch voltage during a fault. If a live conductor touches an exposed conductive part, the voltage on that metal must be removed quickly enough to prevent electric shock. To achieve this, two things must happen. First, the exposed conductive parts must be connected to a protective earthing system that meets the rules of Section 5. Second, an overcurrent device or an RCD must disconnect the fault fast enough to keep the touch voltage safe. The combination of proper earthing and fast disconnection is what makes this method effective. Clause 2.4.3 Types of devices. This clause explains which protective devices can be used for automatic disconnection. Any device used must not automatically reclose after it trips. It must stay open until someone resets it safely. The standard lists several types of acceptable devices. These include enclosed fuse links that meet the correct standard, miniature circuit breakers, molded case circuit breakers, and fixed setting RCDs that meet their relevant standards. Other devices without auto-reclose may also be used if they have similar protection characteristics. Semi-enclosed rewirable fuses must not be used for automatic disconnection because they do not reliably clear faults in the required time. There is one exception. Some devices with auto-reclose may be used if they automatically test the insulation before reclosing, and only reclose when the insulation is safe. Clause 2.4.4 Auto-reclose devices. This clause explains when auto-reclose devices are allowed. An auto-reclose device may be used if several important conditions are met. First, it must not be used as the main method of fault protection required by Clause 1.5.6. Second, the auto-reclose must not operate after someone has manually switched the device off. This prevents unexpected reconnection while someone is working. A warning notice must be fixed near the device to tell workers that an auto-reclose function is present. It must also warn them to turn the device off manually and isolate the supply before starting work. There must be a time delay before the first reclose, such as 3 minutes, to reduce the chance of reconnecting during a dangerous condition. The number of reclose attempts must be limited, such as 3 attempts. There is an exception. If the auto-reclose device performs an automatic insulation test and only reconnects when the insulation is safe, then some of these restrictions do not apply. Clause 2.5 Protection against overcurrent. Clause 2.5.1 General. This clause explains that every active conductor must be protected by a device that automatically disconnects the supply whenever the current becomes too high. Overcurrent can be dangerous because it overheats cables and equipment, and the heat or stress can damage insulation or start a fire. The device must disconnect the circuit before the current grows large enough, or lasts long enough, to cause injury or damage. A fuse must never be placed in the neutral conductor. If a device switches the neutral as part of a multi-pole unit, it must follow the isolation rules in Clause 2.3.2.1.2. Protection against overcurrent includes 2 parts. The first part is protection against overload, which means too much current flowing for too long during normal operation. The second part is protection against short-circuit current, which is a sudden, very high current caused by a fault. Both types of protection must work together, and must match the current carrying capacity of the cables connected to the circuit. The standard also reminds us that the rating of a cable can change depending on how it is installed, the size of the conductor, and its construction. So the protective device must match the actual installation conditions. Clause 2.5.1.2 Consumer Mains. This clause explains how overcurrent protection must be arranged for consumer mains. There are several acceptable options. One option is to place both overload and short-circuit protection at the point of supply. Another option is to provide short-circuit protection at the point of supply, and put overload protection at the main switchboard. A third option allows you to omit short-circuit protection at the point of supply if overload protection is provided at the main switchboard and the consumer mains are designed and installed to meet the construction rules in Clause 3.9.7.1.2. Consumer mains that do not have a service protective device at the point of supply are called unprotected consumer mains. Where unprotected mains are used, the earthing and protection arrangements must follow the diagrams and requirements shown later in the standard. If the consumer mains supply multiple circuits, and each of those circuits already has overload protection, then overload protection at the point of supply is not needed as long as the total load does not exceed the rating of the consumer mains. Clause 2.5.1.3 Submains and final subcircuits. This clause covers overcurrent protection for all subcircuits within the installation. Overload and short-circuit protection must be installed at the origin of every circuit. Protection must also be added at places where the cable becomes smaller or has a reduced current carrying capacity. There are a few exceptions. Some circuits must not be interrupted because the loss of power would create a greater danger than overcurrent itself. These include some safety system supplies, lifting magnets, or certain control circuits. In these situations, the design may require special alarms or monitoring systems instead of disconnecting the supply automatically. Another exception allows protective devices to be placed at a different location when permitted by other clauses in the standard. In some cases, protection may be omitted if allowed by later clauses in Section 2.5.3 or 2.5.4. Clause 2.5.1.4, Omission of protective device for safety reasons. This clause explains that a protective device may be left out when opening the circuit unexpectedly would create a greater danger than leaving the circuit energized. Examples include some control circuits in safety systems or in the secondary circuits of certain transformers. In these cases, a fault alarm or monitoring device is often recommended so that dangerous conditions can still be detected. Clause 2.5.2, Devices for protection against both overload and short-circuit currents. This clause explains the requirements for devices that protect against both overload and short-circuit current. The device must be able to break any overcurrent up to the maximum prospective short-circuit current at the point where the device is installed. It must also meet all the requirements of the overload and short-circuit protection clauses in Section 2.5.3 and Section 2.5.4. The standard allows several types of devices to be used. These include circuit breakers with both overload and short-circuit releases, fuse combination units, and fuses with enclosed fuse links such as high rupturing capacity fuses. A circuit breaker may also be used together with a fuse to provide the required protection. Semi-enclosed rewirable fuses must not be used for this purpose because they cannot reliably interrupt short-circuit currents. General-purpose fuses and most modern circuit breakers normally combine overload and short-circuit protection into one device. A fuse includes all the parts that make up the complete protective unit. Some circuit breakers can replace older fuse carriers, but if they are used in place of semi-enclosed fuse carriers, they must be rated at not more than 80% of the current carrying capacity of the protected conductor. Screw-type enclosed fuses that comply with the correct part of the IEC standard are also acceptable. Clause 2.5.3, Protection against overload current. Clause 2.5.3.1, Coordination between conductors and protective devices. This clause explains how the overload protective device must match the cable it is protecting. For the protection to work properly, two simple conditions must be met. The first condition is that the current the circuit is designed for must not be greater than the continuous current carrying capacity of the conductor. In other words, the expected maximum load on the circuit must be less than or equal to the rating of the cable. The second condition is that the protective device must operate quickly enough to stop the conductor from overheating when an overload occurs. The device must trip before the cable reaches a dangerous temperature. The standard gives formulas to express these relationships, using the design current of the circuit, the rating of the device, and the cable's capacity. The operating current of the device during overload depends on the device type. For circuit breakers, the effective overload operating current is usually 1.45 times the rated current. For fuses, it is normally 1.6 times the rated current, following the International Fuse Series. A note explains that a fuse should normally be rated at no more than 90% of the current carrying capacity of the cable it protects. This ensures that the fuse rating and the cable rating stay coordinated. The standard also reminds us that adjustable devices must be set correctly for the load they protect, and that overload protection does not protect against all types of long-duration low-level overheating unless the system is designed with proper limits. Clause 2.5.3.2, Position of overload protective device, general arrangement. This clause explains where overload protection must be placed. Normally, the overload device must be installed at the origin of every circuit and at each point where the cable becomes smaller or its current carrying capacity reduces. There is one general exception. If the conditions in clauses 2.5.3.3 or 2.5.3.4 are met, then the overload device may be placed somewhere else or may be omitted entirely. These exceptions are explained next. Clause 2.5.3.3, Alternative position of overload protective device. This clause describes the conditions where the overload device may be placed somewhere other than the origin of the circuit. The first condition is that the conductor must have no branch circuits or socket outlets between its origin and the location of the protective device. This means there is no chance of supplying extra loads before the protection is reached. The second condition applies when the conductor supplies one or more circuits that are already individually protected against overload. If the sum of the ratings of those downstream devices does not exceed the capacity of the conductor feeding them, then the overload protection can be placed at another suitable location, such as within a switchboard or busway. The standard provides diagrams showing typical examples of these alternative positions. Clause 2.5.3.4, Emission of overload protective device. This clause explains when overload protection may be left out entirely. One situation is when opening the circuit during an overload would create a greater danger than leaving the circuit energized. This applies to certain safety system supplies, lifting magnets, or some machine excitation circuits. Where this happens, an alarm system or monitoring device may be recommended instead of automatic disconnection. Another situation is when the conductor is not in a location where opening the circuit would create a fire or explosion risk, and one of the following conditions is met. The first condition is that the conductor is on the load side of a change in capacity and is already protected by a device placed upstream. The second condition is that the conductor supplies equipment that cannot cause an overload, such as certain heating appliances. The conductor must also have no branches or socket outlets connected along the way. The third condition is when the conductor supplies equipment used only for telecommunications, signaling, or control, where overload currents cannot occur. Examples of these arrangements are shown in later figures of the standard. Clause 2.5.4, Protection against short circuit current explains how circuits are protected when a fault causes a sudden and very high current to flow. A short circuit is not the same as an overload, because an overload builds up over time, while a short circuit happens instantly and can reach extremely high current levels. If this current is not cleared quickly, conductors can overheat, insulation can break down, and serious damage or fire can occur. This clause explains how to select suitable protective devices and where they must be installed so the installation remains safe. Clause 2.5.4.1, Determining the prospective short circuit current explains that the prospective short circuit current must be known at every relevant point in the installation. This value represents the highest fault current that could flow if a short circuit occurred at that location. The value can be obtained either by measurement using suitable test equipment or by calculation. Whichever method is used, the result must be realistic so that protective devices with adequate braking capacity can be selected. Clause 2.5.4.2, Characteristics of short-circuit protective devices explains that the braking capacity of a protective device must be at least equal to the prospective short-circuit current at the point where the device is installed. If the available fault current is greater than the device rating, the device may fail violently instead of providing protection. An exception is allowed where a device with a lower braking capacity is used together with an upstream device that has sufficient capacity. In this case, the devices must be coordinated so that the total energy released during the fault does not exceed what the downstream device and the connected conductors can safely withstand. The explanation also recognizes that other effects, such as mechanical stress, arcing energy, and forces caused by very high currents, may need to be considered, and this information is normally provided by manufacturers. The clause also explains that short-circuit currents must be cleared before a conductor reaches its maximum safe temperature, because excessive heating can damage the conductor or its insulation. For short-circuit durations up to 5 seconds, an approximate relationship is used to confirm that disconnection occurs quickly enough, taking into account the fault duration, the conductor material factor from ASNZS 3008, the conductor cross-sectional area, and the fault current. Notes explain that correct material factors must be used, that very short duration faults are treated differently, and that in some cases a protective device may have a higher rating than the cable, provided the short circuit energy limit is not exceeded. Clause 2.5.4.3, Position of devices for short circuit protection explains that, under normal conditions, a short circuit protective device must be installed at the origin of every circuit and at any point where the conductor size is reduced. This ensures that smaller conductors downstream are protected against high fault currents. The clause also allows for specific exceptions where the device may be installed in a different position or omitted, subject to conditions explained later in the standard. Clause 2.5.4.4, Alternative position of short-circuit protective device explains that in some situations the protective device does not need to be located exactly at the circuit origin. One situation is where the conductor section between the origin and the device is very short, is mechanically protected to reduce the likelihood of a short circuit, and is installed in a way that minimizes fire risk. Another situation allows the device to be located on the supply side of a reduced conductor, provided the operating characteristics of the device still give adequate protection to the conductor downstream. In practice, this is confirmed by checking that the fault energy let through by the device does not exceed what the conductor can safely withstand. Clause 2.5.4.5, Omission of short-circuit protection explains that in special cases, short-circuit protection may be omitted altogether. This is permitted only where automatic disconnection could create a greater danger than the short circuit itself, where consumer mains are installed in accordance with the special rules for unprotected mains, or where conductors connecting generators, transformers, rectifiers, or batteries to their switchboard meet strict installation conditions. In these cases, the wiring must be installed to minimize the risk of short circuit, must avoid locations that increase fire risk, and must still have short-circuit protection provided for the remainder of the circuit at the associated switchboard. Clause 2.5.5, Protection against switchboard internal arcing fault currents. Clause 2.5.5.1, General. This clause explains when we must protect switchboards from internal arcing faults. An internal arcing fault is a very dangerous fault that creates extremely high temperatures, pressure, and burning metal. It can seriously damage equipment and put people at risk. Protection must be provided whenever a switchboard is rated at 800 amps or more per phase. This applies whether the switchboard is operating normally or being worked on. The supply conductors feeding into the switchboard must also be arranged to reduce the chance of an arc starting. This can be done by using proper insulation or by separating conductors so that accidental contact is unlikely. The standard then explains that the switchboard must meet at least one of several approaches. The first option is to reduce the chance of an internal fault starting. The second option is to limit the harmful effects if a fault does occur. The third option is to use internal separation within the switchboard to prevent the fault spreading. Clause 2.5.5.2, Reduction of the probability of the initiation of a switchboard internal arcing fault. Switchboards rated at 800 amps or more per phase must be built with internal separation in line with ASNZS 61439.2. Separation is required between the busbars in the functional units, between different functional units, between terminals used for external conductors, and between the general supply section and any safety service section of the switchboard. The purpose of this separation is simple. It prevents tools, loose parts, or accidental contact from causing an arc. It also helps ensure that one fault does not spread into another part of the switchboard. The notes explain that separation can be achieved in several ways, including barriers, insulated covers, or specific construction forms. The main idea is preventing things from touching live parts unintentionally. Clause 2.5.5.3, Limitation of the harmful effects of a switchboard internal arcing fault. If a fault does occur, this clause explains how to limit the damage. A protective device must be installed that will disconnect the arc as quickly as possible. The arcing fault current is normally assumed to be between 30% and 60% of the prospective short-circuit current. To keep the switchboard safe, the protective device must operate at a current below 30% of the prospective short circuit level. A maximum clearing time is given by a formula. The idea is that the fault must be cleared before it produces more energy than the switchboard can safely withstand. An example in the standard shows how to calculate the clearing time using the current rating of the switchboard and the prospective fault level. Earth fault protective devices must not have settings higher than 1200 amps. This ensures that earth faults contributing to an arcing event are cleared fast enough. The settings of these protective devices must be checked during inspection. The notes explain that discrimination with the electricity distributor's protective devices may be needed, and that arc detectors can be used to speed up response time. Clause 2.5.6 Coordination of overload and short-circuit protective devices. This clause explains how protective devices must work together. A single device may provide both overload and short-circuit protection if it meets all requirements for both functions. If two separate devices are used, their characteristics must be coordinated so that the energy allowed to pass through the short-circuit device does not exceed what the downstream overload device and the conductor can safely handle. These settings must also be verified during inspection. Section 2.5.7 Reliability of supply. Clause 2.5.7.1 General. This part explains that an electrical installation should be arranged so the supply stays as reliable as possible. To do that, the installation is divided into sensible circuits, and the protective devices are chosen so they discriminate properly. That means if a fault happens on one part of the installation, only the device closest to that fault should operate. The rest of the installation should stay energized. The idea is to minimize how much of the supply is lost when a protective device trips. It also explains that the choice of protective devices, and the way they are set, must be checked during inspection in line with Clause 8.2.2, Sub-Clause C, Item 2. Clause 2.5.7.2, Coordination of protective devices. Clause 2.5.7.2.1, General. This clause says that when we choose protective devices, we need to think about two things. One is discrimination, also known as selectivity. The other is backup, also called cascading. Discrimination means that when two or more protective devices are in series, the device downstream should operate for a given fault, and the device upstream should stay closed. In simple terms, the breaker closest to the fault should trip first. The upstream breaker should not trip for that same fault. The goal is to keep the rest of the installation energized. Backup, or cascading, is about how two devices behave when the fault is large, such as a short circuit. It considers how much energy is passed through to the downstream device, and whether that downstream device can withstand that energy safely. It also includes how the two devices share the fault, and how the upstream device helps the downstream one survive high fault currents. The clause reminds us that manufacturer information should always be used where available, because each device has its own curve, its own energy limits, and its own timing behavior. Figure 2.12 in the standard shows the basic idea of discrimination. When the fault occurs on a branch circuit, the protective device for that branch should clear the fault while the upstream protective devices remain intact. That way the supply to the rest of the installation is not interrupted. Clause 2.5.7.2.2, Safety Service Circuit Discrimination. This clause explains that faults in safety service circuits must not cause a loss of supply to the other safety services. A safety service is something that must keep running during an emergency. At the same time, a fault anywhere on the general electrical installation must not interrupt any of the safety services either. The level of fault current considered here goes up to the level of an arcing fault current, which is generally taken as between 30% and 60% of the prospective short-circuit current. To meet this rule, discrimination must be provided between the protective devices so that faults on any one safety service, or faults on the general installation, do not take out the supply to the other safety services. The standard gives an example in Figure 2.13 to show how the devices should be arranged. Clause 2.5.7.2.3, General Supply Circuit Discrimination. For normal circuits, discrimination should be arranged so that if something goes wrong, the loss of supply is as small as possible. That means you coordinate the protective devices on the outgoing circuits with the protective device on the supply side. The coordination is checked using the time current curves for the devices, or using the manufacturer data. For circuit breakers, the downstream protective device is usually labeled C2 and the upstream device C1. The standard explains how to choose settings so that discrimination is maintained. For circuit breakers rated 800 amps or greater, you must use a coordination study with the manufacturer's curves to confirm that discrimination exists. For circuit breakers rated 250 amps up to 800 amps, discrimination is required based on the overload curves, and recommended for the instantaneous and short time delay settings as well. For circuit breakers less than 250 amps, discrimination is generally considered to be achieved when the upstream breaker has a rating at least 1.5 times that of the downstream breaker, as long as both devices have the same curve type. The clause also describes how fuses and circuit breakers can be coordinated. For fuses used together, discrimination is usually achieved when the upstream fuse has a current rating 1.6 times that of the downstream fuse for overload, and at least 2 times for short-circuit currents. For combinations of a fuse and a circuit breaker, the upstream device must be chosen so its curve stays above the overload and instantaneous curves of the downstream device. The standard notes that discrimination requirements mainly apply for switchboards rated at 800 amps or higher. It also reminds designers to use manufacturer data because every protective device behaves differently, especially when short-circuit currents become high or when current-limiting designs are used. These rules help ensure that faults are isolated quickly and safely without shutting down the whole installation. ASNZS 3000 Section 2.6, New Zealand clauses only, additional protection by RCDs. Clause 2.6.1 General. This clause explains why RCDs with a rated residual operating current not more than 30 mA are used as an extra layer of protection. They give added safety in places where earth leakage current might become dangerous, or where people might use equipment carelessly. These RCDs help reduce the risk of electric shock, but they do not replace the main protection required by Clause 2.4. They do not protect against faults between live conductors. They also do not protect against dangerous voltages that may come into the installation from the supply neutral. The idea is simple. RCDs provide additional protection. They trip when an earth leakage current reaches a set level, and this reduces the chance of serious shock. But they are never the only protection. They work together with the other safety measures in the standard. RCDs used for this purpose must have a sensitivity not exceeding 30 mA. Some RCDs are 10 mA, and these give even greater protection. Clause 2.6.2, Selection and Arrangement of Devices. Clause 2.6.2.1, General. Any RCD used for additional protection must be able to interrupt a circuit when earth leakage rises above its designed trip level. The load rating of the RCD must be at least the same as the maximum demand of the part of the installation it protects, or the highest rating of any overload device on that same part of the installation. Earth or bonding conductors must never pass through the magnetic core of the RCD, because this would affect the correct operation. Circuits must be arranged so the normal leakage from connected equipment will not cause nuisance tripping. We aim to keep normal leakage well below the RCD's rating. Clause 2.6.2.2, Types of RCD. RCDs used in electrical installations must be fixed setting devices that comply with ASNZS 3190, ASNZS 61008.1, ASNZS 61009.1, or IEC 62423. There are several common types. Type AC trips on normal sinusoidal AC leakage. Type A trips on both AC and pulsating DC leakage and is recommended as the general-purpose type for most installations. Type I protects against AC leakage and 10 mA residual currents with fast disconnection. These are used for special locations such as medical areas. Type F protects circuits that may have high-frequency leakage or fast-rising currents, such as from electronic equipment. Type B trips on AC leakage, pulsating DC leakage, and smooth DC leakage from rectifiers or converters. These different types exist because modern equipment can create different leakage waveforms, and the RCD must be designed to detect them correctly. Clause 2.6.2.2.3, New Zealand only. In New Zealand, RCDs required by the standard must interrupt all live conductors. This includes active and neutral conductors. If the RCD is a Type A device, it must meet the New Zealand requirements in ASNZS 61008.1 or ASNZS 61009.1. Clause 2.6.2.3, Protection against initiation of fire. Type S RCDs with rated residual currents from 100 mA to 300 mA may be used to reduce the risk of fire caused by leakage across damaged insulation. They operate more slowly and provide a different kind of protection but are not a substitute for the 30 mA devices needed for shock protection. Clause 2.6.2.4, Arrangement. When additional protection is required for final subcircuits, the RCDs must be arranged to minimize inconvenience and avoid losing supply to large parts of the installation. In any installation where there is more than one RCD and more than one lighting circuit, the lighting circuits must be shared between RCDs so only part of the lighting is lost if one device trips. For residential installations, no more than 3 final subcircuits may be on one RCD. If there is more than one final subcircuit, at least 2 RCDs must be installed. These rules make sure that one tripping device does not shut down the entire home or building. Clause 2.6.3, Additional protection by RCDs. This clause explains when we must install RCDs to give extra protection against electric shock. In simple terms, the rule says that this extra protection sits on top of the normal protection. It does not replace the basic protection, and it does not replace the fault protection that we already need from Clause 2.4. The standard reminds us that other New Zealand standards also talk about RCD requirements, but for our audiobook we focus only on what applies in New Zealand electrical installations under ASNZS 3000. The big idea is this. Extra protection by an RCD is needed in places where a single fault, or people using equipment carelessly, could create a higher risk of electric shock. An RCD that trips at 30 mA, or in some cases 10 mA, brings that extra layer of safety. RCD protection does not fix everything. It cannot protect against faults between live conductors, and it does not protect against dangerous voltages that might enter the installation through the supply neutral. So we still need all the other protective measures required by Clause 2.4. When a fault to earth happens, the RCD must automatically disconnect the supply at a level of earth leakage current that has been set beforehand. That is the essential purpose of additional protection. Clause 2.6.3.3, Installation Requirements, New Zealand only. This clause explains when New Zealand installations must have an RCD for extra protection. For residential installations, extra protection by an RCD with a maximum residual current of 30 mA must be provided for final subcircuits that supply one or more socket outlets, or one or more lighting points, or directly connected handheld equipment such as hairdryers or tools. This also includes combination fan and light units, smoke alarms, bathroom exhaust fans, and ceiling sweep fans, because these are all treated as lighting points. The rule applies across individual domestic installations, residential areas of other electrical installations, multiple residential buildings, and shared external lighting areas. Where RCD protection is required, the device must be fitted at the switchboard where the final subcircuit originates. There are a few exceptions. If a different method of protection is already used that will automatically disconnect the supply under a fault, such as separated supply or extra low voltage, then an RCD might not be required. Another exception applies when a socket outlet is supplying a fixed cooking appliance such as a range or oven or hot plate unit. In those cases, the socket outlet must be placed where it is not likely to be accessed by the general public, and it must be clearly marked to show its restricted use. Clause 2.6.3.3.2, Non-residential installations, New Zealand only. In non-residential installations, 30 mA CD protection must be provided for socket outlets rated not more than 30 A in education and childcare facilities, including kindergartens, daycare centers, and schools up to Year 13, as well as tertiary or vocational training areas. The purpose is to protect children and young people who may not recognize shock hazards. For junior education and childcare facilities, a CD with a maximum rated residual current of 10 mA must be used for socket outlets in areas where teaching or caring for children takes place. These CDs do not need to be Type A unless required for medical devices. Other locations also need a CD protection where socket outlets are used for handheld equipment. This includes outdoor areas, unsupervised public places, and amusement arcades. Some situations are exempt. If another method of fault protection is already used, such as separated supply or extra low voltage, a CD may not be needed. Another exemption applies in places where disconnecting the circuit by an CD would cause a danger greater than the leakage current risk, such as some traffic signal circuits. There are also exemptions for mining sites using reduced low voltage. Clause 2.6.3.3.3 Home care installations, New Zealand only. Where medical electrical equipment is installed in home care situations, some devices must be protected by a Type I CD with a maximum rated residual current of 10 mA, and with a faster tripping time. These installations follow the medical standard as NZS 3003. Clause 2.6.3.3.4 Additions and alterations, New Zealand only. When circuit protection on an existing switchboard is replaced, additional CD protection must be added to the final subcircuit supplied from that switchboard. If socket outlets are added to an existing circuit, and CD protection is required, the CD should ideally be installed at the start of the subcircuit, but it may also be installed at the beginning of the new wiring only. Any new CDs must be recorded at the switchboard. There are two small exceptions. If a socket outlet that is not CD protected is simply replaced with the same type, the rule does not apply. And if socket outlets are added under an exemption that already applies in Clause 2.6.3.3.1 or Clause 2.6.3.3.2, then extra CD protection is not required. Clause 2.7 Protection against overvoltage. Clause 2.7.1 General. When we talk about protection against overvoltage, we are talking about keeping people and property safe if the voltage in the installation suddenly rises above what the system is designed for. This can happen for a few different reasons. A fault could happen between a low voltage circuit and a higher voltage circuit. Switching operations can create sudden spikes. Lightning can also cause dangerous voltage surges, especially in areas where lightning is common. Resonant effects in the network can also push the voltage higher than expected. The idea is simple. Where high voltage could cause danger, we must provide suitable protection so the installation stays safe. Clause 2.7.2 Protection by insulation or separation. This clause is about stopping dangerous voltages from getting into other parts of the installation when two circuits of different voltages sit close to each other. The protection can be achieved by using strong insulation, by screening, or by separating the circuits far enough apart so they can't affect each other. For conductors, we use proper insulation screening or physical segregation so a fault can't easily jump across. For transformers, we use similar ideas, strong insulation between windings, or a conductive screen that is earthed, so any fault energy is safely carried away and the supply disconnects if needed. Transformer windings that operate at different voltages must be clearly separated. If a fault does occur inside a transformer, the design must make sure that the protective device will disconnect the supply quickly. Clause 2.7.3 Protection by protective devices. Sometimes we use protective devices to control overvoltage. These devices limit the sudden voltage rise to a level that the installation can safely handle. They must operate fast enough to keep the voltage below the insulation strength of the equipment. They also need to be suitable for the highest voltage that could appear in normal operation, and must not create danger during operation. This standard does not force you to install surge protection devices for lightning. If lightning is a significant risk in your area, another standard explains how to decide on proper lightning protection and which devices to use. Clause 2.8 Protection against undervoltage. Clause 2.8.1 General. Now we move to undervoltage protection. Undervoltage means the supply drops too low, or the voltage is lost and then comes back. Both situations can be dangerous. If the voltage disappears and then suddenly returns, some equipment can start unexpectedly. Imagine a guillotine, a press, or a powered gate suddenly coming back to life. If the voltage drops too low, motors may struggle to start or run, which can cause overheating or even failure. So we provide undervoltage protection when low voltage could create danger for people or property. But if the equipment can safely handle a short interruption without danger, then undervoltage protection is not required. Clause 2.8.2 Selection of protective device. The protective device used for undervoltage must suit the equipment it is protecting. It must follow the requirements and the relevant standards for starting motors and running electrical equipment. If switching the device back on could be dangerous, it must not automatically reclose. For example, if the supply drops out and comes back, we do not want a dangerous machine restarting by itself unless it is designed for safe automatic restart. Instant disconnection by the undervoltage device must not be slowed down by mechanical delays in its contacts. There is one exception. If a short loss of voltage is not dangerous for the equipment, the undervoltage device can be allowed to delay its operation. Undervoltage protection is often provided by special relays or releases that open a switch or breaker when the voltage drops. Non-latched contactors are also used in many installations, because they drop out naturally when voltage is too low. Clause 2.9 Protection against fire hazard due to arcing faults. Clause 2.9.1 General. In this part of ASNZS 3000, we talk about arcing faults and the fire risk they create. An arcing fault is when electricity jumps across a damaged or loose connection. It creates heat, sparks, and can easily start a fire inside a wall, a socket, or a cable. Arc fault detection devices, spoken as AFDDs, are designed to detect this kind of fault early and disconnect the supply before a fire can start. They add protection for final subcircuits, especially in places where a fire would be very dangerous. Common places where AFDDs are useful include any area where people sleep, places where flammable materials are stored or processed, buildings made from combustible materials such as timber, and any structure where fire can spread quickly. The standard explains that AFDDs are an extra layer of safety. They do not replace other protective requirements. Clause 2.9.2 Type. Any AFDD used in an installation must comply with standard IEC 62606. This ensures the device can correctly detect and disconnect arcing faults. Clause 2.9.3 Rating. The AFDD must have a load current rating that is at least equal to the circuit protective device it works with. In other words, it must be sized so it can safely operate on that circuit. Clause 2.9.4 Arrangement. The AFDD must be installed at the switchboard where the final subcircuit begins. This gives full protection for the entire circuit. Clause 2.9.5 Alterations. When you alter an existing installation, especially old wiring that may be damaged or weakened, you should consider installing an AFDD for extra protection. Things like vermin damage, aged insulation, or brittle wiring can increase the chance of an arcing fault, so adding an AFDD can help reduce the fire risk. Clause 2.9.6 Final subcircuits in Australia. This part is not applicable to New Zealand because Australia does not require AFDD installation. For New Zealand, use the next clause. Clause 2.9.7 Final subcircuits in New Zealand. In New Zealand, AFDD protection is required for any final subcircuit rated at 20 amps or less when it supplies locations with a higher fire risk. These include places where flammable or combustible materials are processed or stored, such as farm sheds, woodworking shops or storage areas, places containing irreplaceable items, historic buildings built from flammable materials, and school dormitories where socket outlets supply student areas. In these locations, wiring faults can lead to fire, so the standard requires an AFDD to be installed at the switchboard that feeds these subcircuits. The notes explain that if the wiring is in poor condition, such as circuits passing through high-risk areas, AFDD protection is strongly advised even if it is not strictly required. Section 2.10 Switchboards. Clause 2.10 begins by telling us the basic idea of a switchboard. A switchboard is the place where we mount and enclose the switchgear and the protective devices for the installation. In simple terms, this is the control center of the electrical system. Clause 2.10.1 explains the general requirement. Every installation needs a switchboard, or sometimes more than one, so that we have a safe and organized location for the main switches, the protective devices, and any other necessary control equipment. The standard also reminds us that a main switchboard must be provided for every electrical installation. This is the switchboard that contains the main switch or switches, and the main protective devices. In some rare cases, the main switch does not need to be located directly on the main switchboard, but it still has to be close enough to be safely reached and operated when needed. Clause 2.10.2 covers the location of switchboards. Switchboards need to be placed in suitable, well-ventilated areas. They must be protected from moisture and must be arranged so that electricians can safely install, replace, or maintain equipment inside the board. That means there must be enough room in front of the board, and enough space for tools and hands to work safely. The access requirements continue with the idea that people must be able to safely reach and operate the equipment. The standard says there must be a clear space in front of the switchboard to allow safe operation and adjustment. For normal installations, this space is at least 1 meter from the face of the board. In a domestic installation, this can be reduced to 0.6 meters from the front. Around switchboard doors, we need at least 0.6 meters of clear space so the doors can open and close safely. No one should be forced into the switchboard or trapped by a door. This is especially important when the doors open into passageways or narrow walkways. The script continues with the requirement for safe exit paths. If a fault happens at the switchboard, people must be able to move away quickly without being blocked by equipment, shelves, or obstacles. This is why exit pathways around switchboards must be clear. Clause 2.10.2.3 explains the requirements for locating the main switchboard. It must be readily accessible. In multiple building sites or multiple tenancy buildings, the main switchboard must not be hidden inside a single tenant's area. It has to be in a location where authorized people can reach it easily and quickly. Clause 2.10.2.4 explains identification of main switchboard. The main switchboard must also be permanently marked with the words main switchboard. The label must be clear, easy to read, and made of durable material. If the room or enclosure itself is the main switchboard room, that room must also be clearly marked, unless the installation is a small domestic one where the location is obvious. Clause 2.10.2.5 covers restricted locations. There are several places where switchboards cannot be installed. For example, a switchboard cannot be installed less than 1.2 meters above the ground unless special conditions are met. A switchboard cannot be installed above water containers or above cooking appliances unless it is fully enclosed and protected from splashing. A switchboard inside a cupboard must be placed in its own dedicated section of the cupboard, with nothing else stored in that space. The cupboard doors must allow safe operation and safe maintenance. The standard also warns against installing switchboards near swimming pools, spas, or in any damp situation zone because of the higher risk of electric shock. Switchboards must not be installed inside a sauna, inside refrigeration rooms, inside fire-isolated stairways, or in areas classified for hose-down sanitizing unless the degree of protection is appropriate. Switchboards must not be installed in the path of fire exits because smoke from a switchboard fault can block escape routes. If a switchboard is placed inside a cabinet or compartment, the doors must be sealed to stop smoke escaping into the escape path. The standard also restricts installations near fire sprinklers. A switchboard cannot be placed where a sprinkler head could spray water onto it, unless the switchboard has protection to at least IPX4, or a shield is provided, or deflectors are fitted to the sprinkler heads. Finally, the standard covers hazardous areas. A switchboard must not be placed in a hazardous area, such as an area with flammable gas or vapor, unless the switchboard is specifically designed and certified for installation in that hazardous zone. This completes the spoken explanation of Section 2.10 on switchboards. It covers what a switchboard is, where it must be located, how it must be accessed, how it must be marked, and the many places where it must not be installed. End of Section 2.10. Clause 2.10.3 Construction. Clause 2.10.3.1 Access to live parts. This clause explains how live parts inside a switchboard must be arranged so that people cannot accidentally touch them. The idea is simple. Basic protection must come from covers, enclosures or barriers, just like we talk about in Clause 1.5.4. There is one exception for non-domestic electrical installations. In some commercial or industrial sites, live parts can be exposed, but only when access is restricted to authorized and trained people, and when the area can be locked or controlled so the public cannot get near it. If removing a cover or panel will expose live parts, then that cover must be clearly marked so anyone opening it understands the danger. This marking follows the requirements of ASNZS 61439.1. Domestic switchboards do not require this marking. Clause 2.10.3.2 Suitability. Switchboards must be strong enough to cope with real-world stresses. That includes mechanical forces, heat, electrical faults and anything in the environment where the switchboard is installed. A switchboard that complies with the ASNZS 61439 series, or the ASNZS 3439 series, is accepted as meeting these requirements. A switchboard must also meet these requirements if either of two things occur. First, the connected load at the switchboard is greater than 125 amperes root mean square per phase. Or second, the prospective short circuit current at the incoming terminals is greater than 10 kiloamps root mean square. Clause 2.10.3.3 Minimum clearances and creepage distances. Any bare conductors or live parts must be fixed in place with enough clearance or creepage distance in air. This spacing prevents accidental flashover or tracking between different phases or between phase and earth. The distances must match the ASNZS 61439 series. Smaller clearances may be used only when the equipment is manufactured and tested to its own standard, or when the live parts are insulated from earth in a way that ensures safety. Clause 2.10.3.4 Orientation and location of fuses and circuit breakers. Clause 2.10.3.4.1 Orientation of circuit breakers. If more than one circuit breaker is mounted in a row, they must all operate in the same direction so that the off and on positions are clear and consistent. You must always be able to see which position each device is in. Clause 2.10.3.4.2 Location of fuses and circuit breakers. Fuses and circuit breakers must be placed so that their purpose and relationship to each circuit is obvious. They may be installed on the back of a panel or escutcheon only in specific situations, such as when used solely as a fault current limiter or when used for control or instrumentation equipment. Combination fuse switch devices may also be mounted behind a panel if they can still be operated safely from the front. Clause 2.10.3.5 Screw-in fuses. Screw-in fuses must be installed so that the center contact connects to the supply side of the base. This prevents accidental contact with live parts. Clause 2.10.4 Bars. Clause 2.10.4.1 General. Bars must be designed so that conductors can be securely terminated. They must follow the requirements in Clause 3.7. Clause 2.10.4.2 Tunnel-type terminals. Tunnel-type terminals that take a conductor directly must not damage the conductor. Terminals must have one of the following: 2 screws, or 1 screw with a diameter at least 80% of the tunnel diameter. Tunnel-type terminals used for the main incoming neutral, the main earthing conductor, the earthing connection, or the neutral bar including the PEN conductor must follow this requirement. Clause 2.10.4.3 Neutral bar. Any switchboard that has a neutral conductor must have a neutral bar that can safely carry the neutral current. It must be positioned so every conductor can be connected without stretching or stressing the cable. The neutral bar must be designed so the incoming neutral cannot be accidentally disconnected. It must also have separate terminals for the incoming neutral and each outgoing circuit. When tunnel terminals are used for the neutral bar, the same rules from Clause 2.10.4.2 apply. Clause 2.10.5 Equipment identification. Clause 2.10.5.1 General. All equipment on a switchboard must be clearly and permanently marked in English. The identification must be easy to understand so anyone working on the switchboard can tell which switch or device supplies which part of the installation. Clause 2.10.5.2 Relationship of electrical equipment. Switches, circuit breakers, fuses and similar equipment must be labeled so their purpose is obvious. Clause 2.10.5.3 Bars. Bars must be marked to show whether they are active, neutral or earth. Domestic switchboards do not need this if the bar colors are clearly visible. Clause 2.10.5.4 Terminals of switchboard equipment. All terminals for incoming and outgoing conductors must be clearly marked so the correct conductor is connected to the correct circuit. The main connection and the connection for the main neutral conductor must be marked at the main neutral bar unless the neutral conductor continues directly through without a break. Clause 2.10.5.5 Common neutral. If one neutral bar is used for more than one circuit, it must be permanently marked so that each neutral conductor can be identified correctly. Clause 2.10.5.6 Fuse. If the fuse marking does not clearly show the rating must be marked either on the fuse, on the panel, or next to it. Fuses used as a group must be arranged so their ratings are easy to compare. Clause 2.10.6 Wiring. Switchboard wiring must be installed so it can withstand the heat and magnetic forces that occur during faults. Where panels need to be moved for maintenance, the wiring must be long enough to allow safe movement, must be held in place to prevent strain, and must be arranged so cables are not crushed behind the panel. Clause 2.10.7 Fire protective measures. Switchboard wiring must be installed in a way that slows the spread of fire. Openings into the enclosure must be sealed so flames or smoke cannot pass easily through. Any hole larger than 5 mm must be sealed with fire-resistant material. Larger conduits and wiring enclosures must also be sealed to prevent air movement that could spread fire. That brings us to the end of Section 2. You can see that this section sets the foundation for electrical safety, from how we protect people against electric shock, right through to how we install and position switchboards. If you understand these ideas well, the later sections of the standard will make a lot more sense. Thanks for listening, and when you're ready, we'll move on to the next section together. Hi everyone, my name is Aria, and I work alongside Whit Roy as an electrical tutor. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 3000, 2018. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for EWRB exam. What this audiobook does is take the key ideas from the standard and explain them in simple, spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real installations. So think of this as a learning companion, not a replacement for the actual standard. Alright, let's get started. Today we're moving into Section 3, Selection and Installation of Wiring Systems, which focuses on wiring systems. In this section, we'll look at how cables and wiring systems must be selected, installed, supported, protected, and enclosed so they remain safe throughout their service life. Everything in this section is about good installation practice, preventing damage, managing heat, allowing for movement, and making sure wiring systems are suitable for the environment they are installed in. This section sets out the practical rules electricians use every day on site, and it links closely with earlier safety principles to make sure installations remain reliable, durable, and safe under normal use and foreseeable conditions. Clause 3.1 General. This part explains that this section sets the minimum rules for choosing and installing wiring systems, and these rules must be met so the installation satisfies the overall safety requirements of the standard. Clause 3.1.1 Application. This clause means the requirements in this section apply to how wiring systems are selected and installed, and the goal is to meet the basic safety outcomes required by Part 1 of the standard. Clause 3.1.2 Selection and Installation. This clause explains that wiring systems must be chosen and installed so they work safely and correctly. They must protect people from touching live parts, either by strong insulation or by keeping live parts out of reach. They must be suitable for carrying current, controlling voltage drop, and meeting minimum size rules for conductors. Connections, joints, and terminations must be reliable and electrically continuous. Supports, suspensions, and fixings must be strong enough for the wiring system. The wiring system must suit its intended use, including special situations such as fire resistance, explosion protection, or safety services. It must be protected from mechanical damage and from environmental or other external effects, using enclosures or other suitable methods. Installation must follow the requirements of this section as well as any extra instructions given by the manufacturer. This clause also highlights that things like conductor material, core identification, insulation properties, temperature rise, bending limits, and tension limits must all be considered. Clause 3.2 Types of wiring systems. This clause states that the type of wiring system and how it is installed must either follow the options set out in Table 3.1 or provide an equivalent level of safety to what is given there. Clause 3.3 External influences. This clause introduces the idea that wiring systems must be able to work safely and properly under the environmental and other conditions they are likely to face at the place of installation. Clause 3.3.1 General. This clause explains that wiring systems must operate safely and function as intended in the conditions they are exposed to. Protection against environmental and other influences can be achieved through suitable design and construction of the wiring system itself, or by adding extra protective measures as part of the installation, as long as those measures do not interfere with normal operation. Clause 3.3.2 Particular influences. This clause signals that specific types of environmental and external conditions must be considered in more detail in the following clauses. Clause 3.3.2.1 Ambient temperature. This clause means wiring systems must be chosen and installed so they are suitable for the highest and lowest local ambient temperatures. Where materials have temperature limits above 60 degrees Celsius or below 0 degrees Celsius, the manufacturer's instructions must be followed. Allowance must be made for expansion of materials caused by normal temperature changes. Where current carrying capacity is selected using as NZS 3008.1, the reference ambient temperature for New Zealand is 30 degrees Celsius for cables in air, and 15 degrees Celsius for cables buried in the ground or installed underground. Clause 3.3.2.2 External heat sources. This clause explains that wiring systems must be protected from heat coming from outside sources, including sunlight. Protection may be achieved by shielding, placing the wiring far enough away from the heat source, selecting a system that allows for extra temperature rise, limiting the current carried to reduce operating temperature, reinforcing or replacing insulation locally, or using another method that gives equivalent protection. Parts of cables or flexible cords within accessories, appliances, or luminaires must be suitable for the temperatures they will experience, or have extra insulation suited to those temperatures. Clause 3.3.2.3 Water or high humidity. This clause requires wiring systems to be selected and installed so that moisture or water entry does not cause damage. Where water may collect or condensation may form and create a hazard, provision must be made for safe drainage. Where wiring systems may be exposed to wave action or moving water, Protection against excessive flexing and mechanical damage must be provided in line with the relevant clauses. Clause 3.3.2.4 Solid foreign bodies. This clause means wiring systems must be selected and installed to reduce the entry of solid objects during installation, use and maintenance. Where dust or other substances may be present in large amounts, extra precautions must be taken to prevent build-up that could reduce heat dissipation. Clause 3.3.2.5 Corrosive or polluting substances. This clause explains that where corrosive or polluting substances may cause deterioration, affected parts of the wiring system must be protected or made from materials that resist those substances. Metals that can cause galvanic action must not be placed in contact with each other. Materials that could cause deterioration or hazardous degradation must also not be placed together. Clause 3.3.2.6 Mechanical damage. This clause requires wiring systems to be selected and installed to reduce the risk of mechanical damage. Protection can be provided by the inherent strength of the wiring system, by choosing a suitable location, or by adding local or general mechanical protection, or by a combination of these methods. Clause 3.3.2.7 Vibration. This clause means wiring systems exposed to vibration that could cause damage, including cables, fixings, and connections, must be suitable for those conditions. Clause 3.3.2.8 Other mechanical stresses. This clause explains that wiring systems must be selected and installed to minimize damage to insulation, sheathing, and connections during installation, operation, and maintenance. Measures may include providing adequate supports at suitable intervals, using fixings that hold the cable without damage, using connections that reduce strain at joints and terminations, observing minimum bending radius limits, and allowing flexibility to accommodate movement or tension. Clause 3.3.2.9 Flora. This clause states that where plant growth is likely to create a hazard, the wiring system must be selected accordingly or special protective measures must be used. Clause 3.3.2.10 Fauna. This clause means that where animals are likely to create a hazard, the wiring system must be selected accordingly or protected by special measures. Clause 3.3.2.11 Solar radiation, direct sunlight. This clause explains that where wiring systems may be exposed to direct sunlight, they must either be suitable for those conditions or be adequately shielded. Sheathed cables exposed to sunlight generally do not need extra protection from ultraviolet radiation unless the manufacturer advises otherwise. Black insulated unsheathed cables with ultraviolet-resistant insulation that complies with ASNZS 3008 do not need extra protection. For other insulation colors, the manufacturer's advice should be followed or a physical barrier provided. Direct sunlight can affect current carrying capacity, and a correction factor may be applied where the cable temperature is higher than ambient. Clause 3.3.2.12 Hazardous areas. This clause states that wiring systems installed in areas with explosive gas or explosive dust atmospheres must be selected and installed in accordance with the relevant hazardous area requirements. Clause 3.3.2.13 Thermal insulation. This clause explains that where cables pass through bulk thermal insulation, their current carrying capacity must be rated according to the length of cable within the insulation. Short lengths up to 150 mm use the in-air rating, longer lengths up to 400 mm use the partially surrounded rating, and lengths greater than 400 mm use the completely surrounded rating. Clause 3.4 Current carrying capacity. This clause sets the overall requirement that conductors must be capable of carrying electrical current safely without overheating, and that current carrying capacity is a key factor in the selection and installation of wiring systems. Clause 3.4.1 General. This clause explains that every conductor must have a current carrying capacity selected in accordance with ASNZS 3008.1. and that this capacity must never be less than the current the conductor is expected to carry in service. When determining the required capacity, allowance must be made for changes that can reasonably be expected to occur over time, such as changes to the environment around the wiring. One specific example is domestic installations, where wiring systems must be installed on the assumption that thermal insulation may be added later in ceilings, walls, or underfloors, even if it is not present at the time of installation. This requirement does not apply to existing wiring systems when a circuit is simply being extended or altered. Clause 3.4.2 Operating temperature limits. This clause states that conductors must operate within the temperature limits specified for their insulation type. The operating temperature must not exceed the limits set out for normal use or maximum permissible conditions. It also makes clear that polymeric cables with normal operating temperatures below 75 degrees Celsius are not considered suitable for use in Australia or New Zealand. The clause highlights that different cable insulation materials have different temperature limits, including limits for normal operation, short-term maximum temperature, and minimum ambient temperature, and these limits must be respected during installation and operation. Clause 3.4.3 Conductors in parallel. This clause explains how current carrying capacity is determined when conductors are connected in parallel. Where circuits use parallel multi-core cables or groups of single-core cables, the total current carrying capacity may be calculated as the sum of the capacities of the individual cables, provided certain conditions are satisfied. The cables must meet minimum size requirements, and the grouping of cables must not reduce their ability to cool in air or in the ground. The sharing of load current between parallel cables or groups must be sufficient to prevent overheating of any individual cable. Equal sharing of load current can be achieved by selecting cables of the same material and cross-sectional area, ensuring the cables follow the same route and have the same length, making sure the conductors of each parallel cable or group are effectively joined together at each end, and arranging phase and neutral conductors so that the effects of mutual impedance are taken into account. Unequal current sharing between cables or groups may be permitted where the design current and overcurrent protection for each cable or group are considered individually. Clause 3.4.4 Coordination between conductors and protective devices. This clause requires coordination between the continuous current carrying capacity of conductors and the rating of the protective devices used in the circuit. The cable capacity must be matched with the current for which the circuit is designed, as well as the type and rating of the overload protective device. Because fuses and circuit breakers have different operating characteristics, different limits apply. The current rating of a circuit breaker must not be greater than the current carrying capacity of the cable, and the current rating of an HRC fuse must not be greater than 90% of the cable current carrying capacity. Clause 3.5 Conductor size. This clause introduces the requirements that apply to the minimum physical size of conductors used in wiring systems. Clause 3.5.1 General. This clause states that the nominal cross-sectional area of conductors must not be less than the minimum values specified for the type of wiring system and the intended use of the circuit. These minimum sizes are set to ensure adequate current carrying capacity, mechanical strength, and reliable connections. Clause 3.5.2 Neutral conductor. This clause explains how the minimum size of a neutral conductor is determined. For a single-phase 2-wire circuit, the neutral conductor or conductors must have a current carrying capacity that is not less than that of the associated active conductor, or not less than the total current to be carried where more than one active conductor is present. For multi-phase circuits, the neutral conductor must be sized so its current carrying capacity is not less than the value determined by the expected loading conditions. Where substantial harmonic currents may be present, such as from nonlinear loads, the third and higher order harmonic currents in the neutral must be taken as 100% of the highest load generated harmonic current on any phase. In consumer mains, submains, and final subcircuits, the current carrying capacity of the neutral conductor must not be less than that of the largest associated active conductor. Certain exceptions are allowed where abnormal conditions or protective arrangements limit the neutral current. Clause 3.5.2 PE in conductors. This clause states that where a combined protective earth and neutral conductor is used for consumer mains or submains forming a separate MEN installation, the minimum size of the PEN conductor must comply with the requirements that apply to active or neutral conductors as appropriate, and must also not be smaller than the size required for an earthing conductor. Clause 3.5.3, Earthing conductor. This clause explains that the size of an earthing conductor must be determined in accordance with the requirements set out in Clause 5.3.3. Clause 3.6, Voltage drop. This clause introduces the requirement to control voltage drop so that electrical equipment operates safely and correctly under normal service conditions. Clause 3.6.1, General. This clause explains that, during normal operation, the voltage available at the terminals of any power-consuming electrical equipment must not fall below the lower limit specified in the relevant equipment standard. Where no specific equipment standard exists, the voltage at the terminals must still be sufficient to ensure the equipment operates safely and properly without impairment. Clause 3.6.2, Value. This clause states that the cross-sectional area of every current-carrying conductor must be selected so that the voltage drop between the point of supply for the low-voltage installation and any point within that installation does not exceed 5% of the nominal supply voltage. The current value used when calculating voltage drop does not have to be greater than the total connected load, or the maximum demand of the circuit, or the current rating of the circuit protective device. This clause also explains that short-term transient effects, such as those caused by motor starting or similar operations that produce brief high currents, are not included in the voltage drop assessment. Simplified estimation methods and conductor size selection guidance are provided elsewhere, and special arrangements apply for reverse voltage rise in grid-connected inverter systems. Specific exceptions allow alternative limits in defined situations, including certain final subcircuits, installations supplied directly from on-site substations, and standalone systems where the overall voltage at equipment remains within acceptable limits. Clause 3.6.3, Conductors in parallel. This clause explains that where conductors are connected in parallel, the voltage drop for the circuit is taken as the voltage drop in one conductor carrying its share of the circuit current, with the total circuit current divided equally between the parallel conductors in accordance with the earlier voltage drop requirements. Clause 3.7, Electrical connections. This clause introduces the requirements for making electrical connections that are electrically sound, mechanically secure, and suitable for long-term service. Clause 3.7.1, General. This clause explains that connections between conductors, and between conductors and electrical equipment, must maintain electrical continuity, provide appropriate insulation, and have adequate mechanical strength. The method used to join or connect conductors must suit the application and ensure the conductivity of the joint is not less than that of the conductor itself. All cables and conductors must be installed so that no undue mechanical stress is placed on any connection. Clause 3.7.2, Connection methods. This clause introduces the acceptable methods and requirements for connecting conductors. Clause 3.7.2.1, General. This clause states that the selection of a connection method must take into account the conductor material and its insulation, the number and shape of wires forming the conductor, the cross-sectional area, the number of conductors being connected together, the temperature reached by terminals in normal service, and the need to prevent moisture entry or water siphoning through cables or enclosures. Clause 3.7.2.1.1, Common requirements. This clause reinforces that all of these factors must be considered together so that the connection remains safe, insulated, and reliable in service. Clause 3.7.2.1.2, Aluminium conductors. This clause explains that joints and connections involving aluminium conductors must use components and techniques specifically designed for aluminium. Special considerations include removing aluminium oxide from the conductor, accounting for the softness of aluminium, allowing for different thermal expansion compared with other metals, and avoiding contact with dissimilar metals that could cause galvanic action. Clause 3.7.2.2, Preparation for connection. This clause states that insulation must only be removed as much as necessary to make the connection. Where insulated conductors are joined, the joint must be insulated to a level not inferior to the original conductor insulation, and any damaged insulation must be reinstated. Clause 3.7.2.3, Loosening of connections. This clause explains that connections must be made so that loosening is unlikely under normal service conditions, including vibration, material changes and temperature variations. Clause 3.7.2.3.1 General. This clause reinforces that connections must remain secure throughout normal operation. Clause 3.7.2.3.2 Crimp joints, compression joints. This clause explains that crimped or compressed connections must be securely retained within a suitable crimping device and made using tools and techniques specified by the manufacturer. Clause 3.7.2.4 Mechanical connection devices. This clause states that mechanical connection devices may be used where they comply with the relevant standard, do not rely on compression of insulation for electrical contact, have suitable short circuit ratings, provide long-term current carrying capacity not less than the connected conductors, do not deteriorate if reused where permitted, include manufacturer information for correct use, and are installed using approved techniques. Clause 3.7.2.5 Retention of stranded conductors. This clause explains that the ends of stranded conductors must be secured to prevent strands from spreading or escaping, and they must not be soft soldered before being clamped under screws or between metal surfaces. Clause 3.7.2.6 Mechanical stress. This clause requires that all cables and conductors be installed so that no undue mechanical stress is applied to any connection. Clause 3.7.2.7 Soldered connections. This clause explains that where soldered connections are used, the design must account for creep, mechanical stress, and temperature rise under fault conditions, and that soft soldered connections must not be clamped under screws or between metal surfaces. Clause 3.7.2.8 Flexible cords. This clause states that joints and flexible cords used as installation wiring must meet the same connection requirements or use suitable couplers, and that flexible cords must be installed so that pulling forces are relieved by proper means rather than knots. Clause 3.7.2.9 Aerial conductors. This clause introduces special rules for joints and connections in aerial conductors. Clause 3.7.2.9.1 Joints and connections. This clause explains that joints in aerial conductors under tension must not be soldered, must be reliable and well protected from movement, sunlight, and moisture, and must be kept as short as practicable. Where dissimilar metals are joined, measures must be taken to prevent galvanic action. Clause 3.7.2.9.2 Prohibited joints. This clause states that joints must not be made, when under tension, in certain types of cables including parallel webbed aerial cables, neutral screened cables, multi-core cables, or conductors of different metals. Clause 3.7.2.10 Underground cables. This clause explains that connections in underground wiring must be sealed to prevent moisture entry. Clause 3.7.2.11 Earthing conductors. This clause states that soldered earthing connections must be mechanically secured independently of the solder, and that tunnel-type terminals must be designed to clamp conductors effectively without cutting them. Clause 3.7.3 Joints and cables. This clause explains that joints and cables must normally be enclosed to protect against external influences, unless specific conditions are met such as no undue strain, compliance with connection requirements, reinstated mechanical protection, and restored insulation and sheathing equivalent to the original cable. Clause 3.7.4 Installation couplers. This clause explains that installation couplers complying with ASNZS 61535 may be used as a permanent connection method for cables, are considered equivalent to a junction box, and are not intended to be connected or disconnected under load. Clause 3.8 Identification. This clause introduces the requirements for identifying conductors so their function is clear and unambiguous. Clause 3.8.1 General. This clause explains that installation wiring conductors must be clearly identified according to their function as active, neutral, earthing, or equipotential bonding conductors, and where color is used, the specified color system must be followed. Clause 3.8.2 Color identification. This clause introduces identification by color or by sleeving. Clause 3.8.2.1 Color identification by sleeving or other means. This clause explains that sleeving or other color identification methods may be used at terminations to identify conductors where appropriate, provided the identification is durable, color-fast, and compatible with the installation. Clause 3.8.2.2, Sleeving of existing earthing and bonding conductors. This clause explains that existing bare or green earthing or bonding conductors installed under previous rules may remain, but where alterations or repairs create new terminations, those conductors must be sleeved green and yellow at the new connection points. Clause 3.8.2.3, Sleeving of existing live conductors. This clause explains that existing live conductors with yellow insulation may remain, but where new terminations or joints are made, white sleeving must be applied at those new points. Clause 3.8.3, Exceptions and special applications. This clause introduces situations where the standard color rules do not apply. Clause 3.8.3.1, General. This clause explains that the standard color identification rules may be relaxed for specific applications covered in the following clauses. Clause 3.8.3.2, Protective earthing and equipotential bonding conductors. This clause explains that earthing conductors do not need to be green and yellow in certain cases, such as bare or aerial earthing conductors, suitable screens used as earthing conductors, insulated earthing conductors not manufactured in green and yellow, or multi-core cables with a dedicated green earth, provided clear identification is applied where needed. Clause 3.8.3.3, Active and neutral conductors. This clause explains that active and neutral conductors may use alternative identification methods where conductors are within multi-core cables and clearly marked. Flexible cords are identified by approved alternative colors, or neutral conductors are distinguished by physical features such as ribs. Clause 3.8.3.4, Alternative and European cable identification colors. This clause explains that alternative and European color systems exist, that care must be taken when connecting imported equipment, and that verification is necessary to confirm correct function and connection. Clause 3.8.3.5, Aerial earthing conductors. This clause states that aerial earthing conductors must be identified at each end of the run, either by the letter E or by the earthing symbol. Clause 3.9, Installation requirements. This clause sets out how wiring systems must be installed so they remain safe, reliable, and fit for service over their full life, taking into account normal use, foreseeable misuse, wear and environmental conditions. Clause 3.9.1, General. This clause explains that wiring systems must be installed using accepted good electrical practice. The methods used must protect the installation against mechanical damage, electrical failure, deterioration from normal wear, and abnormal conditions that can reasonably be expected. The overall intent is that the installation remains electrically sound and mechanically secure in everyday service. Clause 3.9.2, Methods of installation. This clause explains that common installation methods for wiring systems are recognized and set out elsewhere in the section. The effects of external influences at the installation location must always be considered, together with the manufacturer's instructions. Installation methods not specifically shown may still be used, provided the general safety and performance requirements of this section are met. Clause 3.9.3, Support and fixing. This clause introduces how wiring systems must be physically supported and fixed. Clause 3.9.3.1, General. This clause states that wiring systems must be supported by suitable means and fixed using clips, saddles, clamps, or similar devices that do not damage the cable and are not adversely affected by the wiring materials or the surrounding environment. Where wiring passes through building elements, openings must not weaken the structure below the limits required by building codes. Where sheath cables pass through metal structural members, edges must be treated to reduce abrasion. Where disturbance is likely, cables must be fixed close to the opening. Certain exceptions apply where wiring rests on a continuous immovable surface or where alternative fixing methods provide equivalent strength and support. Clause 3.9.3.2, Suspended ceilings. This clause explains that wiring systems in suspended ceilings may be supported by the ceiling system unless the ceiling manufacturer does not allow it. Where cables are in contact with conductive ceiling supports, additional mechanical protection is required. Wiring above suspended ceilings must be fixed at suitable intervals to prevent sagging. The clause clarifies that timber ceiling systems covered by other standards are not included. Clause 3.9.3.3 Wiring systems likely to be disturbed. This clause identifies locations where wiring is considered likely to be disturbed, such as accessible wall surfaces, areas beneath floors, ceiling spaces with sufficient access height, and locations close to access openings. Clause 3.9.3.3.2 Support and protection. This clause requires wiring in disturbed locations to be supported at suitable intervals, secured to prevent accidental withdrawal from equipment, and protected against mechanical damage. It clearly states that ASNZS must not be used as a substitute for mechanical protection where wiring is likely to be disturbed. Clause 3.9.4 Protection against mechanical damage. This clause sets out when and how wiring must be protected from physical damage. Clause 3.9.4.1 General. This clause states that wiring systems installed where mechanical damage may reasonably be expected must be adequately protected, using the methods specified later in this clause group. Clause 3.9.4.2 Wiring systems near building surfaces. This clause explains that wiring fixed or restrained close to walls, floors, ceilings, or roofs must be protected if it is within 50 mm of the surface. The intent is to prevent damage from nails, screws, or similar fixings. The requirement does not apply where the wiring can freely move away from the surface if penetration occurs. Clause 3.9.4.3 Wiring systems under wall lining or roofing material. This clause states that wiring must not be installed in the narrow spaces formed between wall or roof linings and their immediate supporting members, as these locations present a high risk of damage. Clause 3.9.4.3.2 Protection required. This clause explains that where wiring passes through structural members or is fixed close to supporting members, appropriate protection must be provided to reduce the risk of mechanical damage. Clause 3.9.4.4 Protection methods. This clause explains that protection may be achieved by providing adequate mechanical protection, by using earthed metallic protection capable of operating a short-circuit protective device under fault conditions, or by protection using an RCD with a maximum rated residual current of 30 mA. Additional notes clarify how these methods apply to different wiring systems. Clause 3.9.5 Wiring systems installed vertically. This clause explains that vertically installed wiring systems must be arranged to avoid damage caused by their own weight. Adequate support must be provided, with support spaced to prevent strain, typically not exceeding 8 meters unless otherwise recommended by the manufacturer. Clause 3.9.6 Change of direction. This clause requires that changes in direction must not damage cables or place stress on insulation or terminations. Manufacturer bending radius limits must be followed, or minimum acceptable radii applied where manufacturer information is not available. Supports in contact with cables under pressure must not have sharp edges. Clause 3.9.7 Particular installation requirements. This clause introduces additional rules for specific wiring systems and situations. Clause 3.9.7.1 Consumer mains. This clause explains that consumer mains protected on the supply side by a short-circuit protective device must comply with the installation requirements relevant to the wiring system used. Clause 3.9.7.1.2 Unprotected. This clause explains requirements for consumer mains that are not protected on the supply side. These must be constructed to minimize the risk of short-circuit and installed in accordance with additional distributor requirements. Certain wiring systems are recognized as providing adequate short-circuit risk reduction. Clause 3.9.7.2 Insulated and sheathed cables. This clause explains how insulated and sheathed cables may be installed in concrete, plaster, or cement render, with different rules for armored and unarmored cables to ensure adequate protection. Clause 3.9.7.3, Mineral Insulated Metal Sheathed Cables. This clause explains that MIMS cables must be selected to suit corrosion risk, underground installation, vibration and temperature conditions. Movement due to vibration must be managed by suitable cable looping, and supports must withstand the highest operating temperatures of the cable. Clause 3.9.7.4, Flexible cords used as installation wiring. This clause explains when flexible cords may be used as installation wiring, the conditions they must meet, and when flexible cords are not regarded as installation wiring. Clause 3.9.7.5, Low voltage track systems. This clause explains that low voltage track systems must be open to view along their length, positioned to minimize contamination, and supported at suitable intervals so the system remains secure and free from sagging. Clause 3.9.7.6, Under-carpet wiring systems. This clause explains that under-carpet wiring systems must be installed only as complete systems using specified components and tools, must not be interconnected unless permitted, and must be positioned so they remain safe under normal use. Clause 3.9.8, Prevention of mutual detrimental effects between services. This clause introduces the requirement to avoid harmful interactions between electrical wiring and other services. Clause 3.9.8.1, General. This clause explains that wiring systems must be arranged to avoid detrimental effects between different electrical installations, different voltage levels, safety services and non-electrical services. Clause 3.9.8.2, Different electrical installations. This clause states that conductors from different electrical installations must not share the same enclosure unless specific conditions apply, and clarifies what is not considered an enclosure. Clause 3.9.8.3, Segregation of different voltage levels. This clause explains that high voltage, low voltage, and extra low voltage circuits must be segregated unless specific insulation or physical separation arrangements are used. Clause 3.9.8.4, Proximity to non-electrical services. This clause explains separation requirements between electrical wiring and services such as gas, water, and telecommunications, including minimum separation distances and applicable New Zealand requirements. Clause 3.9.9, Selection and installation to minimize the spread of fire. This clause introduces fire safety considerations for wiring systems. Clause 3.9.9.1, General. This clause explains that wiring systems must be selected and installed to minimize the spread of fire and must not reduce the fire performance of the building. Clause 3.9.9.2, Precautions. This clause explains that appropriate materials and installation methods must be used to reduce fire risk, and that fire-rated cables may be installed without additional precautions where suitable. Clause 3.9.9.3, Penetration of fire barriers. This clause explains that where wiring passes through fire-rated building elements, openings must be sealed, fire ratings reinstated, and sealing systems must resist fire, smoke, water, and combustion products. Clause 3.9.10, Limitation of circulating and eddy currents. This clause introduces requirements to limit heating caused by induced currents. Clause 3.9.10.1, General. This clause states that precautions must be taken to limit circulating and eddy currents. Clause 3.9.10.2, Cables for AC circuits, electromagnetic effects. This clause explains that single-core AC cables must be arranged so that all phase conductors and the neutral are contained together, especially in ferrous enclosures, to prevent excessive heating. Clause 3.9.10.3, Cables with non-ferrous metal sheathing. This clause explains bonding and arrangement requirements for single-core cables with non-ferrous metal sheaths, including trefoil and alternative formations. Clause 3.9.11, Minimization of electromagnetic interference. This clause explains that where sensitive equipment is present, electromagnetic interference may be reduced by suitable cable selection, shielding, or installation configurations that reduce magnetic field effects. Clause 3.10, Enclosure of cables. This clause explains when cables must be enclosed, what types of enclosures are acceptable, and how those enclosures must be installed so that cables are protected from damage and remain safe throughout their service life. Clause 3.10.1 General. This clause explains that some types of cables must be enclosed to provide mechanical protection, electrical safety, and durability, depending on how and where the cable is installed. Clause 3.10.1.1 Insulated, unsheathed cables. This clause explains that insulated, unsheathed cables must be enclosed in a wiring enclosure along their entire length. The purpose of this requirement is to protect the insulation from damage and to reduce the risk of electric shock or short circuit. The clause also explains that there are limited situations where an enclosure is not required, including where the cable is used as an aerial conductor in accordance with Clause 3.12, where the cable is installed within an enclosed wall cavity close to an accessory and terminates within 100 mm of the opening, where the cable is inside switchboards or metering enclosures and not exposed to touch during normal operation, where the cable is an earthing or equipotential bonding conductor installed in accordance with Section 5, and where the cable is part of an extra low voltage circuit installed in accordance with Clause 7.5. Clause 3.10.1.2 Insulated and sheathed cables. This clause explains that insulated and sheathed cables generally do not need to be installed in a wiring enclosure because the sheath provides protection. However, if the insulation or sheath does not meet combustion propagation requirements, the cable must be installed in fire-rated enclosures. It also explains that where the sheath is removed, any exposed insulated cores must then be enclosed in accordance with the rules for insulated, unsheathed cables. Clause 3.10.2 Wiring enclosures. This clause introduces the requirements for wiring enclosures used to protect cables that require enclosure. Clause 3.10.2.1 Types. This clause explains the acceptable types of wiring enclosures. These include conduits complying with AS NZS 2053 or AS NZS 61386, such as steel conduit, flexible metal conduit, rigid or flexible insulating conduit, and corrugated insulating conduit. It also includes cable trunking systems complying with AS NZS 4296, with or without compound filling, and other enclosures that provide mechanical protection at least equivalent to conduit or trunking. The clause also explains that covers of wiring enclosures containing unsheathed cables must be securely retained and, where readily accessible, must not be removable without tools. Clause 3.10.2.2 Change of wiring enclosures. This clause explains that any change from one type of wiring enclosure to another must be made either at a switchboard or by using a suitable device that fully protects the conductor insulation and maintains continuity of conductive enclosures. Clause 3.10.2.3 Entry of water. This clause explains that wiring enclosures must be installed in a way that prevents water from entering electrical equipment or enclosures. Where enclosures are exposed to the weather, suitable measures must be provided to prevent rain entry. The clause also explains that the relative height of enclosure ends must be considered to reduce the risk of water tracking into equipment. Clause 3.10.3 Installation of wiring enclosures. This clause explains that wiring enclosures must be installed using safe and sound practice and must provide adequate protection in accordance with the requirements of Clause 3.3 and the following clauses. Clause 3.10.3.1 General. This clause explains that wiring enclosures must be installed so they do not obstruct natural water drainage on roofing materials and do not promote the buildup of debris. This may be achieved by installing the enclosure across the roofing profile or by installing it within valleys or trays using suitable supports such as standoff brackets. Clause 3.10.3.2 Support. This clause explains that wiring enclosures must be supported by suitable means to prevent damage to the enclosure or to the cables they contain. Clause 3.10.3.3 Continuity. This clause explains that mechanical and electrical continuity of conductive wiring enclosures must be maintained. An exception is allowed where the enclosure is not required to be earthed, such as where it contains insulated and sheathed cables only. Clause 3.10.3.4 Bending. This clause explains that bends in wiring enclosures must be made so that cables and conductors are not damaged. In rigid conduit, bends must not significantly reduce the internal diameter. Where direction changes occur in trunking or ducts, the arrangement must still allow cables to be bent without damage, and the cable bending requirements of Clause 3.9.6 must be met. Clause 3.10.3.5, Passage of conductors. This clause explains that conductors and cables passing through enclosures or openings must be adequately protected. Openings must be of suitable size and fitted with securely fixed bushes, or otherwise be free of sharp edges that could damage insulation or sheathing. Clause 3.10.3.6, Terminations. This clause explains that wiring enclosures must terminate at electrical equipment in a way that fully protects the enclosed cables as they enter the equipment. Flexible conduit must be securely anchored at each end to fixed conduit, structures, or equipment. Clause 3.10.3.7, Installation in direct sunlight. This clause explains that rigid insulating conduit fittings, and cable trunking systems installed in direct sunlight must either be designed for that use or be painted with a light-colored water-based acrylic paint to reduce heat and ultraviolet damage. Clause 3.10.3.8, Provision for expansion. This clause explains that allowance must be made for thermal expansion in runs of rigid insulating conduit. It also explains that insulating conduit expands with temperature, and that expansion must be accommodated to prevent stress or damage. Clause 3.10.3.9, Cable trunking. This clause explains that cable trunking systems must be installed so that covers can be opened where practicable. Covers remain continuous through walls and floors, trunking is accessible along its entire length, and cables do not rely on removable covers for support. It also explains that non-hygroscopic trunking must be used for insulated, unsheathed conductors, and that live parts of accessories mounted on trunking must be arranged so that basic protection is provided. Clause 3.11, Underground wiring systems. This clause explains the requirements for wiring systems that are installed below ground. Underground wiring must be suitable for the environment it is placed in, protected against damage that could reasonably occur during excavation or ground movement, and installed in a way that reduces the risk of accidental contact or damage in the future. Clause 3.11.1, Suitability and protection. This clause explains that cables installed underground must be appropriate for the soil and environmental conditions they are exposed to. They must be protected against damage that could be caused by manual digging or mechanical excavation, and suitable warning, marking, or protective measures must be provided so that people carrying out excavation work are alerted to the presence of the underground wiring system. Clause 3.11.2, Classification of wiring systems. This clause explains that underground wiring systems are classified into 3 categories, and that the category depends on the type of cable used and the form of enclosure or protection provided. Category A systems are those that are inherently suitable for underground installation and do not require additional mechanical protection. Category B systems are suitable for underground installation only when extra mechanical protection is provided. Category C systems are those where cables are installed in a channel cut into rock and then covered with concrete. Clause 3.11.3, Category C underground wiring system. This clause explains that a Category C underground wiring system consists of cables installed in a channel that is cut into rock and then covered with concrete. It also explains that where a Category A system is installed in a channel cut into rock and meets the requirements for Category C, it may be treated as a Category C system. Clause 3.11.4, Installation requirements. This clause explains that underground wiring systems must be installed in accordance with the detailed installation requirements that follow, and that the dimensions and arrangements shown apply in any direction where cover is relied upon to reduce the risk of damage during excavation. Clause 3.11.4.1, General. This clause states that underground wiring systems must be installed in accordance with the requirements that follow in this section, and that these requirements are intended to reduce the risk of damage and improve safety over the life of the installation. Clause 3.11.4.2, Unenclosed. This clause explains that where Category A or Category B wiring systems use cables that are not installed in a wiring enclosure, the cables must be laid on a bed of sand or friable soil that is free from sharp stones. The bedding must be at least 50 mm thick, and the cables must then be covered with at least 50 mm of the same material before backfilling. Clause 3.11.4.3, Category B wiring system mechanical protection. This clause explains that Category B systems must be provided with additional mechanical protection. The protection must be placed no more than 75 mm above the cable, must be at least 150 mm wide, and must overlap the cable by at least 40 mm on each side. The protection may consist of materials such as concrete slabs, fibrous cement slabs, bricks designed for cable protection, polymeric cable cover strips, or other materials that provide an equivalent level of protection. Clause 3.11.4.4, Minimum depth of cover. This clause explains that underground wiring systems must be installed with not less than the minimum depth of cover specified for the category of system in the location. The depth is measured vertically from the surface of the ground or from the surface of any concrete placed above the wiring system, and the required depth varies depending on whether the wiring is within or outside a building and whether additional protection is provided. Clause 3.11.4.5, Identification of underground wiring. This clause explains that underground wiring systems must be identified by orange marker tape installed above the wiring system. The marker tape must be positioned at approximately half the depth between the surface and the cable, or above any additional mechanical protection. Where cables are installed in rock channels, the marker tape must be placed directly above the wiring system before the concrete is poured. Marker tape may be omitted for board installations if the cable route is permanently recorded and, where an enclosure remains after boring, that enclosure is colored orange. Clause 3.11.4.6, Marking and recording of underground cable location. This clause explains that permanent signs must be provided to show where an underground cable enters or leaves a building, unless the entry point is obvious. It also explains that the route of underground cables must be recorded on a plan so the location can be identified in the future. This plan must be kept at the switchboard where the circuit originates. Marking is not required for underground wiring installed entirely within the confines of a building. Clause 3.11.5, Spacing from other underground services. This clause explains that underground wiring systems must be separated from other underground services by at least 100 mm. They must also maintain separation from gas, water, and telecommunications services in accordance with the required spacing rules. Exceptions are allowed where multiple services are installed in a common trench, provided each service is in a separate enclosure and clearly identified. Clause 3.12, Aerial wiring systems. This clause explains that aerial wiring systems are used where cables are supported above ground, and that their use may be restricted by local authorities in some areas, especially where there is a higher risk such as bushfire zones. Clause 3.12.1, Types of conductor. This clause states that conductors used as aerial conductors must be suitable for aerial use, and this includes hard-drawn bare conductors, polymeric insulated cables, neutral screened cables, and insulated conductors that are twisted, bundled, or arranged together for aerial installation. Clause 3.12.2, Arrangements. This clause explains that aerial conductors must be arranged so they are safely installed and supported. It also introduces that further requirements apply to insulation, size, spacing, supports, and hardware, which are covered in the following clauses. Clause 3.12.3, Clearances. This clause explains that aerial conductors for low-voltage systems must be installed so that clearances from the ground, buildings, and other structures are not less than the minimum values required. These clearances must be maintained in all directions, taking into account sag caused by heat and movement caused by wind. When conductors are installed, extra allowance must be made so that the required clearances are still met at the maximum operating temperature. Where aerial conductors terminate near buildings or structures, suitable clearances must be provided to prevent contact. Connections between aerial conductors and circuit wiring are not treated as aerial conductors, but they must still be kept out of arm's reach from the ground or from accessible elevated areas. Clause 3.12.4 Distance between supports. This clause explains that the span length between supports for aerial conductors must not exceed the maximum values specified for the conductor type and size. Longer spans may be used only where the design follows sound engineering practice. This clause recognizes that correct span length helps control sag, tension, and mechanical stress on the conductors. Clause 3.12.5 Aerial conductor supports. This clause states that supports used for aerial conductors must be insulators or purpose-designed fittings that are suitable for the type of conductor being supported. It also explains that pin-type insulators must not be used where the strain on the conductor could cause it to lift or separate from the insulator, as this would create a safety risk. Clause 3.12.6 Poles and posts, including supports, struts and extensions to structures. This clause explains that poles and posts used to support aerial conductors must be made from materials suitable for the conditions of use. Their size and depth in the ground must be adequate to provide stability. Where ground conditions are poor, the depth must be increased or other stabilizing methods used. This ensures the support remains secure under load and environmental conditions. Clause 3.12.7 Joints and connections. This clause explains that all joints and connections in aerial conductors must be made in accordance with the general requirements for joints and connections. The intention is to ensure electrical reliability, mechanical strength, and long-term safety. Clause 3.13 Cables supported by a catenary. This clause introduces wiring systems where cables are supported by a separate catenary wire, rather than being self-supporting. It explains that this method reduces mechanical stress on the cable. Clause 3.13.1 Types of cables. This clause explains that cables supported by a catenary must be stranded cables that provide double insulation, or the equivalent level of insulation. Where installed outdoors, both the cable and the catenary support must be suitable for exposure to direct sunlight. Cables supported by a catenary are considered to be adequately supported because the catenary carries the mechanical load. Clause 3.13.2 Catenary supports. This clause explains that a catenary must provide even support along the cable run, be made from materials that resist corrosion and deterioration, be securely fixed at each end, be capable of withstanding expected mechanical stresses such as wind or ice, and be installed at a height that prevents danger to people, livestock, or damage to the cable. Where the catenary forms part of the cable, it must be installed in accordance with the manufacturer's instructions. Clause 3.13.3 Clearances. This clause explains that cables supported by a catenary must maintain minimum clearances. Outdoors, the clearances must meet the same requirements as those for neutral screened aerial cables. Indoors, the cable must be kept at least 100 mm away from moving parts or equipment that operates at elevated temperatures. Clause 3.14 Safety services. This clause states that wiring systems used for safety services must meet all the requirements of this section, and in addition must be installed in accordance with the specific requirements for safety services. This ensures that circuits supplying safety systems remain reliable and protected under fault or emergency conditions. Clause 3.15 Busways, including rising main systems. This clause explains that busbar trunking systems, also called busways, must comply with ASNZS 61439.6 and must be installed exactly as the manufacturer instructs. When a busway is used as part of a wiring system, its installation must also meet the relevant installation requirements already set out in Clause 3.9. This means the same general rules for fixing, support, mechanical protection, and installation practice apply to busways as they do to other wiring systems, including the requirements that deal with penetration of fire-rated building elements. Clause 3.16 Earth Sheath Return (ESR) System. This clause explains that an earth sheath return system is a system where the copper sheath of a MIMS cable acts as a single conductor that performs two functions at the same time, being both the protective earthing conductor and the neutral conductor. Only a copper sheath is permitted to be used in this combined role, and it is referred to as a PEN conductor. These cables must be installed in accordance with Clause 3.9.7.3, along with the additional conditions set out in this clause. The copper sheath must have enough cross-sectional area and conductivity so it can safely carry both neutral current and earth fault current. The ESR system is only permitted in installations that use the MEN earthing system, and it must start at the point where the neutral and earthing conductors are connected together to form the MEN connection. If at any point the combined protective earthing and neutral conductor is changed so that the neutral and the protective earth become separate conductors supplying electrical equipment, they must not be recombined later to form another PEN conductor. The ESR system must not be installed in hazardous areas. Conductors used in an ESR system must not be smaller than 2.5 square millimeters. At every joint in the cable sheath, and at all terminations, the continuity of the combined PEN conductor must be maintained, and this must be ensured by using a bonding conductor in addition to whatever sealing and clamping method is used on the external conductor. The resistance of this bonding conductor at joints must not be greater than the resistance of the cable sheath itself. At terminations, two separate conductors must be used, one for protective earthing and one for the neutral. The minimum size of the protective earthing conductor must comply with Clause 5.3.3 in Table 5.1, and the neutral conductor must be not less than 6 square millimeters, or comply with Clause 3.5.2. Where several cables are associated together, such as single-core cables used in a multi-phase circuit, the cables must be arranged in accordance with Clause 3.9.10.3. The circuit must be clearly identified at the switchboard where it originates so it is obvious that the circuit uses an ESR system. No switch is allowed to operate in the combined protective earthing and neutral conductor of an ESR system. Only electrical fittings that are specifically identified as suitable for use with an ESR system are permitted to be used. Circuits that use ESR systems cannot be protected by RCDs. That brings us to the end of Section 3. We've now covered the key requirements for wiring systems, including how they are installed, supported, protected, enclosed, run underground, installed overhead, and used for special systems such as safety services and earth sheath return systems. These rules are essential for ensuring wiring systems are safe, durable, and fit for purpose over their entire life. As we move on, the next section will build on this foundation and look at further requirements that apply to specific situations within electrical installations. Hi everyone, my name is Aria, and I work alongside Whit Roy as an electrical tutor. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 3000, 2018. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for EWRB exam. What this audiobook does is take the key ideas from the standard and explain them in simple, spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real installations. So think of this as a learning companion, not a replacement for the actual standard. All right, let's get started. Today we move into Section 4 of ASNZS 3000. This section focuses on the selection and installation of electrical equipment. It explains how electrical equipment must be chosen, installed, protected, connected, and controlled so it operates safely under normal use and under fault conditions. Throughout this section, we look at how equipment is protected against heat, mechanical damage, fire, and electric shock, and how correct installation helps prevent harm to people, property, and the electrical installation itself. Everything in this section is about making sure electrical equipment is fit for purpose, suitable for its environment, and installed in a way that keeps everyone safe. Clause 4.1, General. This clause sets the scene for Section 4 and explains that this part of ASNZS 3000 is about the minimum requirements for selecting and installing electrical equipment so the installation meets the safety goals of Part 1 of the standard. It covers equipment such as appliances and accessories and focuses on making sure everything chosen and installed is suitable for its intended use. Clause 4.1.1 Application. This clause explains that the section applies to the selection and installation of electrical equipment, including appliances and accessories, and that the goal is to meet the overall safety requirements of the standard, not just to make equipment work but to make sure it works safely for people and property. Clause 4.1.2 Selection and Installation. This clause explains that electrical equipment must be chosen and installed so it works properly under the conditions it is expected to face, does not cause harmful effects to the electrical installation, operates safely when correctly assembled and connected to the supply, and does not create danger from electric shock, fire, high temperature, or physical injury during reasonably expected conditions such as overloads, abnormal operation, or faults. It also explains that equipment must be installed to meet the requirements of this section as well as the manufacturer's instructions, and that some equipment must comply with nominated Australian or New Zealand standards or other relevant standards. The clause then explains that the section covers matters such as external influences and environmental conditions, harmful effects on the installation and supply, protection against thermal effects, methods of connection, installation of socket outlets and lighting and heating equipment, electricity converters including UPS systems, control and protection of motors, transformers, capacitors, equipment containing liquid dielectrics, and smoke alarms and fire detectors. The notes explain that some equipment may be remotely switched, meaning care is needed when working on it because it could become live without warning, that clearances are required near cooking surfaces, that special rules apply in rooms with baths or showers, and that in New Zealand attention is drawn to NZEC P55 for wiring and fittings near conductive thermal insulation. Clause 4.1.3 External Influences. This clause explains that all electrical equipment must have characteristics suited to the conditions it is likely to be exposed to so it will function properly at its installed location. It explains that this suitability may come from the equipment's own design and construction or from additional protective measures provided as part of the installation, as long as those measures do not interfere with correct operation. The clause then explains that damage can result from many external influences, including mechanical damage, whether such as rain, snow, ice and sunlight, water from splashing or high humidity, plant growth, animals, excessive dampness, corrosive fumes or liquids, galvanic action, dust or foreign objects, steam, oil, temperature extremes, solar radiation, explosive atmospheres, vibration, and seismic activity such as earthquakes. The notes explain that IP classifications describe protection against water and solid objects, that purpose-made drainage features can be used without reducing protection, that drilling holes can destroy the IP rating, that some accessories without a marked degree of protection may still be considered protected when installed in sheltered locations, that accessories installed outside those sheltered areas must meet a minimum IP33, and that some specific enclosures and metering equipment have stated exceptions. Clause 4.1.4 Adverse Effects and Interference. This clause explains that electrical equipment must be selected so that during normal operation, including switching, it does not cause harmful effects to other equipment. It explains that issues to consider include power factor, excessive voltage fluctuation, severe distortion of current waveforms, and electromagnetic emission. Clause 4.1.5 Air Extraction Systems. This clause explains that air extraction systems can affect the safe operation of combustion appliances, including appliances in other rooms, and may create a risk of carbon monoxide poisoning. It advises that customers should have fluid combustion appliances tested by a competent person to confirm correct and safe operation. Clause 4.2 Protection against thermal effects. This clause explains that Section 4.2 is about managing heat produced by electrical equipment so that heat does not damage equipment, wiring, buildings, or create safety risks such as fire or burns during normal operation. Clause 4.2.1 General. This clause explains that electrical equipment must be selected and installed so that, when it is correctly installed and operating as intended, its temperature does not negatively affect the equipment itself, the electrical installation, or anything nearby, whether electrical or not. It explains that ventilation must be provided when needed so operating temperatures stay within the equipment's rated limits when heat is produced in normal use, and it reminds us that temperature can change how equipment performs or behaves, so this must be considered during selection and installation. Clause 4.2.2 Prevention of fire hazard. This clause introduces the need to prevent fire risks caused by electrical equipment. Clause 4.2.2.1 Installation of electrical equipment. This clause explains that electrical equipment must not be installed in a position where it could create a fire hazard. Clause 4.2.2.2 Storage of flammable materials. This clause explains that where an area may be used to store flammable materials, steps must be taken to prevent ignition from sparks or high temperatures, and it points out that special requirements apply in hazardous areas. Clause 4.2.2.3 Protection from high temperatures. This clause explains how fixed electrical equipment that can reach high temperatures must be managed so it does not create a fire risk. It explains that where surface temperatures could ignite nearby materials, the equipment must be mounted on or within materials that can tolerate the heat and do not easily conduct heat, or be screened from combustible building elements using suitable heat-resistant materials, or be mounted far enough away so heat does not cause damage, with supports that limit heat transfer and allow safe cooling. It also explains that where equipment produces radiant heat, it must be placed far enough away so nearby objects or building elements are not exposed to dangerous temperatures during normal operation. The notes explain that some building materials can slowly break down when exposed to heat over long periods, that many common electrical items are sources of high temperature, and that restricting heat dissipation can cause equipment itself to overheat. Clause 4.2.2.4 Emission of arcs or sparks. This clause explains that where permanently connected electrical equipment could emit arcs or sparks during normal service, it must be fully enclosed in arc-resistant material, or screened from nearby building elements using arc-resistant material, or mounted far enough away to allow arcs or sparks to safely extinguish without causing damage. Clause 4.2.2.5 Electrical equipment enclosures. This clause explains that enclosures must be able to withstand the highest temperatures likely to be produced by the equipment, and that flammable or easily combustible materials must not be used to build those enclosures. Clause 4.2.2.6 Prevention of spread of fire. This clause explains that switches, socket outlets, and similar accessories must be arranged so there is sufficient separation from openings in fire-rated walls, ceilings, or floors, and that openings made for electrical equipment must not weaken fire-rated barriers beyond the permitted extent. Clause 4.2.2.7 Thermal insulation, New Zealand only. This clause explains that in New Zealand domestic installations, appliances and accessories must not be installed on thermal insulation in ceilings, walls, or underfloors, and this applies even if insulation is not present at the time but may be added later. Clause 4.2.3 Protection against burns. This clause explains that accessible parts of electrical equipment within arm's reach must not reach temperatures that could cause burns under normal conditions, and that any accessible part of the installation that could exceed safe temperature limits, even briefly, must be guarded to prevent accidental contact. It also explains that some equipment is exempt where temperature limits are controlled by an appropriate standard, and that items such as lamps are excluded from this requirement. Clause 4.3 Connection of electrical equipment. This clause introduces the rules for how electrical equipment is to be connected to installation wiring. Clause 4.3.1 General. This clause explains that electrical equipment may be connected to installation wiring using the permitted connection methods, and that the point of connection must be as close as practical to the equipment and protected from mechanical damage or interference. It explains that wiring forming part of the equipment itself is considered equipment wiring and must comply with the relevant product standard, or ASNZS 3100 where no product standard exists, and that certain accessories must not be used where the connection point is not readily accessible. Clause 4.3.2 Direct Connection. This clause introduces direct connection methods. Clause 4.3.2.1 General. This clause explains that installation wiring may be directly connected to terminals provided on the equipment for that purpose. Clause 4.3.2.2 Installation Coupler. This clause explains that an installation coupler meeting ASNZS 61535 is suitable for connecting cables, including flexible and rigid types. It explains that installation couplers are intended for permanent connections between wiring sections and are treated like junction boxes, and that they require deliberate action to disconnect and are not intended to be used under load or as socket outlets. Clause 4.3.3 Installation wiring connected by an installation coupler or couplers. This clause introduces requirements for wiring connected using installation couplers. Clause 4.3.3.1 General. This clause explains that cords or cables connected by an installation coupler must be heavy-duty sheathed types suitable for the protective device, adequately protected and installed to reduce mechanical damage, supported and fixed correctly, and kept as short as practicable, with a specific allowance for reduced cable size where wiring terminates within a single item of equipment such as a luminaire or single socket outlet. Clause 4.3.3.2 Socket outlets. This clause explains that socket outlets supplied by installation couplers must be suitable for their intended use, securely fixed, installed to meet location requirements, designed to prevent dust or water buildup when mounted on horizontal surfaces, and securely supported where not readily accessible so that no strain is placed on wiring during plug insertion or removal. Clause 4.3.4 Socket outlets in installation wiring. This clause explains that installation wiring must terminate at a suitable socket outlet, with the connection to the equipment continued using a plug and flexible cord or cable. Clause 4.3.5 Other connecting devices. This clause explains that where wiring terminates at a junction box, sealing rows, or similar connecting device for specific equipment, the wiring from that device to the equipment is considered equipment wiring. Clause 4.3.6 Equipment wiring. This clause explains that equipment wiring must be as short as practicable, have a current carrying capacity suitable for the connected load, be protected against short circuit, include a protective earthing conductor where earthing is required, and be selected and installed so that wiring and connections within luminaires are not damaged by heat or ultraviolet radiation. It also explains that smaller conductors may be used where a proper assessment shows protection requirements are met, and clarifies when wiring associated with pendant socket outlets is considered installation wiring rather than equipment wiring. Clause 4.4 Socket outlets. This clause introduces the requirements for socket outlets, covering their types, where they may be installed, how they are protected, how they are switched, and how they are connected safely within an electrical installation. Clause 4.4.1 Types. This clause introduces the different types of socket outlets that may be used. Clause 4.4.1.1 General. This clause explains that socket outlets must be suitable for their intended use in the location where they are installed, and that they must comply with the relevant recognized standards that apply to the particular socket outlet design. Clause 4.4.1.1.1 Socket outlets application. This clause explains that socket outlets must match the purpose and installation location and must comply with recognized standards such as ASNZS 3112, ASNZS 3123, IEC 60309, or ASNZS 3131, or equivalent standards. Clause 4.4.1.1.2 Socket outlets, alternative pin configurations. This clause explains that socket outlets using alternative pin configurations, such as overseas styles, may only be used under specific conditions. It explains that they must have a single set of pin apertures with an earthing contact and must meet the national standard of the country they represent, and that socket outlets accepting multiple pin configurations are not permitted, except for shaver socket outlets complying with ASNZS 3194. It explains that their installation must meet the general socket outlet location rules, that they must be rated for the installation voltage unless supplied at a lower voltage, and that where they normally supply a lower voltage than the installation, they must actually be supplied at that lower voltage. It also explains that these socket outlets must have been tested to meet equivalent safety requirements to those applied to standard socket outlets. In New Zealand only, this clause explains that these socket outlets are limited to specific locations such as facilities directly associated with international airports or residential areas of non-domestic installations that provide accommodation for international visitors or guests. It also explains that where a nominal 230-volt supply is required, additional protection by an ACD with a maximum rated residual current of 10 mA and by an AFDD is required, and that where a 110-volt supply is required, the socket outlet must be supplied at reduced low voltage. Clause 4.4.1.1.3, Low Voltage Fixed Socket Outlet. This clause explains that a low voltage fixed switch or socket outlet, or its faceplate, must not include connection devices for telecommunications, data, television, radio, or similar wiring systems, while allowing USB charging socket outlets on the faceplate. Clause 4.4.1.2 Different Systems. This clause explains that where extra low voltage and higher voltage systems exist in the same premises, any socket outlet supplied at extra low voltage must be clearly marked with their voltage and be designed so that an extra low voltage plug cannot be inserted into a socket outlet connected to a higher voltage system. It also explains that socket outlets for SELV and PELV systems must not have an earthing contact and must comply with the relevant clause referenced in this section. Clause 4.4.1.3 Socket outlets for electric vehicle charging. This clause explains that information for the installation and location of socket outlets for electric vehicle charging is provided elsewhere in the standard, and that in New Zealand the detailed requirements are specified in the relevant clause covering electric vehicle charging installations. Clause 4.4.2 Location. This clause introduces requirements for where socket outlets may be installed. Clause 4.4.2.1 Accessibility. This clause explains that socket outlets must be installed so that plugs can be easily inserted and withdrawn without damaging the plug or the flexible cord or cable. It explains that socket outlets must not be installed where a permanent fixture would restrict plug removal, and it also notes that where gas appliances are installed, the means of electrical isolation must remain accessible. Clause 4.4.2.2 Protection of socket outlets. This clause explains that socket outlets must be installed so they are not exposed to undue mechanical stress or damage during normal use. It explains that where socket outlets are installed in floors or horizontal surfaces, they must be arranged to prevent the build-up of dust or water. It explains that where socket outlets are installed close to a floor, they must be positioned so plugs are withdrawn horizontally, unless certain protective design conditions are met. It also explains that socket outlets must be installed so plugs do not loosen or malfunction due to gravity, vibration, or cable weight, and that where socket outlets are not readily accessible and are used for fixed appliances or luminaires, they must be securely fixed to prevent strain on the wiring during plug insertion or removal, with stated exceptions where mechanical stress is already adequately controlled by the wiring system and its support. It further explains that socket outlet use is restricted in damp locations, hazardous areas, and other special situations, and that where socket outlets are installed in fire-rated or acoustic building surfaces, their protective properties must be maintained. Clause 4.4.3 Earthing contacts. This clause explains that every socket outlet must have an earthing contact, except where socket outlets are used for SELV or PELV systems, in which case no earthing contact is permitted. Clause 4.4.4 Switching device. This clause introduces requirements for controlling socket outlets. Clause 4.4.4.1 General. This clause explains that each socket outlet must normally be controlled by its own separate switch that meets the relevant switching standards and operates in all active conductors. It explains that switches controlling socket outlets must comply with the location and marking requirements that follow, and it sets out exceptions where a single switch may control two adjacent socket outlets, where low current socket outlets for fixed appliances or luminaires do not need a switch, or where switching occurs by plug insertion and withdrawal. Clause 4.4.4.2 Rating. This clause explains that a switch controlling a socket outlet must have a current rating that is not less than the rating of the socket outlet it controls, and where one switch controls two socket outlets, the switch rating must be sufficient for the combined or protected circuit current, whichever is lower. Clause 4.4.4.3 Location and Marking. This clause explains that the switch controlling a socket outlet must be located as close as practicable to the socket outlet and be clearly identified to show what it controls. It explains that where the switch is remote from the socket outlet, it must be installed in a convenient and accessible position, and both the switch and the socket outlet must be clearly and permanently labeled to show their relationship, with stated exceptions where the socket outlet is high above ground, dedicated to a specific appliance, and not intended for general use. Clause 4.4.4.4 Pendant Type Socket Outlet. This clause explains that where a switch is built into a pendant type socket outlet attached to a flexible cord, the switch must interrupt all live conductors. It also explains that for multi-phase pendant socket outlets, switching only the active conductors is permitted provided the outlet is independently supported. Additional mechanical protection is provided where needed, and the supply cord is suitable for expected movement and vibration. Clause 4.4.5 Polarization and Phase Sequence. This clause explains that where socket outlets of the same type are installed within an installation, their connection order must be consistent. It also explains that for 3-pin flat-pin socket outlets, the arrangement of earth, active, and neutral must follow the specified clockwise order when viewed from the front of the socket outlet, ensuring correct polarity throughout the installation. Clause 4.5 Lighting Equipment and Accessories. This clause introduces the requirements for lighting equipment and accessories, focusing on safe location, protection against heat, fire risk, burns, and correct installation to suit the environment and building construction. Clause 4.5.1 Lamp holders, including lamp holders incorporated in a luminaire T. His clause introduces requirements that apply specifically to lamp holders, whether they are separate or built into a luminaire. Clause 4.5.1.1 Location. This clause explains that all lamp holders must be positioned so they are adequately protected from damage that could reasonably be expected during normal use. It explains that for low-voltage lamp holders, their location must reduce the risk of accidental contact with live parts when a lamp is removed and reduce the risk of mechanical damage to the lamp or lamp holder. It explains that this protection can be achieved either by installing the lamp holder at least 1.8 meters above the ground, floor, or platform, or by fitting a suitable guard around the lamp and lamp holder. It also explains that pendant lamp holders must not be installed where they are exposed to significant air movement, such as outdoors or near fans, where movement could affect safe operation. Clause 4.5.1.2 Edison screw lamp holders. This clause explains that every low-voltage Edison screw lamp holder must be connected so that, where a neutral conductor is required, it is connected to the outer contact. It explains that this requirement does not apply where the lamp holder is part of an appliance installed in a permitted manner or where the luminaire and lamp holder include a shroud or skirt that prevents contact with the outer contact. Clause 4.5.1.3 Festoon lighting. This clause explains that festoon lighting must be located and supported so that lamps are kept well clear of flammable materials or structural metalwork, and are not within arm's reach of the ground or other places where a person is likely to stand. It explains that festoon lighting may be within arm's reach only when installed immediately below a ceiling. Clause 4.5.2 Lamps and luminaires. This clause introduces requirements for the installation of lamps, luminaires, and associated gear. Clause 4.5.2.1 General. This clause explains that lamps, luminaires, and their associated auxiliary equipment must be installed so they do not cause excessive temperature rise, ignition, or deterioration of materials they are mounted on or materials they illuminate. It explains that luminaires must be suitable for the highest temperatures they are likely to experience from external influences and must be installed in accordance with the manufacturer's instructions, taking into account the highest rated lamp that may be used. The notes explain that some building materials can degrade or even self-ignite after long-term exposure to heat, and that luminaires can generate high temperatures, meaning cables with suitable temperature ratings must be selected. Clause 4.5.2.2 Lamps near flammable materials. This clause explains that where lamps are installed near flammable materials, they must either be suitably shielded so the material cannot be touched, or separated by enough distance so the material does not reach excessive temperature. It explains that where no product information is available, minimum separation distances must be applied, and that flammable shades must not be installed where they could come into contact with any lamp. Clause 4.5.2.3 Recessed luminaires. This clause introduces requirements specific to recessed luminaires. Clause 4.5.2.3.1 General requirements. This clause explains that recessed luminaires and their auxiliary equipment must be installed in a way that prevents excessive temperature rise and reduces the risk of fire from ignition of combustible materials. It explains that this can be achieved by using luminaires certified as suitable for contact with combustible materials or insulation, by installing luminaires with tested and classified barriers, or by providing adequate separation from insulation and combustible materials using clearances or fire-resistant barriers. Clause 4.5.2.3.2 Warning sign. This clause explains that where recessed luminaires are installed in an accessible roof space, a permanent and legible warning sign must be installed near the access point so it is clearly visible to anyone entering the space, and that the sign must contain specific wording and lettering of a minimum size. It explains that this warning sign is not required where all recessed luminaires in that roof space are classified as IC or IC4. Clause 4.5.2.3.3 Installation. This clause explains that recessed luminaires must be installed using luminaires that are correctly designed, certified, and marked, and that manufacturer's instructions must be followed for installation conditions. It explains that in New Zealand, unmarked recessed luminaires must be treated as do not cover types and must be installed using barriers or clearances to prevent contact with materials that could restrict airflow or be damaged by heat. It explains that where insulation is already installed and recessed luminaires are added or altered, care must be taken so safety is not compromised. It explains that bulk thermal insulation can reduce cooling air circulation and that unless the manufacturer permits otherwise or a suitable barrier is provided, space above the luminaire must remain clear. It explains that where insulation is loose, barriers or guards must be used to maintain clearances, that auxiliary equipment operating at high temperature must be installed above insulation unless instructions allow otherwise, that supplied barriers must be installed as part of the luminaire, that higher wattage lamps require stricter installation methods, and that combustible materials must be kept away from hot surfaces to reduce ignition risk over time. Clause 4.5.2.3.4 Classifications of recessed luminaires. This clause explains that recessed luminaires are classified according to recognized classifications that define whether they can be abutted against or covered by normally flammable materials or insulation. It explains the meaning of different classifications and how they relate to excess of insulation or debris to heated parts of the luminaire, and it explains that certain classifications are not permitted in residential installations in New Zealand. Clause 4.5.2.3.5 Requirements for specific classifications. This clause explains that in New Zealand, recessed luminaires permitted in residential installations are limited to specific classifications, and that non-residential installations allow a broader range of classifications. It also explains that certain older classification markings may be treated as equivalent to newer classifications where labeled accordingly. Clause 4.5.2.4 Suspended ceilings. This clause explains that luminaires supported by ceiling panels must not impose loads greater than the panel can safely carry and must not operate at temperatures that would deform, discolor, or otherwise damage the ceiling panel, and it notes that some ceiling systems require additional support or infill panels in accordance with manufacturer information. Clause 4.6 Smoke Alarms. This clause explains that national building codes and legislation set rules for how smoke alarms are installed, including where they are located, how many are required, and whether they must be interconnected for alarm purposes. It explains that where mains-powered smoke alarms are installed, they may be connected either to the lighting final subcircuit or to their own individual final subcircuit. The notes explain that connection to the lighting final subcircuit gives a clear indication that the mains supply is available, because a loss of supply would usually be noticed by the lights not operating, and it also explains that smoke alarms are not classed as safety services for the purposes of this standard. Clause 4.7 Cooking Appliances. This clause introduces requirements for electrical safety related to cooking appliances. Clause 4.7.1 Switching Device. This clause explains that a fixed or stationary cooking appliance with an open cooking surface that uses electric heating must be provided with a switch that operates in all active conductors, and that this switch must be mounted near the appliance in a visible and readily accessible position. It explains that this requirement does not apply to enclosed cooking appliances such as built-in ovens or microwave ovens. In New Zealand only, where an appliance has an open cooking surface that uses both gas and electricity, the switching device must operate in all active conductors. It explains that a single switch may control associated cooking appliances located in the same room. It also explains that the switch must not be mounted on the cooking appliance itself, should normally be within 2 meters of the appliance, must not be positioned so the user has to reach across the open cooking surface, and must not be installed in prohibited locations. It explains that switches must be clearly marked to identify the appliance they control, and that where cooking appliances are installed in public or open areas, the switch may be protected by a lockable cover to prevent vandalism while still allowing operation for maintenance. Clause 4.7.2 Connection, New Zealand only. This clause explains that in New Zealand, a freestanding cooking appliance must be connected to the installation wiring using either a socket outlet or an installation coupler, and it explains that this requirement does not apply to built-in hobs in ovens. Clause 4.7.3 Clearance from open cooking surfaces. This clause explains that socket outlets and switches must not be installed in prohibited locations near open gas or electric cooking surfaces. It explains that this includes areas within 150 millimeters of the edge of the cooking surface, as well as areas directly above the surface up to a range hood, cupboard, ceiling, or 2.5 meters above the floor, whichever is lower. It explains that this requirement does not apply where an appliance complies as a complete unit with an appropriate standard. Clause 4.8 Appliances producing hot water or steam. This clause introduces requirements for appliances that produce hot water or steam. Clause 4.8.1 General. This clause explains that all appliances producing hot water or steam must be protected against overheating in all service conditions, either by design or by installation. It explains that protection must be provided by an appropriate non-self-resetting device that operates independently of the thermostat. Clause 4.8.2 Water heaters. This clause introduces specific requirements for water heaters. Clause 4.8.2.1 Access to easing equipment of pressure relief and terminals of protective devices. This clause explains that every unvented water heater must be installed so that pressure relief easing equipment and the terminals of protective devices are readily accessible for operation, inspection, and adjustment. It explains that an unvented water heater operates at the pressure of the water system, with flow controlled by valves in the outlet system. Clause 4.8.2.2 Protective devices fitted to unvented water heaters. This clause explains that over-temperature cutouts and similar protective devices fitted to unvented water heaters must operate directly in the circuit wiring to the heater elements and must not be arranged to operate through relays or contactors. Clause 4.8.2.3 Isolating switch. This clause explains that every directly connected water heater must be provided with an independent, lockable isolating switch. It explains that this isolating switch must be additional to any automatic switch built into the heater and must be installed adjacent to, but not on, the water heater. It also explains that where a water heater is supplied by more than one final subcircuit, all of those subcircuits must be capable of being isolated by a single isolating switch. Clause 4.9, Room Heaters. This clause introduces requirements for permanently connected room heaters. Clause 4.9.1, General. This clause explains that where one or more permanently connected room heaters are installed in a room, each room heater, or each group of room heaters, must be provided with an individual isolating switch and an individual functional switch. It explains that where multiple room heaters in one room are supplied by the same final subcircuit, a single isolating switch may be used for that room. Clause 4.9.2, Isolating Switches. This clause explains that isolating switches for room heaters must be installed either immediately adjacent to or within the room where the heater is located, or on the switchboard where the room heater final subcircuit originates. It also explains that isolating switches may be incorporated into temperature control devices, provided they have a definite off position. Clause 4.9.3, Functional Switches. This clause explains that functional switches for room heaters must be installed in a readily accessible position in the same room as the heater, or immediately adjacent to the entrance to that room. It explains that a functional switch may be a switch built into the room heater with an off position, or an isolating switch installed in accordance with the requirements for isolating switches. Clause 4.10, Electric heating cables for floors and ceilings and trace heating applications. This clause introduces requirements for electric heating cable systems used in floors, ceilings, and trace heating, with the aim of ensuring safe installation, correct operation, and protection against overheating, fire, and damage. Clause 4.10.1, General. This clause explains that cables used for electric heating in floors, ceilings, and trace heating must be specifically designed for heating purposes and must not be ordinary wiring. It explains that all heating equipment must be installed strictly in accordance with the manufacturer's instructions so the system operates safely and as intended. Clause 4.10.2, Heating cables. This clause explains that heating cables must be installed so they do not come into contact with flammable materials. Where the system is designed to be embedded, the cables must be fully and properly embedded in the material they are intended to heat and must not be damaged by movement, flexing, or shifting of that material over time. It also explains that where heating cables are designed as trace heating, they must be installed so heat is effectively transferred to the surface or material they are attached to. In New Zealand only, this clause explains that in floor and ceiling heating cables must be installed in accordance with NZS 6110. Clause 4.10.3, Isolating Switches. This clause explains that heating systems made up of cables or groups of cables must be provided with isolating switch or switches that meet the general isolation requirements of the standard. It explains that isolating switches may be built into temperature control devices, provided there is a definite off position. It explains that isolating switches must be installed either immediately next to an entrance to, or within, the room or area containing the heating system, or on the switchboard where the heating final subcircuit originates. It also explains that where heating cables are used for trace heating, the isolating switch does not have to be located in those specific positions. Clause 4.10.4, Functional Switches. This clause explains that heating systems must also be provided with functional switching in accordance with the functional switching requirements of the standard. It explains that functional switches must be installed in a readily accessible position either immediately next to an entrance to, or within, the room or area containing the heating system. It also explains that a functional switch may be the same device as the isolating switch where it meets the required conditions, and that for trace heating applications the location requirements for the functional switch do not apply. Clause 4.10.5, Additional Protection. This clause explains that all heating cables must be provided with additional protection by an ACD with a rated residual current not exceeding 30 mA. It explains that where heating units have a conductive covering, that covering must be earth. It explains that where underfloor heating units do not have a conductive covering, an earth metallic grid with spacing not exceeding 30 mm must be installed above the heating cable. It also explains that all heating units must be provided with sufficient mechanical protection to prevent damage. Clause 4.10.6 Signs. This clause explains that where heating cables are installed, suitable signs must be provided at each location to draw attention to their presence. It explains that where there is a risk of overheating due to coverings or building materials placed over embedded heating equipment, warning signs must be provided. It explains that this requirement can be met by clearly and permanently marking the functional switch or switches for the heated area, or by providing suitable labeling at the relevant distribution board. Clause 4.11 Electric duct heaters. This clause explains that the electrical parts of electric duct heater installations must comply with the requirements of this standard. It also explains that such installations fall within the scope of other standards and safety requirements, and that compliance may be required by regulatory authorities. Clause 4.12 Electricity converters. This clause introduces requirements for equipment that converts or stabilizes electrical supply. Clause 4.12.1 General. This clause explains that electricity converters include both static and dynamic equipment designed to stabilize voltage, change voltage or frequency, or provide temporary continuous supply when the main supply is interrupted. It explains that examples include UPS systems, semiconductor power converters and inverters, voltage stabilizers, motor generator sets, and rotary converters, and that transformers and engine-driven generating sets complying with ASNZS 3010 are not considered electricity converters. Clause 4.12.2 Selection and installation. This clause explains that guidance for selecting and installing electricity converters is provided in other relevant standards, depending on the type of converter, including UPS systems, semiconductor converters, batteries, and rotating electrical machines. Clause 4.12.3 Control. This clause explains that where an installation is supplied through an electricity converter, the converted supply must be controlled by isolating switching at the converter output or at the switchboard connected to that output. It explains that each converter must have suitable means for starting and stopping, and where more than one control device is used they must be grouped and clearly identified. It explains that converters must be arranged so they cannot energize the installation upstream of the point of connection, except where permitted subject to distributor requirements. It also explains that protection connections must remain intact whenever supply is available from the converter. Clause 4.12.4 Isolation. Clause 4.12.4.1 General. This clause explains that every electricity converter must have an independent isolating switch. It explains that the isolating switch must be located adjacent to or on the converter so the operator can clearly see anyone working on it, must be capable of being secured in the isolated position, must meet motor-related requirements where applicable, must be manually operated, and must not be capable of being overridden by programmable control systems. Clause 4.12.4.2 Electricity converters incorporating batteries. This clause explains that where batteries are part of an electricity converter, a clearly identified switch must be installed next to the batteries to interrupt their supply. It explains that a single switch may be used where it incorporates both the C and DC switching functions. Clause 4.12.5 Overcurrent protection. Clause 4.12.5.1 Electricity converter protection. This clause explains that electricity converters must be provided with overcurrent protection unless interruption of supply would create a greater hazard. It explains that overcurrent devices must be located as close as practicable to the converter output so unprotected conductors are kept as short as possible and do not exceed 15 meters, and that these conductors must be fully enclosed in non-flammable material. It explains that overcurrent protection may be provided internally within the converter or by limiting the converter's ability to supply fault current. It also explains that where converters operate in parallel, circulating harmonic currents must be limited so conductor ratings are not exceeded, and it describes acceptable methods for achieving this. Clause 4.12.5.2 Circuit Protection. Clause 4.12.5.2.1 General. This clause explains that every submain or final subcircuit supplied from an electricity converter must be individually protected and must include additional protection where required. Clause 4.12.5.2.2 are CDs. This clause explains that the waveform of earth fault current from electricity converters can affect a CD operation, and that the correct type of a CD must be selected. It explains that where an inverter is used, the RCD must be suitable for the inverter waveform and installed in accordance with the manufacturer's recommendations. Clause 4.12.6 Earthing. This clause explains that the output of an electricity converter must use the same earthing system as the associated installation. It explains that protective earthing conductors must not be switched and that critical protective connections, including the MEN connection, must remain intact whenever the converter is supplying the installation. Clause 4.12.7 Neutral Continuity. This clause explains that electricity converters, particularly static converters such as UPS systems, must be arranged so the neutral conductor to the load is not interrupted during bypass or maintenance switching. Clause 4.12.8 Electrical equipment connected to output. This clause explains that all equipment connected to the output of an electricity converter must be suitable for the voltage, current, and frequency produced by the converter, and it provides notes on conductor ratings, voltage drop, and a CD selection for converter-supplied circuits. Clause 4.13 Motors. This clause explains the safety requirements that apply to electric motors, focusing on preventing injury, preventing damage, and ensuring motors can be safely controlled, stopped, isolated, and protected during operation and maintenance. Clause 4.13.1 Protection against injury from mechanical movement. This clause is about protecting people from hazards created by moving parts of motors, such as shafts, fans, belts, and driven equipment, during normal use, stopping, or maintenance. Clause 4.13.1.1 Switching devices. Every motor must be provided with one or more switching devices that can start and stop the motor during normal operation, provide emergency stopping in accordance with Clause 2.3.5. and allow the motor to be isolated for mechanical maintenance in accordance with Clause 2.3.6, so the motor cannot operate while work is being carried out. Where several motors operate together as a group, such as in coordinated systems, one switching device may be used to control more than one motor. A separate switch for isolating the supply is not required where the motor is connected by a plug-in socket outlet, where it is part of an appliance with no exposed moving parts, or where the motor rating does not exceed 150 volt-amperes. Reference is made to Clause 2.3 for correct location and function of switching devices, and requirements may exist for motor isolating switches to be capable of being locked in the on position for certain applications. Clause 4.13.1.2 Rating of switches. The isolating switch must have a rating that is not less than the full load current of the motor when installed in the motor supply circuit, or the control circuit current when installed in the motor starter circuit. Where a switch operates directly in the motor supply circuit, it must be capable of safely interrupting the locked rotor or stall current of the motor. Where no manufacturer information is available, the stall current is taken as 8 times the full load current for alternating current motors, or 4 times the full load current for direct current motors. Suitable switches include those complying with ASNZS 3133 or ASNZS 60669.1 and marked with the letter M, switches complying with ASNZS 3947.3 and marked with utilization categories AC23 or EC23, and switches incorporated with and supplying a socket outlet intended for use with a plug complying with ASNZS 3112. Where one switch isolates more than one motor, it must be capable of interrupting the locked rotor or stall current of the largest motor, together with the full load current of all other motors in the group. Clause 4.13.1.3 Devices for starting and stopping. Devices used for starting and stopping motors must be located so they can be easily operated by the person responsible for the motor. A stopping device or isolating switch must be provided wherever danger is likely to occur due to moving parts. The stopping device must remain effective even if a fault occurs in the motor control circuit. Where motors are remotely controlled, stopping devices must be provided at all points where danger is likely to occur. Emergency stopping arrangements are required to comply with Clause 2.3.5. Clause 4.13.1.4, Protection against restarting or reversal. Where unexpected restarting of a motor could create danger, the motor must be provided with a means to prevent automatic restarting after stopping. This protection is not required where danger is avoided by other suitable measures, such as warnings or guarding. Where safety could be affected by incorrect direction of rotation, suitable measures must be taken to prevent danger caused by reversal of rotation, particularly where reverse current braking is used. Clause 4.13.2, Protection against overload. Each electric motor with a rating exceeding 370 watts must be provided with control equipment that includes protection against overload of the motor. This requirement does not apply to motors that are incorporated into electrical equipment that complies with an appropriate product standard. Clause 4.13.3, Protection against overtemperature. This clause deals with protection to prevent motors from overheating and damaging their windings. Clause 4.13.3.1, General. Electric motors must be provided with overtemperature protective devices where they may be required to run unattended and have a rating greater than 480 volt amperes for shaded pole motors, or greater than 240 volt amperes for other unattended motors, or where they have a rating greater than 2250 watts. Continuously running motors or motors under automatic control in non-domestic premises, where no person is normally present nearby, are considered to be unattended, although consideration may be given where a caretaker or responsible person is present. Examples of unattended motors include motors operating refrigeration in shops, motors located in remote parts of buildings such as drainage sumps, and motors operating communal refrigeration systems. Clause 4.13.3.2, Protection prohibited. Overtemperature protection must not be provided for motors associated with fire protection services, or where opening the motor circuit would itself create a hazard. Overtemperature protection is also not required for unattended submersible pump motors immersed in water where the motor rating does not exceed 2250 watts. Clause 4.13.3.3, Overtemperature protective devices. Overtemperature protection for motor windings must be provided by thermal overload protective devices complying with ASNZS 60947.4.1, or by built-in thermal protection complying with ASNZS 60947.8, or by another device that provides an equivalent level of protection. The protective device must disconnect the appropriate number of supply conductors, being one conductor for single-phase alternating current motors and direct current motors supplied from a two-wire system with one line earthed, and two conductors for three-phase alternating current motors and direct current motors supplied from two unearthed lines. Where automatic reset thermal protection is used for unattended motors, the device must protect the motor windings from excessive temperature under continuous tripping conditions. Clause 4.14, Transformers. This clause explains the installation and safety requirements that apply to transformers used in electrical installations, focusing on correct installation, control, protection, and earthing so that transformers operate safely and do not create electrical or thermal hazards. Clause 4.14.1, General. Transformers must be installed in accordance with clauses 4.14.2 through to 4.14.5. Certain transformers are excluded from these requirements, including instrument transformers, extra-low voltage transformers, luminous discharge tube transformers, and transformers that are incorporated into motor starters or similar electrical equipment. Clause 4.14.2, Secondary circuit. Clause 4.14.2.1, General. Wiring and electrical equipment connected to the secondary winding of a transformer must comply with the requirements of this standard that apply to extra low voltage, or high voltage installations, depending on the nominal voltage of the transformer secondary. Clause 4.14.2.2, Control and Protection. Conductors connected to the secondary windings of a transformer must be treated as submain or final subcircuit conductors as appropriate, and they must be controlled and protected in accordance with the relevant requirements of clauses 2.3 and 2.5. This requirement does not apply where the transformer secondary winding supplies only one submain or one final subcircuit, or where the secondary conductors have a current carrying capacity not less than the rated load current of the transformer primary winding multiplied by the ratio of the primary voltage to the secondary voltage. Clause 4.14.3, Low voltage transformer supply. Clause 4.14.3.1, Isolating transformers. Electrical equipment may be supplied through an isolating transformer in accordance with Clause 7.4. Clause 4.14.3.2, Other transformers. Electrical equipment supplied from transformers other than isolating transformers must be earthed in accordance with Clause 5.4. Earthing is not required on the secondary side where the low-voltage transformer output complies with the requirements of the ASNZS 61558 series. Clause 4.14.4, Autotransformers. An autotransformer must not be used to supply electrical equipment, including circuit wiring, where the voltage rating is less than the highest input or output voltage of the autotransformer. Clause 4.14.5, Step-up transformers. Where a transformer is used to raise the voltage above the supply voltage, no connection is permitted between the primary and secondary windings. An exception is allowed where a connection is made using a protective earthing conductor to provide an earth reference supply. Clause 4.15, Capacitors. This clause explains the safety requirements for the installation, control, protection, and discharge of capacitors, so stored electrical energy does not create a shock or equipment hazard. Clause 4.15.1, General. Capacitors must be installed in accordance with clauses 4.15.2 and 4.15.3. These requirements do not apply to capacitors that are fitted as an integral part of other electrical equipment, such as luminaires, where the capacitor is already covered by the product standard. Clause 4.15.2, Electrical equipment. Clause 4.15.2.1, General. Electrical equipment and wiring used to connect to capacitors must be suitable for the highest voltages, currents, and temperatures that are likely to occur in service. Adequate means must be provided so that heat produced by the capacitor and associated equipment can be safely dissipated. Clause 4.15.2.2, Rating of circuit breakers, switches or contactors. Any circuit breaker, switch, or contactor used to control a capacitor must be suitable for switching capacitors and must have an appropriate rating for the reactive component. An example of a suitable device is a contactor with utilization category AC6B to ASNZS 60947.4.1. Clause 4.15.2.3, Current carrying capacity of supply conductors. Where a capacitor is controlled by a circuit breaker, the conductors supplying the capacitor must have a current carrying capacity not less than the greater of 135% of the rated current of the capacitor, or the setting of the circuit breaker. Where a capacitor is permanently connected to a motor circuit, the conductors must have a current rating not less than the greater of 1/3 of the rating of the motor circuit conductors, or 135% of the rated current of the capacitor. Clause 4.15.3, Provision for discharge and control. Clause 4.15.3.1, General. Capacitors with values greater than 0.5 microfarads must be provided with a discharge path. These capacitors must be controlled using one of the methods described in clauses 4.15.3.2 or 4.15.3.3. After a capacitor has been disconnected from the supply, the voltage between its terminals must reduce to not more than 50 volts within 1 minute for capacitors rated up to and including 650 volts, or within 5 minutes for capacitors rated above 650 volts. Capacitors and electrical equipment containing capacitors must be provided with a warning notice advising that capacitors must be completely discharged before working on the equipment. Clause 4.15.3.2, Capacitors connected in parallel with individual appliances. Where a capacitor is connected in parallel with an individual appliance, it must be connected so that the windings of the appliance provide a permanent discharge path for the capacitor, and no switch or fuse is permitted between the capacitor and the appliance. These requirements do not apply where the capacitor incorporates a permanently connected discharge device. In this arrangement, the capacitor is regarded as being controlled by the control gear of the appliance. Clause 4.15.3.3 Capacitors not connected in parallel with individual appliances. Where a capacitor is not connected in parallel with an individual appliance, it must be controlled by a circuit breaker fitted with an overcurrent release. Provision must be made to discharge the capacitor either by auxiliary contacts of the circuit breaker that automatically connect a discharge device immediately when the capacitor is disconnected from the supply, or by a permanently connected discharge device connected in parallel with the capacitor. Where the capacitor rating does not exceed 100 kV ampere reactive, or where each capacitor in a shunt-connected capacitor bank does not exceed 100 kV ampere reactive, the capacitor may instead be controlled by a quick make and break switch or contactor protected by fuses, provided the switch incorporates a means of manual operation for individual isolation of each capacitor or the capacitor bank as a whole, and a permanently connected discharge device is provided. No fuse or switch is permitted between the auxiliary contacts of the circuit breaker and the discharge device, or between a permanently connected discharge device and the capacitor. Clause 4.16 Electrical equipment containing liquid dielectrics. This clause explains the safety precautions required where electrical equipment contains significant amounts of flammable liquid, such as oil-filled transformers or capacitors, so that burning liquid and combustion products like flame, smoke, or toxic gases do not spread to other parts of the premises. Clause 4.16.1 General. Wherever electrical equipment contains flammable liquid in significant quantity, precautions must be taken to prevent the spread of burning liquid and the products of combustion to other areas of the building or site. Clause 4.16.2 Liquid dielectrics having a flash point not exceeding 250 degrees Celsius. Where equipment is filled with a liquid dielectric with a flash point not exceeding 250 degrees Celsius and the total liquid capacity exceeds 50 liters in any unit or group of adjacent units, measures must be taken to limit the spread of fire, and these measures may include fire-resisting enclosures, dikes, bunds, curb areas, basins, trenches filled with coarse crushed stone, or trapped drains where required, with smaller quantities generally requiring only measures to prevent liquid escape and with consideration given to automatically switching off the supply at the start of a fire. Clause 4.17 Batteries. This clause indicates that information on selecting and installing batteries is provided in as NZS 3011.1, as NZS 3011.2, and as NZS 5139, which should be followed where batteries form part of an electrical installation. Clause 4.18 Gas appliances and equipment. Clause 4.18.1 Gas appliances. Clause 4.18.1.1 General. Any gas appliance connected to an electricity supply must be provided with an electrical means of isolation located adjacent to the appliance and accessible when the appliance is installed, and for cooking appliances the isolation device must not be located in prohibited positions near open cooking surfaces, with appliances that combine gas and electric open cooking surfaces also complying with the requirements for cooking appliances. Clause 4.18.1.3 In New Zealand only. In New Zealand installations, a gas appliance must be provided with a means of electrical isolation using either a plug connected to an accessible switched socket outlet, a plug connected to a socket outlet that may be inaccessible but controlled by a separate accessible switch operating in all active conductors, or an accessible lockable isolating switch operating in all active conductors. Clause 4.18.2 Gas cylinders containing heavier than air gases outdoors. Clause 4.18.2.1 Sources of ignition. Electrical equipment that could act as an ignition source must not be installed within the hazardous areas associated with outdoor gas cylinders, except where equipment is approved or not considered an ignition source under the relevant clauses. Clause 4.18.2.2 Hot particles in surfaces. Exclusion zones in hazardous areas for hot particles and surfaces are determined in accordance with Clause 7.7 and as NZS 6007.9.14. Clause 4.18.3 Gas cylinders indoors, New Zealand only. In New Zealand, indoor compartments provided for gas cylinders must not contain electrical equipment or wiring connections that could act as ignition sources, such as socket outlets, switches, or appliances. Clause 4.18.4 Gas relief vent terminal, natural gas, LP gas or biogas. Electrical equipment that could act as an ignition source must not be installed within the hazardous areas associated with gas relief vent terminals, except where equipment complies with the relevant zone requirements. Clause 4.18.5 Reticulated lighter-than-air gas system, metering system and regulators, New Zealand only. In New Zealand domestic installations, only electrical equipment that is directly associated with the gas supply may be installed within the hazardous area associated with reticulated gas regulators. Clause 4.19 Air conditioning and heat pump systems. Air conditioning and heat pump systems that incorporate a compressor must be provided with a lockable isolating switch in accordance with Clause 2.3.2.2, installed adjacent to but not on the unit, and arranged so that all parts of the system, including ancillary equipment, are isolated, with additional isolating and warning arrangements required where internal and external units are supplied separately. Clause 4.20 Lifts. Clause 4.20.1 General. Electrical installations for lifts must comply with this standard and the applicable building code, covering electric lifts, electro-hydraulic lifts, goods lifts, passenger lifts, and motor room-less lifts, with emergency lifts also meeting the additional requirements for safety services. Clause 4.20.2 Lift supply arrangement. Each lift must be supplied by a dedicated circuit to ensure reliable and identifiable electrical supply. Clause 4.20.3 Labeling. Lift circuits must be clearly identified by contrasting coloring or other suitable means so that they are recognizable and not inadvertently switched off. Clause 4.20.4 Motor room-less lifts. Clause 4.20.4.1 General. Motor room-less lifts are lifts designed without a traditional lift motor room, and where installed as emergency lifts they must also comply with the additional safety service requirements. Clause 4.20.4.2 MRL switchboards. Switchboards associated with motor room-less lifts must not be located in the lift shaft and must be readily accessible where they are remote from the main switchboard. Clause 4.20.4.3 Switchgear. Protective and control devices for motor room-less lifts must be located in a readily accessible position to allow safe operation, inspection, and maintenance. That now brings us to the end of Section 4. We have covered the key requirements for selecting, installing, protecting, and connecting electrical equipment, including socket outlets, lighting, motors, transformers, capacitors, heating systems, gas-related equipment, and special installations such as lifts. The main message from this section is that electrical equipment must always be suitable for its job, installed correctly, and protected against the conditions it will face during normal operation and fault situations. With Section 4 complete, we are now ready to move on to the next section of the standard. Hi everyone, my name is Aria, and I work alongside Whit Roy as an electrical tutor. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 3000, 2018. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for EWRB exam. What this audiobook does is take the key ideas from the standard and explain them in simple, spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real installations. So think of this as a learning companion, not a replacement for the actual standard. All right, let's get started. Hi everyone, welcome back. In this section we're working through Section 5, Earthing Arrangements and Earthing Conductors. This section explains how earthing systems are arranged in New Zealand electrical installations, how protective earthing and bonding are provided, and how earth fault protection is achieved by automatic disconnection of supply. We'll look at main earthing conductors, mean connections, earth electrodes, continuity, equipotential bonding, and earth fault loop impedance. Everything in this section is critical for electrical safety, because correct earthing limits touch voltages and ensures protective devices operate quickly during a fault. Let's begin with Section 5. Clause 5.1, General. This part explains that Section 5 sets the basic requirements for how earthing arrangements are chosen and installed, so the installation can meet the overall safety goals of Part 1 of the standard. Clause 5.1.1, Application. This clause explains that the rules in this section apply to the selection and installation of earthing arrangements, and these arrangements must be suitable to satisfy the general safety requirements of the standard. Clause 5.1.2, Selection and Installation. This clause explains that earthing arrangements must be chosen and installed so they can carry out several essential functions. These include allowing the supply to disconnect automatically if a short circuit, earth fault, or excessive earth leakage current occurs through protective earthing, allowing equipment that needs an earth reference to operate correctly through functional earthing spoken as FE, reducing dangerous voltage differences between exposed conductive parts and other conductive parts by equipotential bonding, providing a reliable low-impedance path for earth fault and earth leakage currents without damage from thermal, mechanical, or environmental effects, and allowing exposed conductive parts and extraneous conductive parts to be properly connected to the earthing system. Clause 5.1.3, Main Earthing System. This clause explains that the protective earthing arrangements in this standard apply to installations connected to a multiple earthed neutral system, spoken as MEN, which is the standard distribution system used in New Zealand. In this system, the neutral conductor, spoken as the PEN conductor, is earthed at the source of supply and again at regular points along the distribution system, including at each connected installation. Within the electrical installation, the earthing system is kept separate from the neutral conductor and arranged so exposed conductive parts of equipment can be connected to earth. Clause 5.1.4, Other Earthing Systems. This clause explains that earthing systems other than the MEN system may be used, provided the general safety requirements of Part 1 are met and the characteristics of the supply system are taken into account. The examples given include installations complying with IEC 60364, surface mine installations complying with ASNZS 3007, some existing installations permitted under earlier editions of the standard, installations not supplied from a distribution system, and installations using IEC 60364 systems that allow alternatives such as TN, TT, or IT systems. Clause 5.2, Earthing Functions. This clause introduces the different purposes that earthing can serve within an electrical installation. Clause 5.2.1, Protective Earthing. This clause explains that when a fault occurs between a live part and an exposed conductive part, a dangerous touch voltage can appear between parts that can be touched at the same time. Protective earthing is intended to limit this risk by ensuring automatic disconnection of supply. This is achieved by connecting exposed conductive parts to the earth neutral of the distribution system and by using overcurrent or earth leakage protection devices that disconnect the affected part of the installation within the allowed time. Clause 5.2.2, Functional Earthing FE. This clause explains that some equipment requires an earth connection for correct operation rather than for safety. In these situations, functional earthing conductors are not required to withstand fault currents and are not identified in the same way as protective earthing conductors. Examples include functional earth connections used in certain RCDs to allow internal electronic circuits to operate if the incoming neutral becomes disconnected, and conductors used for systems such as cathodic protection or radio interference suppression. Where a clean earth is required for data or signaling, the equipment manufacturer should be consulted. Functional earthing for data and signaling should be insulated from protective earthing and normally connected at only one point, usually at the main earthing terminal or connection bar, and care is needed to prevent accidental contact between the two systems. No specific insulation color is assigned, but green or green and yellow must not be used. Clause 5.2.3, Earthing for combined protective and functional purposes. This clause explains that when earthing is used for both protective and functional purposes, the requirements for protective earthing always take priority. Clause 5.3, Earthing system parts. This clause explains that when an electrical installation uses protective earthing with automatic disconnection of supply and is connected to an MEN distribution system, the earthing system must include all the necessary parts to make it work safely and effectively. These parts include protective earthing conductors to connect exposed conductive parts, a main earthing conductor, a main earthing terminal or connection bar, the MEN connection between the main earthing terminal and the supply neutral bar, an earth electrode, and equipotential bonding for extraneous conductive parts where required. It also explains that all parts of the earthing system must comply with the detailed requirements set out in the following clauses of this section. Clause 5.3.1, General. This clause explains that the protective earthing arrangement of an installation connected to the MEN system is made up of several essential components that work together to allow fault currents to flow safely and to ensure automatic disconnection of supply. These components must all be present where required, and they must meet the requirements of the later clauses that describe materials, sizes, and installation rules. Clause 5.3.2, Earthing conductor material and type. This clause introduces the rules that control what materials earthing conductors may be made from and what forms they may take, so that they are suitable for carrying fault currents reliably. Clause 5.3.2.1, Conductor material. This clause explains that earthing conductors are normally made from copper or aluminium, but other materials may be used if they perform at least as well in terms of electrical resistance and corrosion resistance. Clause 5.3.2.1.1, Copper conductors. This clause explains that copper earthing conductors must be made from high conductivity copper and may be stranded, circular braided, or solid. Where solid copper is used, it must not be smaller than 10 square millimeters in cross-section and must have a minimum thickness of 1.5 millimeters. The clause also explains that smaller solid conductors may be allowed where a particular cable standard permits it, and that copper cable components such as sheaths or screens may act as earthing conductors if they meet the relevant requirements. Clause 5.3.2.1.2, Aluminium conductors. This clause explains that aluminium conductors may be used for earthing, but only if specific conditions are met. Smaller aluminium conductors must be solid, and a minimum size is required for main earthing conductors. Connection methods must follow the rules of Section 3. Installation must prevent corrosion, and aluminium earthing conductors must not normally be installed underground or in damp conditions unless they are specifically designed for that environment. Clause 5.3.2.1.3, Other materials. This clause explains that materials other than copper or aluminium may be used as earthing conductors if their resistance is no greater than that of a copper conductor of the required size and if their resistance to corrosion is suitable for the application. Clause 5.3.2.2, Conductor type. This clause explains that protective earthing conductors may be installed as separate conductors, installed together with live conductors in the same enclosure, incorporated within multi-core cables, or provided in the form of busbars. It also explains that, subject to special conditions, certain conductive parts such as wiring enclosures, cable sheaths, armors, screens, conductive frameworks, and catenary wires may be used as protective earthing conductors. It clearly explains that pipes carrying gas, water, flammable liquids, or similar non-electrical services must not be used as earthing conductors, although bonding to them may still be required. Clause 5.3.2.3, Special conditions. This clause explains that when conductive wiring enclosures, cable sheaths, armors, screens, frameworks, or similar parts are used as protective earthing conductors, extra conditions apply. The electrical equipment must be supplied by live conductors contained within the enclosure, and there must be reliable electrical continuity between the enclosure and the equipment being earthed. Where cable sheaths or screens are used, the live conductors must be incorporated within the same cable. The clause also explains that certain exceptions apply for specific cable types where protective earthing conductors are associated only with the circuit supplied by that cable. Clause 5.3.2.4 Insulation. This clause explains that earthing conductors are generally required to be insulated. It then explains that some forms of earthing conductors do not require insulation, including aerial conductors, flat-braided conductors, bus bars, certain cable sheaths, conductive frameworks and wiring enclosures deemed to be earthing conductors, copper conductors buried directly in the ground and catenary wires. Clause 5.3.2.5 Identification. This clause explains that insulated earthing conductors must be identified in accordance with the identification rules of the standard so they can be clearly recognized. Clause 5.3.3 Earthing conductor size cross-sectional area. This clause introduces the requirements that control how large earthing conductors must be, so they can safely carry fault currents and remain reliable over time. Clause 5.3.3.1 Protective earthing conductors. This clause explains that the size of a protective earthing conductor must be sufficient to carry prospective fault current for the time needed for the protective device to operate, must provide an appropriate earth fault loop impedance, must have enough mechanical strength and resistance to external influences, and must allow for any deterioration that may reasonably occur over time. Clause 5.3.3.1.1 General. This clause explains that the required cross-sectional area of a copper protective earthing conductor may be selected either from the appropriate table based on the size of the largest active conductor supplying the installation, or by calculation. It also explains several exceptions and notes, including how to deal with parallel active conductors, how to select sizes when conductor sizes do not exactly match the table, and how conductive enclosures or frameworks used as earthing conductors must have an impedance no greater than that of an equivalent copper earthing conductor. Clause 5.3.3.1.3 Calculation. This clause explains how to calculate the minimum size of a protective earthing conductor using a formula. In spoken form, the formula says that S equals I times the square root of T divided by K. S is the required cross-sectional area of the protective earthing conductor, measured in square millimeters. I is the value of the fault current, measured in amperes, that would flow through the overcurrent protective device if a short circuit occurred with negligible impedance. T is the disconnection time of the protective device, measured in seconds, that corresponds to that fault current. K is a factor that depends on the material of the earthing conductor, the insulation, and the initial and final temperatures the conductor can safely withstand. This clause explains that the calculated size must not be less than the result of this equation and that if the calculation produces a non-standard conductor size, the next largest standard size must be used. Clause 5.3.3.2 Main earthing conductor. This clause explains that the size of the main earthing conductor depends on how it is connected. Where it connects the main earthing terminal to an earth electrode, its size is determined in relation to the size of the largest active conductor of the consumer mains, using the relevant table. Minimum and maximum copper sizes are specified. The clause also explains conditions where the size may instead be determined by the largest outgoing submain or final subcircuit, or by the minimum size needed to carry maximum demand. Where the conductor connects an earth bar to an earth bar within a supply substation, the size may be selected from the table or by calculation. It also explains that in these cases the main earthing conductor forms part of the earth fault current path and must be sized based on the prospective fault current and disconnection time. Clause 5.3.3.3 Aerial earthing conductors. This clause explains that aerial protective earthing conductors must be sized in accordance with the general earthing conductor rules and must also comply with additional requirements that take into account conductor type and span length. Clause 5.3.3.4 Earthing conductors and cables, flexible cables or flexible cords. This clause explains how to select the minimum size of protective earthing conductors when they are incorporated into cables or flexible cords. It explains the minimum sizes for single-core cables, multi-core cables, and flexible cords, including special conditions where smaller sizes may be permitted. It also explains the requirements for screen and drain wires and the exception where separation from live conductors by double insulation applies. Clause 5.3.4, Main Earthing Terminal Connection or bar. This clause explains that every electrical installation must have a main earthing terminal, connection, or bar located at the main switchboard. All earthing and bonding conductors are required to be connected, either directly or indirectly, to this point so that an equipotential bonding network is formed. This includes protective earthing conductors, the main earthing conductor, the MEN connection, equipotential bonding conductors, and functional earthing conductors where these are required. It also explains that the main earthing terminal or connection may be a soldered connection. Clause 5.3.5, MEN connection. This clause introduces the requirements for the MEN connection, also known as the MEN link. Clause 5.3.5.1, General. This clause explains that every electrical installation must have an MEN connection at the main switchboard. The purpose of this connection is to link the earthing system of the installation to the supply neutral conductor by connecting the main earthing terminal or bar to the neutral bar. It explains that in some cases the neutral to earth connection may be made at other permitted locations, such as within an owner or user-operated supply substation, at a distributor's neutral bar, or through an earthing conductor or terminal provided by the electricity distributor. It also explains that the MEN or NE connection must be located in a position that is accessible for disconnection and testing. Clause 5.3.5.2, Size. This clause explains that the MEN connection must be a conductor that complies with the general earthing conductor requirements and must be large enough to carry the maximum current that could flow under short-circuit conditions. It explains that the minimum size must not be less than the current carrying capacity of the main neutral conductor, and for certain large switchboards it must be sized in the same way as a protective earthing conductor. It also explains situations where the minimum size of the MEN connection does not need to be larger than the main earthing conductor, such as where short-circuit protection is provided on the supply side of the consumer mains, or where double insulation of the consumer mains is maintained up to the supply protective device. Clause 5.3.5.3, Identification. This clause explains that where the MEN connection is insulated, the insulation must be colored green, or green and yellow, in accordance with the conductor identification rules. Clause 5.3.6, Earth electrodes. This clause introduces the requirements for connecting the earthing system of an installation to the general mass of Earth. Clause 5.3.6.1, General. This clause explains that the connection of the installation earthing system to the general mass of Earth must be made using an earth electrode. It also explains that while no specific resistance to earth value is required for installations connected to an MEN system, the combined earthing system must still meet the earth fault loop impedance requirements. It also notes that guidance on measurement methods is available in other standards. Clause 5.3.6.2, Types. This clause explains that earth electrodes must be selected so they can resist corrosion and have adequate mechanical strength, taking into account soil type and environmental conditions. It explains that electrodes must be of approved types, and that in some cases conductive reinforcement in concrete foundations that are in contact with the ground may be used instead of a separate electrode. Clause 5.3.6.3, Installation. This clause explains how earth electrodes must be installed. For New Zealand installations, vertical electrodes must be driven to a minimum depth of 1.8 meters. Where strip-type electrodes are installed horizontally, they must be buried with at least half a meter of cover and must have a minimum horizontal length of 7.5 meters. Clause 5.3.6.4, Location. This clause explains that earth electrodes must be installed in a location that maintains effective contact with soil that does not dry out excessively, such as ground exposed to weather or areas that naturally remain moist. It explains that electrodes must be separated from other buried conductive surfaces to reduce corrosion caused by electrolytic action, and that the connection between the main earthing conductor and the electrode must be accessible. It also explains that the location of the earth electrode must be identified at the main switchboard. Clause 5.3.7 Functional earthing conductors. This clause explains that functional earthing conductors provided only to ensure correct operation of equipment do not need to meet the same requirements as main or protective earthing conductors. It also explains that where earthing is used for both protective and functional purposes, the protective earthing requirements take priority. The clause notes that functional earth connections should normally be independent of protective earth and limited to the main earth connection point, and that where a clean earth is specified, the equipment manufacturer should be consulted. Clause 5.4 Earthing of equipment. This clause introduces the requirements for earthing different types of electrical equipment and conductive parts. Clause 5.4.1 General. This clause explains the general principles for earthing equipment. Clause 5.4.1.1 Exposed conductive parts. This clause explains that exposed conductive parts of electrical equipment must be earthed when the equipment is installed or could operate in an earthed situation, or where exposed conductive parts are electrically continuous with extraneous conductive parts located in an earthed situation. It explains that equipment protected by electrical separation does not require earthing, and that equipment supplied by SELV or PELV does not need to be earthed. It also explains that equipment with double insulation does not require earthing, provided the wiring and internal construction maintain that insulation under all conditions. Clause 5.4.1.2 Conductive building materials. This clause explains that conductive building materials must be earthed in accordance with the bonding requirements of the standard. Clause 5.4.1.3 Connection of electrical equipment to earth. This clause explains that equipment required to be earthed must be arranged so it can be connected to earth by protective earthing conductors or by other permitted earthing media such as conductive parts of cables, wiring enclosures, or switchboard frameworks, provided these comply with the earthing conductor requirements. Clause 5.4.2 Socket outlets. This clause explains that the earthing contact of every socket outlet must be earthed. It also explains that socket outlets supplied as separated circuits must be bonded to the protective bonding system, and that socket outlets supplied as extra low voltage circuits must not have an earthing contact. Clause 5.4.3 Lighting points. This clause explains that a protective earthing conductor must be provided at every lighting point, including where transformers supply extra low voltage lighting. It also explains situations where a protective earthing conductor is not required, such as certain pool and fountain zones, specific insulated lamp holders, lighting points earthed through conductive conduit or pipe, luminaires installed on non-conductive poles in unearthed situations, and extra low voltage lighting points. Clause 5.4.4 Luminaires. This clause explains that exposed conductive parts of luminaires must be earthed, except where earthing is not required under the general rules or where a protective earthing conductor is not required at the lighting point. Clause 5.4.5 Conductive supports for aerial conductors. This clause explains that conductive poles, posts, brackets, stay wires, and similar supports for low-voltage aerial conductors must be earthed. It then explains several exceptions where earthing is not required, such as where supports are permanently separated from conductors by double insulation, where adequate clearances are maintained, or where stay wires are effectively insulated within reach. Clause 5.4.6 Structural metalwork including conductive building materials. This clause introduces the requirements for earthing structural metalwork. Clause 5.4.6.1 General. This clause explains that structural metalwork forming part of a structure containing an electrical installation must be earthed where it is permanently connected to installation wiring. It explains that the size of the earthing conductor must be selected based on the size of the largest active conductor within the framework, and that for combined outbuildings each building must have its own earthing connection. Clause 5.4.6.2 Connection to protective earthing conductors. This clause explains that earthing of parts of structural metalwork may be achieved by connecting a suitably sized protective earthing conductor at one point, provided the resistance between the earth bar and all parts to be earthed does not exceed 0.5 ohms. Clause 5.4.7 Submersible pumps. This clause explains that exposed conductive parts of submersible pumps must be earthed by a protective earthing conductor terminated at a pump motor. It explains that the termination must be sealed against moisture and protected from mechanical damage and corrosion, and that this may be achieved by terminating at a housing terminal or an internal or external constructional component that meets the bonding requirements. Clause 5.4.8 Variable frequency devices. This clause explains that devices producing high-frequency currents in the protective earth can create dangerous touch voltages. It explains that these voltages may not be detected using normal test instruments, and that the manufacturer's instructions must be followed when installing this type of equipment. It also draws attention to the safety requirements for electronic equipment in AS 62103. Clause 5.5 Earthing arrangements. This clause introduces how earthing conductors are arranged within an installation so that all required parts are correctly connected, continuous, and able to perform their protective function. Clause 5.5.1 Main earthing conductor. This clause introduces the requirements for the main earthing conductor that connects the installation earthing system to the earth electrode. Clause 5.5.1.1 Arrangement. This clause explains that the main earthing conductor must run from the main earthing terminal, connection, or bar at the main switchboard directly to an earth electrode that meets the requirements of Clause 5.3.6. The conductor must be run as directly as practicable and must not be connected to the terminal of any accessory, luminaire or appliance. It also explains that, in some cases, the main earthing conductor may instead be taken to an earth bar within a customer's substation, or to an earthing conductor or terminal provided by the electricity distributor, including a distributor-neutral bar where required. It is noted that distributor-provided earthing arrangements may include a special earthing conductor, the conductive sheath of a supply cable, or a neutral bar at a substation. Clause 5.5.1.2 Connection to earth electrode. This clause explains that the connection between the main earthing conductor and the earth electrode must be accessible so it can be visually inspected and tested. It explains that access may be provided by an underground pit with a cover that remains accessible above ground, provided there is enough space for testing connections and the pit is clearly identified. Where reinforcing steel is used as the earth electrode, this requirement is satisfied by providing a test point on the main earthing conductor. The clause also explains that the connection must be made using a suitable device that provides good electrical conductivity, must be protected against mechanical damage at the location, and must be suitably protected against corrosion. Clause 5.5.1.3 Labeling. This clause explains that the main earthing conductor must have a permanent label at the point where it connects to the earth electrode. The label must clearly warn that the main electrical earthing conductor must not be disconnected. It also explains that where the method of connection does not allow disconnection, this labeling requirement does not apply. Clause 5.5.1.4 Resistance. This clause explains that the resistance of the main earthing conductor, measured between the main earthing terminal or bar and the earth electrode, including the electrode connection, must not exceed 0.5 ohms. Clause 5.5.2 Protective earthing conductors. This clause introduces how protective earthing conductors are arranged and connected throughout the installation. Clause 5.5.2.1 Arrangement. This clause explains that all protective earthing conductors must be directly connected to the main earthing conductor or to another point on the earthing system that is connected to the main earthing conductor. It explains that protective earthing conductors must not normally carry load current. The clause then explains that connections may be made at the main earthing terminal or bar at the main switchboard, at any point along the main earthing conductor, at a dedicated earthing terminal or bar at a distribution board that complies with the requirements, or at a suitable point on another protective earthing conductor arranged in accordance with the rules. Clause 5.5.2.2 Restricted connections. This clause introduces restrictions on how protective earthing conductors may be shared or extended. Clause 5.5.2.2.1 Circuits. This clause explains that where a protective earthing conductor is incorporated in the same cable sheath or wiring enclosure as its associated live conductors, it must only be used to earth equipment supplied from that same circuit. It also explains that this does not prevent the use of an unenclosed common protective earthing conductor serving multiple circuits. Clause 5.5.2.2.2 Earthing of equipment. This clause explains that a protective earthing conductor that originates at a distribution board must not be used to earth equipment that is supplied from another switchboard. Clause 5.5.2.2.3 Earthing facilities for distribution boards. This clause explains that a protective earthing conductor originating at a distribution board must not be used to provide earthing facilities for another distribution board. It then explains exceptions where the earthing facilities originate from the same distribution board as the associated active conductors, or where a common protective earthing conductor connected to the main earthing conductor is used, provided continuity does not depend on terminals at distribution boards and there is a direct connection between the common conductor and any branch protective earthing conductors. Clause 5.5.3 Particular methods of earthing. This clause introduces specific earthing methods for certain installation situations. Clause 5.5.3.1 Outbuildings. This clause explains that all parts of an electrical installation in or on an outbuilding that are required to be earthed must be earthed using one of the permitted methods. It explains that an individual outbuilding may be earthed either by connection to a protective earthing conductor from the main installation, or as a separate MEN installation. It also explains that combined outbuildings must be connected to a protective earthing conductor and must not be earthed as separate MEN installations. For separate MEN installations, the clause explains that the submain neutral supplying the outbuilding becomes a combined protective earthing and neutral conductor, spoken as APEN conductor, and the outbuilding installation is treated as a separate electrical installation. It explains limits on the number of MEN connections, how distribution boards are treated, how the earthing conductor to the earth electrode is regarded, how submains may be run, and that the combined PEN conductor must not rely on parallel paths through pipes or structural metal. Clause 5.5.3.2 Wiring systems. This clause explains that exposed conductive parts of wiring enclosures must be earthed at the end adjacent to the switchboard or accessory where the wiring system originates. It also explains that conductive sheaths, armors, and screens of cables or cords must be earthed at the same originating end. Clause 5.5.3.3 Electrical equipment supplied by flexible cord or flexible cable. This clause explains that exposed conductive parts of electrical equipment supplied by a flexible cord or flexible cable must be earthed by connection to a protective earthing conductor that is incorporated with the associated live conductors in the same sheath, braid, or enclosure. Clause 5.5.3.4 Switchboards. This clause explains that electrical equipment mounted on a conductive switchboard framework may be earthed by that framework, provided the framework complies with the protective earthing conductor requirements. Clause 5.5.3.5 Unprotected consumer mains. This clause explains that exposed conductive parts associated with consumer mains that do not have short-circuit protection on the supply side must be earthed by a conductor with a current carrying capacity at least equal to that of the main neutral conductor, or by direct connection to an earth bar of equivalent capacity. It explains that these consumer mains are those not protected by a service protective device, and that fault conditions may cause the earthing conductor to carry maximum fault current continuously for the duration of the fault. It also explains permitted connection points and notes situations where the requirement does not apply when double insulation is maintained and supply-side protection is provided. Clause 5.5.3.6 Conductive switchboard enclosures associated with unprotected consumer mains. This clause explains the earthing arrangements for conductive switchboard enclosures where unprotected consumer mains are present, including how connections are made to the main neutral conductor, the main earthing bar, and the MEN link, depending on the insulation and protection conditions of the consumer mains. Clause 5.5.3.7, Additional Notes and Exceptions. This clause explains that systems using double insulation for aerial conductors may be considered as providing double insulation, lists examples of exposed conductive parts associated with consumer mains, and notes that upstream distributor protection may provide short-circuit protection in some cases. Clause 5.5.4, Continuity. This clause explains that earthing conductors must be protected so their electrical continuity is maintained over time. They must be protected against mechanical damage, chemical deterioration, and forces such as vibration or movement. Where painted or coated metal parts are bolted or clamped together, suitable devices such as star washers or similar methods must be used so paint or coatings are effectively cut through and a reliable earth connection is maintained across those joints. Clause 5.5.4.1 General. This clause explains that earthing conductors must be installed and protected in a way that ensures they remain electrically continuous and reliable throughout the life of the installation. Clause 5.5.4.2 Conductive wiring enclosures. This clause explains that conductive wiring enclosures and associated fittings that are required to be earthed, including those used as an earthing medium, must be mechanically secure and electrically continuous. It also explains that the impedance of the wiring enclosure earthing arrangement must meet the earth fault loop impedance requirements of the standard. Clause 5.5.4.3 Conductive sheaths, armors and screens of cables. This clause explains that conductive cable sheaths, armors, and screens that are required to be earthed must be mechanically and electrically continuous. Their impedance must be no greater than that required for an equivalent copper earthing conductor, ensuring fault currents can flow effectively. Clause 5.5.4.4 Connecting devices. This clause explains that where electrical equipment is connected by a plug-in socket or similar device, any earthing connection to exposed conductive parts must be made automatically before the live connections are made when the plug is inserted, and must be broken automatically after the live connections are broken when the plug is withdrawn. Clause 5.5.5 Installation. This clause introduces the installation requirements that ensure earthing conductors remain protected and effective. Clause 5.5.5.1 General. This clause explains that all earthing conductors and other earthing media must be installed to provide adequate protection against expected mechanical damage, accidental interference, and chemical deterioration. It also notes that in areas of high lightning activity, additional guidance should be considered. Clause 5.5.5.2 Protection against mechanical damage. This clause explains that earthing conductors must be protected against being displaced, damaged, or cut. Protection may be achieved by fixing the conductor with suitable clips or clamps that do not damage the conductor strands, by guarding the conductor with metallic barriers or other robust material, or by installing the conductor within a wiring enclosure. Clause 5.5.5.3 Protection against corrosion. This clause explains that earthing conductors and their fixings must be protected against corrosion, including corrosion caused by moisture or contact between dissimilar metals. In underground or damp locations, all joints and terminations must be sealed to prevent moisture ingress and fittings must be corrosion resistant. Where exposed to the weather, joints and terminations must also be corrosion resistant and protected to prevent moisture entering and affecting the conductor. Clause 5.5.5.4 Aerial earthing conductors. This clause explains that aerial earthing conductors must be properly supported and must be identified in accordance with the conductor identification rules. Clause 5.5.5.5 Buried earthing conductors. This clause explains that earthing conductors buried in the ground or installed in underground enclosures must meet depth and mechanical protection requirements appropriate to the installation method. It also explains that bare earthing conductors may only be buried directly in the ground if they are copper and not less than 25 square millimeters. A conductor passing through a wall or partition is not considered to be a buried earthing conductor. Clause 5.5.6 Connections. This clause introduces requirements for how earthing connections must be made. Clause 5.5.6.1 Conductors. This clause explains that connections in earthing conductors must comply with the general connection requirements of the standard. Clause 5.5.6.2, Constructional Components. This clause explains that exposed conductive parts of electrical equipment may be earthed by connecting a protective earthing conductor to a constructional bolt, stud, or screw that forms an integral part of the equipment, provided specific conditions are met. The terminal must be mechanically and electrically continuous with the exposed conductive part. The protective earthing conductor must be removable without reducing the effectiveness of the fixing or causing parts of the equipment to lose rigidity. Removing covers to access terminals must not disturb the earthing connection, and the bolt, stud, or screw must not be used to position or adjust the equipment. Clause 5.6, Equipotential Bonding. This clause introduces equipotential bonding and explains that its purpose is to reduce the risk of dangerous voltage differences between exposed conductive parts of electrical equipment and extraneous conductive parts. Clause 5.6.1, General. This clause explains that voltage differences can arise from several sources, including faults on extraneous conductive parts such as water or gas pipes, load currents flowing through the soil, telecommunication system voltages on nearby equipment, and lightning discharges affecting the installation or incoming services. Clause 5.6.2, Arrangement. This clause explains that equipotential bonding must be provided in accordance with the detailed requirements of the following clauses so that potential differences are minimized between electrical equipment connected to the earthing system and other conductive parts that may independently contact earth. It also explains that additional equipotential bonding requirements apply in special locations and installations, including hospitals, explosive atmospheres, telecommunications installations, film and broadcast sites, photovoltaic systems, grid-connected inverters, generating systems, and separated circuits. Clause 5.6.2.2, Conductive Water Piping. This clause explains that conductive water piping that is installed and accessible within a building, and that is continuously conductive from inside the building to a point of contact with the ground, must be bonded to the earthing system. The bonding must be made using an equipotential bonding conductor connected to the main earthing conductor or earthing bar, as close as practicable to where the pipe enters the building. It also explains that this bonding must be to the earthing system of the installation and not directly to the earth electrode alone. Clause 5.6.2.3, Other Conductive Piping Systems. This clause explains that conductive piping systems such as fire sprinkler pipes, gas pipes, water pipes, or pipes carrying flammable liquids that are unavoidably in contact with exposed conductive parts of electrical equipment must be connected to that equipment by equipotential bonding. It also explains that bonding is not required where the piping system is already effectively earthed through its connection to associated electrical equipment. Clause 5.6.2.4, Conductive Cable Sheaths and Conductive Wiring Enclosures. This clause explains that conductive cable sheaths, armors, or wiring enclosures associated with circuits operating above extra low voltage must either be bonded to conductive pipes containing flammable agents to prevent dangerous voltage differences, or be separated from those pipes by specified clearances or insulating barriers where bonding is not practicable. Clause 5.6.2.5, Showers and Bathrooms. This clause explains that any conductive reinforcing material within concrete floors or walls of rooms containing showers or baths must be bonded to the earthing system. It explains how equipotential bonding conductors are to be connected and provides guidance for combined outbuildings, continuous reinforcement, and existing installations, with the aim of avoiding potential differences in these locations. Clause 5.6.2.6, Swimming and Spa Pools. This clause introduces the special equipotential bonding requirements for pools and spas. Clause 5.6.2.6.1, Bonding Arrangement. This clause explains that an equipotential bonding conductor must be connected between the conductive pool structure, specified items of electrical equipment, conductive fixtures and fittings, and the earthing conductors of circuits supplying the pool or spa. It also explains that the resistance of this bonding conductor between these items must not exceed 0.5 ohms. Clause 5.6.2.6.2, Conductive pool structures. This clause explains that where the pool structure is conductive, extraneous conductive parts including reinforcing metal must be bonded to a pool equipotential bonding connection point, which is also bonded to the earthing conductors of the circuit supplying the pool or spar. It explains situations where additional bonding is not required when electrical continuity is already ensured. Clause 5.6.2.6.3, Pool equipotential bonding conductor connection point. This clause explains that a dedicated bonding connection point may be used for pool bonding. It must be accessible after construction, clearly identified, correctly designed, protected against mechanical damage, and protected against corrosion. Clause 5.6.2.6.4, Electrical equipment. This clause explains that exposed conductive parts of electrical equipment in pool zones, and equipment in contact with pool water, must be equipotentially bonded. It also notes situations where separation or insulation means bonding is not required. Clause 5.6.2.6.5, Conductive fixtures and fittings. This clause explains that fixed conductive items within arm's reach of the pool edge, such as ladders, diving boards, fences, pipework, and reinforcing metal, must be included in the equipotential bonding system where required, to prevent dangerous voltage differences. Clause 5.6.2.7, Telephone and telecommunication earthing systems. This clause explains that telephone and telecommunication earthing systems may be connected in common with the electrical installation earthing system. The purpose of doing this is to reduce the risk of dangerous voltage differences appearing between the two systems during faults or abnormal conditions. If the telephone or telecommunication earthing system is directly connected to the electrical installation earthing system, it must be connected either to the electrical installation earthing system at a dedicated enclosed terminal provided for this purpose, or directly to the earth electrode using an independent connecting device that is clearly identified. Where an enclosed terminal is used, several conditions apply. The terminal must be connected to the main earthing conductor of the electrical installation via protective earthing conductor in accordance with Clause 5.5.2. The terminal must not be installed inside a switchboard. It must be installed in a convenient and readily accessible position, and the minimum cross-sectional area of the protective earthing conductor used for this connection must be 6 square millimeters. This clause also notes that in Australia, installation requirements are covered by ASNZS 5009, while in New Zealand, guidance is given in the TCF Premises Wiring Code of Practice. Further detail on bonding arrangements is provided in Appendix F. Clause 5.6.3, Bonding conductors. This clause introduces the requirements for equipotential bonding conductors. Clause 5.6.3.1, General. This clause explains that the selection and installation of equipotential bonding conductors must follow the same general principles as protective earthing conductors in Clause 5.5. The key focus is ensuring safety by maintaining effective electrical bonding. An exception is noted that the size of an equipotential bonding conductor is determined in accordance with Clause 5.6.3.2. Clause 5.6.3.2, Size. This clause explains that the size of equipotential bonding conductors must be selected based on the specific bonding application and the detailed requirements set out in this clause. For conductive piping, cable sheaths and wiring enclosures, the equipotential bonding conductor required under clauses 5.6.2.2 to 5.6.2.4 must have a cross-sectional area of not less than 4 square millimeters. For showers, bathrooms, swimming pools and spa pools, the equipotential bonding conductors required under clauses 5.6.2.5 and 5.6.2.6 must also have a cross-sectional area of not less than 4 square millimeters. For telephone and telecommunication earthing systems connected in accordance with Clause 5.6.2.7, the equipotential bonding conductor must have a cross-sectional area of not less than 6 square millimeters. This clause also explains that in some swimming or spa pool situations, the size of the equipotential bonding conductor may be determined as for an earthing conductor, where the bonding conductor is incorporated within a multi-core flexible cord supplying equipment that must be removed for maintenance. Clause 5.7, Earth fault loop impedance. This clause introduces earth fault loop impedance as a key factor in ensuring automatic disconnection of supply. Clause 5.7.1, General. This clause explains that effective fault protection by automatic disconnection of supply works by disconnecting the supply to the faulty part of the installation in a way that limits touch voltage to safe values during an insulation fault. Automatic disconnection depends on both the characteristics of the circuit protective device and the impedance of the earthing system. If the touch potential exceeds 50 volts AC or 120 volts ripple-free DC, the protective device must disconnect the supply within the required time. Clause 5.7.4, Impedance. This clause explains the condition that must be met to ensure automatic disconnection of supply. The requirement is expressed by the relationship ZS times IA is less than or equal to UO. Now let's explain what this means in simple spoken terms. ZS is the impedance of the earth fault loop. This includes the impedance of the source, the active conductor from the source to the point of fault, and the return path from the point of fault back to the source through the protective earthing conductor and the neutral. IA is the current needed to cause the automatic operation of the protective device within the required disconnection time. In other words, it is the fault current that will make the fuse blow or the circuit breaker trip fast enough. UO is the nominal AC voltage to earth, which in a standard New Zealand installation is 230 volts. What this formula is telling us is simple. The total impedance of the fault loop must be low enough so that, when a fault occurs, enough current flows to operate the protective device quickly. If the impedance is too high, the fault current will be too small, the device will not trip in time, and dangerous touch voltages may remain on exposed conductive parts. So, to comply with this clause, the measured or calculated earth fault loop impedance must always be low enough to satisfy this relationship. The notes explain that additional requirements apply in patient areas of hospitals and similar locations, that the return path includes both protective earthing and neutral conductors, and that Appendix B provides guidance on calculation methods and measurement techniques. Clause 5.8, Other earthing arrangements. This clause explains that where fault protection is provided by electrical separation, protective earthing conductors and equipotential bonding conductors must be arranged in accordance with Clause 7.4. It also explains that some earthing systems should be independent systems. However, if they are connected to the electrical installation earthing system, they must not reduce the integrity of the electrical installation protective earthing system. Examples of these independent systems include lightning protection systems, static electricity protection systems, radio frequency interference screened installations, information technology installations, explosion protection systems, and cathodic protection systems. The clause finishes by noting that requirements for protective earthing and bonding for these systems may be found in other standards. That brings us to the end of Section 5, Earthing Arrangements and Earthing Conductors. In this section, we've covered how earthing systems are constructed, how bonding reduces dangerous voltage differences, and how earth fault loop impedance ensures fast and safe disconnection of supply. These requirements form the foundation of electrical safety in New Zealand installations and are essential knowledge for everyday electrical work and for EWRB examinations. Always remember, correct earthing saves lives and protects property. In the next section, we'll move on to the next set of requirements in the standard. Hi everyone, my name is Aria, and I work alongside Whit Roy as an electrical tutor. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 3000, 2018. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for EWRB exam. What this audiobook does is take the key ideas from the standard and explain them in simple, spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real installations. So think of this as a learning companion, not a replacement for the actual standard. Alright, let's get started. Hello everyone, in this section we are moving into section 6, which covers damp situations. In this part of the standard, we look at electrical installations in places where water, moisture, or high humidity can increase the risk of electric shock. These locations include areas like bathrooms, pools, fountains, saunas, refrigeration rooms, and places where regular hosing down or sanitizing is carried out. Because moisture changes how electricity behaves and lowers the body's resistance, the rules in this section focus on extra protection, correct equipment selection, and clear limits on what is allowed. Everything in this section is about reducing risk and keeping people safe in wet and damp environments. Clause 6.1 General. This clause introduces the overall idea that damp locations need special attention because moisture can change how electricity behaves and can increase danger if equipment is not suitable. Clause 6.1.1 Application. This clause explains that the rules in this section apply wherever water or high humidity can affect electrical equipment. It makes clear that these requirements exist to deal specifically with damp conditions, where normal dry area assumptions are no longer safe. Clause 6.1.2 Selection and Installation. This clause explains that, on top of the rules already given in sections 2 to 5 of this standard, electrical equipment used in damp situations must be chosen and installed to do two main things. First, it must give stronger protection against electric shock in places where water or high humidity increases the risk, because moisture lowers body resistance and makes contact with earth potential more likely. Second, it must provide enough protection to prevent damage that could reasonably happen because of water or high humidity. The clause also explains that the specific rules for particular damp situations are added to, and do not replace or change, the general rules in the other sections. If this section does not give a specific requirement, then the normal requirements from the other sections still apply. This section applies to damp situations such as baths, showers and other fixed water containers, swimming pools, paddling pools and spa pools or tubs, fountains and water features, saunas, refrigeration rooms, and areas used for sanitizing or general hosing down operations. Clause 6.2 Baths, showers and other fixed water containers. This clause explains that special electrical safety rules apply where baths, showers, or other fixed water containers are installed, because the presence of water increases the chance of electric shock by reducing body resistance and increasing contact with earthed parts. Clause 6.2.1 Scope. This clause explains that the requirements apply to electrical installations in locations that contain a bath, a shower or other fixed water containers, including the surrounding zones. The increased risk comes from people being in contact with water and also in contact with conductive parts connected to the general mass of earth. It explains that fixed water containers are those designed to normally hold water for use, and it excludes containers that are accidental or not intended to hold water as part of normal use. It also explains that a full chemical safety washdown facility, such as a deluge shower where a person can stand, is treated as a shower, and that a self-contained eye wash with a fixed or flexible hose is treated as a fixed water container. The clause explains that all requirements are based on classifying zones around the water container, and that physical barriers such as screens, doors, curtains, or fixed partitions may be used to limit how far spray can reach, provided they give effective protection. It also explains that ceilings, walls, doors, windows, and floors can limit the size of the zones. Because of the nature of these locations, some normal methods of protection against electric shock are not allowed, and reference is made to the clause dealing with prohibited measures. Notes explain that special requirements may apply for medical treatment baths, that equipment behind a fixed panel with at least IPX4 protection and requiring a tool for access is not considered to be in a classified zone, and that equipment recessed into a ceiling so that live parts are above the ceiling surface is considered to be outside the zones below. Clause 6.2.2 Classification of zones. This clause explains that different zones are defined around baths, showers, and other fixed water containers to control what electrical equipment is allowed and what level of protection is required. Clause 6.2.2.1 Baths and showers. This clause explains that 4 zones, called Zones 0, 1, 2, and 3, are defined for baths and showers. Zone 0 is the inside of the bath or the shower base. Zone 1 for a bath includes Zone 0, the vertical projection of the internal rim of the bath above Zone 0, and where a shower is present, the vertical plane with a radius of 1.2 meters from the fixed plumbing connection. In New Zealand, Zone 1 is limited vertically by the floor and a horizontal plane 2.25 meters above the floor, or by the height of the fixed plumbing connection if that is higher. Zone 1 for a shower includes Zone 0 and extends horizontally from the fixed plumbing connection. Where the connection is on a wall, the zone extends 1.2 meters, unless a barrier of sufficient height reduces this distance. Where the connection is on the ceiling, the horizontal distance is defined differently, and in New Zealand the radius is 1.2 meters, unless reduced by a suitable barrier. Zone 2 extends beyond Zone 1 by 0.6 meters horizontally and up to 2.25 meters above the floor. Zone 3 extends beyond Zone 2 by a further 2.4 meters horizontally and, in New Zealand, up to 2.25 meters above the floor. This clause explains how these zones are used to manage electrical safety around baths and showers. Clause 6.2.2.2 Other fixed water containers. This clause explains that only Zones 0 and 2 are defined for fixed water containers other than baths and showers. Zone 0 is the inside of the container. For small containers not exceeding 40 liters with fixed water outlets, Zone 2 extends a short distance from the rim and slightly above the container. For larger containers or where water outlets are supplied through flexible hoses, Zone 2 extends further from the rim and higher above the container. Notes explain that there is no Zone 1 or Zone 3 for these containers and give an example of a flexible hose outlet. Clause 6.2.3 Protection against electric shock, prohibited measures. This clause explains that certain methods of protection against electric shock are not allowed in these locations. Specifically, protection by obstacles and protection by placing out of reach are prohibited. Clause 6.2.4 Selection and installation of electrical equipment. This clause explains that electrical equipment installed in classified zones must meet minimum protection requirements and follow specific installation rules. Clause 6.2.4.1 Degree of protection required. This clause explains that equipment installed in Zone 0 must have at least IPX7 protection, equipment in Zones 1 and 2 must have at least IPX4 protection, and equipment in Zone 3 has no specific IP requirement stated. Clause 6.2.4.2 Socket outlets. This clause explains that socket outlets must not be installed within 0.3 meters of the floor in bathrooms or similar locations where the floor can become wet. It explains that socket outlets are not allowed in Zone 0 or Zone 1. In Zone 2, socket outlets are only allowed if they are part of a compliant shaver supply unit or are protected by an RCD with a rated residual current not exceeding 30 mA and enclosed in a cupboard that maintains protection during normal use. In Zone 3, socket outlets must be protected by an RCD, or supplied by a separated circuit, or supplied as an SELV or PELV system, with additional limits on how close they can be to the floor. Clause 6.2.4.3 Switches and other accessories. This clause explains that switches and similar accessories must not be installed within 0.3 meters of the floor where the floor is likely to become wet. It explains that switches and accessories are not allowed in Zone 0, and that in Zones 1 and 2 only equipment with the required degree of protection is permitted. Clause 6.2.4.4 Luminaires. This clause explains that luminaires in Zone 0 must have the required degree of protection, be specifically designed for use in baths or showers, be supplied at extra low voltage, and be supplied from a source outside Zone 0 as an SELV or PELV system. In Zones 1, 2, and 3, luminaires must have at least the required degree of protection. Exceptions are explained for certain Class 2 luminaires and for luminaires supplied as SELV or PELV from outside Zone 2. Clause 6.2.4.5 Other electrical equipment. This clause explains that appliances and other electrical equipment installed in Zone 0 must be specifically designed for use in a bath, shower, or water container and must have the required degree of protection. Equipment installed in Zones 1, 2, and 3 must meet at least the protection requirements for the relevant zone. It also explains that heating cable systems embedded in the floor and protected in accordance with the relevant clause may be installed. Clause 6.2.4.6 Switchboards. This clause explains that switchboards must not be located within any classified zone. Clause 6.2.4.7 Electricity generation systems. This clause explains that electricity generation systems, including generator sets, standalone systems, grid-connected inverters, and battery systems, must not be installed within any classified zone. Clause 6.3 Swimming pools, paddling pools and spa pools or tubs. This clause explains that special electrical safety requirements apply to locations containing swimming pools, paddling or wading pools, and spa pools or tubs, including the surrounding zones. The risk of electric shock is higher in these locations because water reduces body resistance and increases the chance of the body coming into contact with water and conductive parts connected to the general mass of Earth. Clause 6.3.1 Scope. This clause explains that the requirements apply to electrical installations in areas with swimming pools, paddling pools, and spa pools or tubs, together with their surrounding zones. It explains that special requirements may be needed for medical pools or large commercial pools. The rules are based on classifying zones around the water container. It explains that ceilings, walls, doors, floors, barriers, and fixed partitions, such as a solid fence of sufficient height, may be used to limit how far the zones extend if they provide effective protection against splashing or spraying water. It also explains that these requirements apply to pools in natural waters, lakes, gravel pits, coastal areas, and similar locations where people swim or paddle. Because of the nature of these locations, some normal methods of protection against electric shock are not allowed, and reference is made to the clause dealing with prohibited measures. Clause 6.3.2 Classification of zones. This clause explains that zones are defined around pools and spas to control what electrical equipment may be installed and what level of protection is required. Clause 6.3.2.1 Swimming pools and paddling pools. This clause explains that 3 zones, called Zones 0, 1, and 2, are defined for swimming pools and paddling pools. Zone 0 is the interior of the pool. Zone 1 includes Zone 0 and extends outward from the internal rim of the pool, includes the floor or surface where people stand, and extends up to a horizontal plane 2.5 meters above that surface. Where diving boards, springboards, starting blocks, or slides are provided, Zone 1 also extends around these items and up to a height above the highest surface expected to be used by people. Zone 2 extends beyond Zone 1 by a further horizontal distance and also includes the floor or surface expected to be occupied, up to 2.5 meters above that surface. Clause 6.3.2.2 Spa pools or tubs, general. This clause explains general requirements for spa pools and tubs, including how their water capacity affects the way zones are defined. Clause 6.3.2.2 Water capacity exceeding 5,000 liters. This clause explains that spa pools or tubs with a water capacity exceeding 5,000 liters are classified using 3 zones, Zones 0, 1, and 2, in the same way as swimming pools and paddling pools. Clause 6.3.2.3 Water capacity not exceeding 5,000 liters. This clause explains that spa pools and tubs with a water capacity greater than 680 liters and up to 5,000 liters are classified using Zones 0 and 1 only. Zone 0 is the interior of the water container. Zone 1 extends out from the internal rim by a defined horizontal distance and includes the floor or surface where people stand, up to a horizontal plane 2.5 meters above that surface. Clause 6.3.3 Protection against electric shock. This clause explains that additional protective measures are required in pool and spa locations to control electric shock risk. Clause 6.3.3.1 Prohibited measures. This clause explains that protection by obstacles and protection by placing out of reach are not permitted as methods of protection against electric shock in these locations. Clause 6.3.3.2, Supplementary Equipotential Bonding. This clause explains that where electrical equipment in a classified zone is required to be earth, all exposed conductive parts and extraneous conductive parts in zones 0, 1, and 2 must be connected together by supplementary equipotential bonding conductors and connected to the protective earthing conductor of the equipment. Clause 6.3.3.3, Voltage Gradients. This clause explains that where electrical equipment is in contact with pool or spa water, insulation failure can create dangerous voltage differences across or through the water. Even very low voltages can be hazardous to people immersed in water. The clause explains that protection must include the use of RCDs with a rated residual current not exceeding 30 mA for circuits supplying Class 1 equipment, or electrical separation provided in accordance with the relevant clauses. Clause 6.3.4, Selection and Installation of Electrical Equipment. This clause explains that electrical equipment installed in classified zones must meet specific protection and installation requirements. Clause 6.3.4.1, Degree of Protection Required. This clause explains that equipment installed in Zone 0 must have at least IPX8 protection, equipment in Zone 1 must have at least IPX5 protection, and equipment in Zone 2 must have at least IPX4 protection. Clause 6.3.4.2, Wiring Systems. This clause explains that wiring systems must be installed to prevent moisture entering connections and to prevent water siphoning through wiring enclosures or cables. It explains that bare aerial conductors are not allowed over zones 0, 1, or 2, and that other aerial cables must comply with the relevant clause. Clause 6.3.4.3, Socket Outlets. This clause explains that socket outlets must not be installed within 0.3 meters of any floor or surface that is likely to become wet. Socket outlets are not allowed in Zone 0. Socket outlets are not normally allowed in Zone 1 unless they are necessary for pool equipment, and in that case they must meet specific location and protection requirements, including minimum heights and distances from the water container. Clause 6.3.4.4, Switches and Other Accessories. This clause explains that switches and other accessories are not permitted in Zone 0. In Zones 1 and 2, switches and accessories may be installed only if they have the required degree of protection. Clause 6.3.4.5, Luminaires, Appliances and Other Electrical Equipment. This clause explains general requirements for luminaires, appliances, and other electrical equipment installed in classified zones. Clause 6.3.4.5.1, General. This clause explains that luminaires, appliances, and other electrical equipment installed in classified zones must meet the specific requirements set out in this section, excluding socket outlets and switches which are covered separately. Equipment installed in Zone 0 must be specifically designed for use in a swimming or spa pool, have the required degree of protection, and comply with the relevant general installation requirements. Clause 6.3.4.5.2, Zone 0 Luminaires. This clause explains that luminaires installed in Zone 0 must comply with the relevant ASNZS standards, be supplied by SELV at extra low voltage, and must not be provided with a protective earthing conductor. Clause 6.3.4.5.3, Zone 0 Appliances and Other Electrical Equipment. This clause explains that appliances and other electrical equipment in Zone 0 must be supplied from an individual source located outside Zone 0, operate at extra low voltage, and be supplied as an SELV or PELV system. Clause 6.3.4.5.4, Zone 1 Luminaires, Appliances and Other Electrical Equipment. This clause explains that equipment in Zone 1 must either be supplied as SELV or PELV, be of Class 2 construction and fixed in position, or be of Class 1 construction supplied from a circuit protected by an RCD with a rated residual current not exceeding 30 mA. Clause 6.3.4.5.5, Zone 2 Luminaires, Appliances and Other Electrical Equipment. This clause explains that equipment in Zone 2 must either be supplied as SELV or PELV, be supplied as a separated circuit, be of Class 2 construction, or be of Class 1 construction supplied from a circuit protected by an RCD with a rated residual current not exceeding 30 mA. Clause 6.3.4.6 Switchboards. This clause explains that switchboards must not be installed within any classified zone. Clause 6.3.4.7 Electricity generation systems. This clause explains that electricity generation systems, including generators, standalone systems, grid-connected inverters, and battery systems, must not be installed within any classified zone. Clause 6.3.4.8 Electricity distributors' electrical equipment. This clause explains that pools and spas must not be located in areas containing electrical equipment owned by the electricity distributor if that equipment would fall within a classified zone. Clause 6.4 Fountains and water features. This clause explains that special electrical safety requirements apply to electrical installations where fountains and water features are installed, including the surrounding zones. The risk of electric shock is higher because water reduces body resistance and increases the chance of contact with water and conductive parts connected to the general mass of Earth. The requirements are based on classifying zones around the water container and are intended to protect electrical equipment from the corrosive effects of water treatment chemicals and to manage the higher risk where people may be partly immersed in water. Clause 6.4.1 Scope. This clause explains that the requirements apply to electrical installations associated with fountains and water features and their surrounding zones. It explains that these requirements may not apply where the water depth does not exceed 0.3 meters, or where suitable measures are used to restrict people from entering the water. It also explains that ceilings, walls, doors, floors, barriers, and fixed partitions can be used to limit the extent of zones if they provide effective protection against spraying or splashing water. Because of the nature of these locations, certain normal methods of protection against electric shock are not allowed, and reference is made to the clause covering prohibited measures. Clause 6.4.2 Classification of zones. This clause explains that two zones, Zone 0 and Zone 1, are defined for fountains and water features. Clause 6.4.2.1 Zones. This clause explains that Zone 0 is the interior of the water container, including recesses in walls or floors and the interior of water jets or waterfalls. Zone 1 extends outward from the internal rim of the water container, includes the floor or surface expected to be occupied by people, and extends up to a horizontal plane 2.5 meters above that surface. Where sculptures or decorative water containers are present, Zone 1 also extends around them and up to a defined height above them. Clause 6.4.3 Protection against electric shock. This clause explains how electric shock protection must be achieved in fountain and water feature locations. Clause 6.4.3.1 Use of SELV. This clause explains that where SELV is used, basic protection must still be provided in accordance with the relevant clause, regardless of the nominal voltage. Clause 6.4.3.2 Application of protective measures against electric shock. This clause explains that electrical equipment must either be earthed and protected by an RCD with a rated residual current not exceeding 30 mA, or supplied at extra low or low voltage through an isolating transformer that complies with the relevant ASNZS standard and is not earthed, or supplied by other suitable measures that take account of the equipment construction, installation method, and physical location. Clause 6.4.3.2.2 Prohibited measures. This clause explains that protection by obstacles and protection by placing out of reach are not permitted as methods of protection against electric shock in these locations. Clause 6.4.4 Selection and installation of electrical equipment. This clause explains that electrical equipment installed in classified zones must meet specific protection and installation requirements. Clause 6.4.4.1 Degree of protection required. This clause explains that equipment installed in Zone 0 must have at least IPX8 protection, and equipment installed in Zone 1 must have at least IPX5 protection. Clause 6.4.4.2 Wiring systems. This clause explains that wiring systems for fountains and water features must use suitable insulated and sheathed copper cables or flexible cords appropriate for immersion in the type of water used. Where wiring is exposed to mechanical damage, it must be enclosed, and wiring must be installed to prevent moisture entering connections and to prevent water siphoning through enclosures or cables. Clause 6.4.4.3 Socket outlets. This clause explains that socket outlets are not permitted in Zone 0 or Zone 1. Clause 6.4.4.4 Switches and other accessories. This clause explains that switches and accessories are not permitted in Zone 0. In Zone 1, switches and accessories may only be installed if they have the required degree of protection. Clause 6.4.4.5 Luminaires, appliances and other electrical equipment. This clause explains the requirements for luminaires, appliances, and other electrical equipment installed in classified zones. Clause 6.4.4.5.1 General. This clause explains that equipment installed in Zone 0 must be specifically designed for use in a fountain or water feature, have the required degree of protection, and comply with the relevant general installation requirements. Clause 6.4.4.5.2 Zone 0 luminaires. This clause explains that luminaires installed in Zone 0 must comply with the relevant ASNZS standards, be supplied by SELV at extra low voltage, and must not have a protective earthing conductor. Clause 6.4.4.5.3 Zone 0 appliances and other electrical equipment. This clause explains that equipment in Zone 0 must be supplied from an individual source located outside Zone 0, operate at extra low voltage, and be supplied as an SELV or PELV system. Clause 6.4.4.5.4 Zone 1 luminaires, appliances and other electrical equipment. This clause explains that equipment installed in Zone 1 must either be supplied as SELV or PELV, be of Class 2 construction and fixed in position, or be of Class 1 construction fixed in position and supplied from a circuit protected by an RCD with a rated residual current not exceeding 30 mA. Clause 6.4.4.6 Switchboards. This clause explains that switchboards must not be installed within any classified zone. Clause 6.4.4.7 Electricity generation systems. This clause explains that electricity generation systems must not be installed within any classified zone. Clause 6.4.4.8 Electricity distributors' electrical equipment. This clause explains that fountains and water features must not be located where electrical equipment owned by the electricity distributor would fall within a classified zone. Clause 6.5 Saunas. This clause explains that special electrical safety requirements apply to electrical installations in rooms or enclosures containing heating equipment used only for sauna heating. The requirements are based on classifying zones around the sauna heater. Because of the nature of these locations, certain normal methods of protection against electric shock are not allowed. Clause 6.5.1 Scope. This clause explains that the requirements apply to electrical installations associated with sauna heating equipment. Clause 6.5.2 Classification of zones. This clause explains that 3 zones, Zone 1, Zone 2, and Zone 3, are defined for sauna rooms. Clause 6.5.2.1 Zones. This clause explains that Zone 1 is the area immediately around the sauna heater, limited horizontally from the external edge of the heater and vertically between the floor and the cold side of the ceiling insulation. Zone 2 extends beyond Zone 1 to the cold side of the wall insulation and up to 1 meter above the floor. Zone 3 extends above Zone 2 and includes the area up to the cold side of the ceiling insulation. It also explains that Zone 3 is directly above Zone 2. Clause 6.5.3 Protection against electric shock. This clause explains how electric shock protection must be achieved in sauna locations. Clause 6.5.3.1 Use of SELV. This clause explains that where SELV is used, basic protection must still be provided in accordance with the relevant clause, regardless of the nominal voltage. Clause 6.5.3.2 Prohibited measures. This clause explains that protection by obstacles and protection by placing out of reach are not permitted. Clause 6.5.3.3, Additional protection by a CD. This clause explains that all equipment within the sauna room, except the sauna heater itself, must be protected by an ACD with a rated residual current not exceeding 30 mA. Clause 6.5.4, Selection and installation of electrical equipment. This clause explains the requirements for selecting and installing electrical equipment in sauna rooms. Clause 6.5.4.1, Degree of protection required. This clause explains that electrical equipment installed within the sauna room must have a minimum degree of protection of at least IPX4B or IP24. Clause 6.5.4.2, Requirements in classified zones. This clause explains that only equipment belonging to the sauna heater may be installed in Zone 1, and that there are no special heat resistance requirements for equipment installed in Zone 2. Clause 6.5.4.3, Wiring systems. This clause explains that wiring systems should be installed outside the zones on the cold side of the thermal insulation. Where wiring is installed on the warm side, it must be heat resistant and metallic sheaths or conduits must not be accessible during normal use. Clause 6.5.4.4, Socket outlets, switches and other accessories. This clause explains that socket outlets, switches, and accessories must not be installed within the sauna room or enclosure, except for switches and accessories that form part of the sauna heater. Clause 6.5.4.5, Sauna heating appliances. This clause explains that sauna heating appliances must be installed in accordance with the manufacturer's instructions. Clause 6.5.4.6, Switchboards. This clause explains that switchboards must not be installed within any classified zone. Clause 6.6, Refrigeration rooms. This clause explains that special electrical safety requirements apply to all areas within refrigeration rooms, including freezers and cold rooms. Because of low temperatures, condensation, and moisture, some normal methods of protection against electric shock are not permitted. Clause 6.6.1, Scope. This clause explains that the requirements apply to the entire area inside refrigeration rooms. It also explains that, due to the nature of these locations, certain methods of protection against electric shock are not allowed, and reference is made to the clause covering prohibited measures. Clause 6.6.2, Protection against electric shock. This clause explains how protection against electric shock must be achieved in refrigeration rooms. Clause 6.6.2.1, Use of SELV. This clause explains that where SELV is used, basic protection must still be provided in accordance with the relevant clause, regardless of the nominal voltage. Clause 6.6.2.2, Prohibited measures. This clause explains that protection by means of obstacles and protection by placing out of reach are not permitted as methods of protection against electric shock in refrigeration rooms. Clause 6.6.3, Selection and installation of electrical equipment. This clause explains the requirements for selecting and installing electrical equipment within refrigeration rooms. Clause 6.6.3.1, Degree of protection required. This clause explains that electrical equipment installed in a refrigeration room must have a minimum degree of protection of at least IPX4B or IP24. It also notes that additional requirements apply where areas are subject to sanitization or hosing down operations. Clause 6.6.3.2, Wiring systems. This clause explains the requirements for wiring systems used to supply, control, and protect electrical equipment in refrigeration rooms. Clause 6.6.3.2.1, General. This clause explains that wiring systems must not be affected by the low operating temperatures of the room and must not create pockets or channels where moisture can collect or travel into electrical equipment. It also explains that wiring systems not associated with the refrigeration room equipment must not pass through or be installed in these rooms. Clause 6.6.3.2.2, Types permitted. This clause explains that permitted wiring systems include unenclosed sheathed cables such as served MIMS cables, insulated cables enclosed in wiring enclosures with adequate drainage, and other wiring systems that are not inferior to these. It also explains that PVC insulated cables may not be suitable where cables are subject to bending, flexing, or vibration at very low temperatures. Clause 6.6.3.2.3, Sealing. This clause explains that wiring enclosures must be sealed with a compound that does not set hard at points where they pass from refrigerated to non-refrigerated spaces, and where cables enter motors, luminaires, switches, or other electrical equipment. Clause 6.6.3.3, Socket outlets, switches and other accessories. This clause explains that socket outlets, switches, and accessories must be designed so moisture cannot be retained within their enclosures. This requirement may be met by using permanently sealed accessories or accessories with the required degree of protection. Clause 6.6.3.4, Luminaires, lamp holders and other equipment. This clause explains the requirements for luminaires, lamp holders, and similar equipment in refrigeration rooms. Clause 6.6.3.4.1, Luminaires. This clause explains that luminaires must be permanently sealed to prevent the entry of liquid or vapor, or be designed so moisture cannot enter live parts and cannot be retained in or on the fitting. Clause 6.6.3.4.2, Lamp holders. This clause explains that lamp holders must be of the all-insulated type or another suitable type that prevents any external metal parts from becoming live. It also explains that lamp holders on flexible pendants must not be suspended within 2.5 meters of the floor. Clause 6.6.3.5, Fixed appliances and motors. This clause explains that fixed appliances and motors must be designed and constructed to suit the specific location and conditions found in refrigeration rooms. Clause 6.6.3.6, Heating elements and door seals. This clause explains that heating elements installed in refrigeration room door seals must be provided with additional protection by an RCD with a fixed rated residual current not exceeding 30 mA. Clause 6.6.3.7, Switchboards. This clause explains that switchboards must not be installed inside refrigeration rooms. Clause 6.7, Sanitization and general hosing down operations. This clause explains that special electrical safety requirements apply to electrical installations in locations where sanitization or general hosing down operations are carried out. Clause 6.7.1, Scope. This clause explains that the requirements apply to electrical installations in areas where sanitization or hosing down occurs. It explains that, because of the nature of these locations, certain methods of protection against electric shock are not permitted. It also explains that these locations can include food production and processing areas, agricultural and horticultural premises, rooms where livestock are kept, areas where feed or food products are handled, greenhouses, hydroponic installations, dairies, meat processing facilities, and car wash bays. Clause 6.7.2, Classification of zone. This clause explains how the classified zone is determined based on the extent of the area likely to be affected by hosing. Clause 6.7.2.1, Zones. This clause explains that where the entire area is sanitized or hosed down, the classified zone includes the whole space between the floor, walls, and ceiling. Where hosing is limited to floors and walls, the classified zone includes areas from the floor up to 2 meters above the floor, all walls in the area, and ceiling areas within 1 meter of the walls. Where hosing is limited to the floor only, the classified zone includes areas from the floor up to 1 meter above the floor. Clause 6.7.3, Protection against electric shock. This clause explains how protection against electric shock must be achieved in sanitization and hosing down locations. Clause 6.7.3.1, Use of SELV. This clause explains that where SELV is used, basic protection must still be provided in accordance with the relevant clause, regardless of the nominal voltage. Clause 6.7.3.2, Prohibited measures. This clause explains that protection by means of obstacles and protection by placing out of reach are not permitted. Clause 6.7.4, Selection and installation of electrical equipment. This clause explains the requirements for selecting and installing electrical equipment in classified zones subject to sanitization or hosing. Clause 6.7.4.1 Degree of protection required. This clause explains that electrical equipment must have at least IPX5 protection where low or medium pressure hosing is used, and at least IPX6 protection where high pressure hosing is used. Clause 6.7.4.2 Electrical equipment. This clause explains that electrical equipment and wiring systems in the classified zone must not be affected by the hosing method. Materials, temperature, or pressure must be protected against moisture accumulation, and must not provide channels or pockets through which moisture can enter electrical equipment. Clause 6.7.4.3 Switchboards. This clause explains that switchboards installed in classified zones subject to sanitization or hosing down operations must have a minimum degree of protection of IPX6. That brings us to the end of Section 6 on damp situations. We have covered how different wet and high moisture locations are classified, why zones are used, and how electrical equipment must be selected and installed to manage the higher risk of electric shock. These rules are especially important in everyday locations where people may be wet, barefoot, or in contact with conductive surfaces. As always, this section gives practical safety guidance, but it should be used alongside the other sections of the standard when designing, installing, or inspecting electrical work. Take your time to understand these requirements, because correct application in damp situations is critical for electrical safety. Hi everyone, my name is Aria, and I work alongside Whit Roy as an electrical tutor. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 3000, 2018. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for EWRB exam. What this audiobook does is take the key ideas from the standard and explain them in simple, spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real installations. So think of this as a learning companion, not a replacement for the actual standard. All right, let's get started. Welcome to Section 7 of ASNZS 3000, Special Electrical Installations. In this section, we move away from standard electrical installations and focus on situations where extra care, additional controls, or special design rules are required. These include safety services, electricity generation systems, electrical separation, extra low voltage systems, high voltage installations, hazardous areas, and other specialized applications. Each part of this section explains how normal installation rules are adjusted or added to, so electrical safety is maintained even in higher risk or unusual environments. Everything in this section builds on the core safety principles of the standard while addressing the specific needs of these special installations. Clause 7.1 General. This clause introduces Section 7 and explains that this part of ASNZS 3000 deals with special electrical installations. It sets the scene by making it clear that this section focuses on installations that have higher risks or special conditions compared with normal electrical work, and that these installations still need to meet the overall safety intent of Part 1 of the standard. Clause 7.1.1 Application. This clause explains that Section 7 sets out the minimum requirements for how electrical equipment is selected and installed when it is used in special electrical installations. The key idea is that these requirements must be met so that the installation still satisfies the general safety principles of Part 1 of ASNZS 3000, even though the installation itself is unusual or has added risks. Clause 7.1.2 Selection and Installation. This clause explains that each type of special electrical installation has its own specific requirements, and these requirements can replace or change the general rules found in other sections of the standard. It also makes clear that if Section 7 does not state a specific requirement for a situation, then the normal requirements from the other sections of ASNZS 3000 still apply. The clause then explains that this section applies to a range of special electrical installations, including electrical systems used for safety services, electricity generation systems, protection methods that use electrical separation, extra low voltage electrical installations, and high voltage electrical installations. It also applies to installations in areas where there may be an explosive hazard, and to electrical installations in particular locations or situations such as construction and demolition sites, electromedical treatment areas, transportable structures and vehicles and the places they are supplied from, marinas and recreational boats, shows and carnivals, cold cathode illumination systems, telecommunication networks, power supplies, cranes and hoists, lifts, generating sets, outdoor sites under heavy conditions, and electric fences. Clause 7.2 Safety Services. This clause introduces the part of ASNZS 3000 that deals specifically with safety services. It explains that these rules apply to electrical installations that must keep working so that people can be protected during emergencies, such as fires or other dangerous situations. Clause 7.2.1 Scope in general. This clause explains that Clause 7.2 sets the overall boundaries for safety services and how they are treated within an electrical installation, focusing on systems that are critical to safe operation when normal conditions are lost. Clause 7.2.1.1 Scope. This clause explains that the requirements of Clause 7.2 apply to building services that are essential for safety. These include systems needed for fire detection, warning and extinguishing, smoke control, evacuation systems, and any electrical systems that protect the safety of people who rely on lifts during emergencies. The key idea is that these systems must remain reliable so they can function when they are most needed. Clause 7.2.1.2 General. This clause explains that the main purpose of these requirements is to make sure the electricity supply to safety equipment is not accidentally disconnected. The intent is that equipment needed during emergency conditions must continue to receive power so it can operate properly when normal building services may be failing. The clause then explains that some equipment does not need to comply with Clause 7.2, including escalators or moving walkways, certain lifts in single private homes installed to the correct lift standard, lifts that are not classed as emergency lifts under building codes, some pumps where failure would not affect fire water supply, deleted text that no longer applies, and smoke alarms in single private homes which are covered elsewhere. The notes explain that other standards give guidance for emergency power in hospitals, clarify how the term safety services has been used in different editions and building codes, and explain that fire resistance level is expressed in minutes and relates to structural adequacy, integrity, and insulation as defined by the relevant building and fire standards. Clause 7.2.2 Supply Systems. This clause explains how power supplies for safety services must be arranged. It states that wiring systems for safety services must be able to keep supplying electricity to equipment even when exposed to fire. It also explains that a power source intended for safety services must not be used for other purposes if doing so would reduce the availability of power for safety services. Where safety services need to operate during emergencies or when the normal supply is lost, it may be necessary to automatically disconnect non-essential equipment so enough capacity is available for safety services. An exception is explained for certain fire detection, alarm and intercom systems that use compliant battery backup supplies. Clause 7.2.2.1 General. This clause reinforces that wiring systems associated with safety services must be selected and installed so that they can maintain supply under fire conditions, and that the integrity of the supply takes priority over normal electrical loads. Clause 7.2.2.2 WS classification is not provided. This clause explains what to do when a relevant standard does not specify a wiring system classification. It states that in these cases, the wiring system must either be able to keep supplying power when exposed to fire or mechanical damage, or be protected so that fire or mechanical damage will not prevent it from supplying the equipment. It explains that this can be achieved by suitable enclosures or by locating the wiring where it will not be exposed to damage. The clause also explains that conductors supplying safety services must be physically separated from other wiring systems by a minimum distance or by suitable barriers, and must also be separated from other safety services. It further explains that conductors for different safety services must not be combined together within the same multi-core cable, and must not be combined with conductors of other wiring systems. Where cabling passes through areas with different protection requirements, the highest level of protection must be applied unless it is not practical to do so. The clause then explains exceptions where fire protection requirements do not apply, such as wiring installed in locations that already provide protection, certain battery-backed emergency systems, and wiring for electric-driven fire pumps that are part of a larger pump arrangement. Clause 7.2.2.2 Wiring Systems. This clause explains that wiring systems supplying safety services, including their supports, must comply with the relevant wiring system standard and the required wiring system classification, depending on what equipment is being supplied and where it is installed. Clause 7.2.2.3 Alternative Supply Systems. This clause explains that alternative supplies may be needed so a building can continue to be used safely when the normal power supply is lost. It explains that the alternative supply must have enough capacity to operate all required safety services and, where needed, to support continued occupation of parts of the building. It also explains that generating sets or other independent power sources must be sized to supply all safety services at the same time, including allowance for motor starting. The clause notes that a separate alternative supply may also be provided for non-safety purposes such as security or protecting business assets. Clause 7.2.2.3.1 Continued Occupation. This clause explains that where an alternative supply is provided to allow people to remain safely in a building, it must be capable of supplying both safety services and the electrical equipment needed for continued occupation during a loss of normal supply. Clause 7.2.2.3.2 Fire Management System. This clause explains that when a fire management system is used to control safety services, it must be connected to the alternative supply. The alternative supply must have enough capacity to operate all the required safety services in fire mode, including allowances for starting motors or staged operation of equipment. Clause 7.2.3 Main Switchboard and Switchgear. This clause explains that special arrangements are required for switchboards and switchgear supplying safety services so that faults in the general installation do not affect critical safety equipment. Clause 7.2.3.1 General. This clause explains that each safety service must be controlled by a main switch that is separate from the switches used for the rest of the installation and from switches used for other safety services. It also explains that main switchboards must be installed in accordance with the relevant installation and building code requirements. Clause 7.2.3.2 Switchgear. This clause explains that switchboards supplying safety services must be constructed so the safety services switchgear is separated from general switchgear by metal partitions. The purpose is to reduce the chance that a fault in the general installation will spread to the safety services. It also explains that non-metallic cases do not meet this requirement. Clause 7.2.3.3 Cables in the same enclosure. This clause explains that conductors for safety services must not be enclosed together with conductors for other safety services or other wiring systems. It then explains how separation can be achieved using divided ducts, compliant wiring systems, or physical separation within switchboards so that effective segregation is maintained. Clause 7.2.3.4 Arrangement. This clause explains that where a supply isolating device is installed, it must be capable of breaking load, such as a load break switch or circuit breaker. It also explains that discrimination must be achieved between protective devices if a circuit breaker is used. The clause notes that additional requirements may apply, including the ability to lock the device on and labeling to restrict operation to authorized personnel only. Clause 7.2.3.5 Discrimination Selectivity of Circuit Protective Devices. This clause explains that protective devices must be selected so that a fault on one safety service does not cause loss of supply to other safety services, and that a fault in the general electrical installation must not interrupt power to safety services. It also explains that fault current limiting devices used to protect safety services must not be used to protect general installation circuits. Finally, it explains that discrimination must be arranged between outgoing circuit protection and upstream protective devices so faults are cleared in the correct order. Clause 7.2.4 Main switches. This clause explains the requirements for main switches used to control safety services. The key idea is that safety services must have their own dedicated control so that they are not affected by faults or switching in the general electrical installation. Clause 7.2.4.1 General. This clause explains that every safety service must be controlled by a main switch that is separate from main switches used for any part of the general electrical installation and also separate from main switches used for other safety services. The purpose is to make sure that a fault on one safety service does not cause loss of supply to other safety services, and that a fault in the general electrical installation does not interrupt power to safety services. It explains that there is no limit on how many main switches may be installed to control safety services if needed. It also explains that an automatic transfer switch may be used as a main switch, provided it meets the requirements of Clause 2.3.3. The clause further explains that fault current limiting devices used to protect safety services must not be used to protect any part of the general electrical installation. Clause 7.2.4.2 Arrangement of main switches. This clause explains how main switches for safety services must be arranged. It states that they must be connected on the supply side of all general electrical installation main switches, must not be subject to the control of any general electrical installation main switch, and must control only electrical equipment that is regarded as safety services. The clause then explains that this requirement does not need to apply to certain situations, including high-voltage switches supplying low-voltage switchboards that are not regarded as general installation main switches, low-voltage switches that can only be operated by authorized persons and are clearly marked, safety services installed in individual or combined outbuildings or fire-separated portions of a building, and certain automatic fire detection, alarm, sound and intercom systems provided they meet the stated supply, marking and secondary power source requirements. Clause 7.2.4.3 Mechanical protection. This clause explains that switches and control equipment forming part of a safety service installation must be adequately protected if their location or conditions of use mean they could be subject to mechanical damage. The intent is to make sure the switch remains operable during an emergency. Clause 7.2.4.4 Identification. This clause explains that all switches operating in the supply circuit to safety services must be clearly identified so it is obvious which safety service they control. It explains that main switches for safety services must be identified as a main switch, must clearly indicate the safety service equipment they control using uppercase lettering, must be marked with the words "in the event of fire do not switch off" in uppercase, and must also be identified by contrasting color or another suitable method so they can be quickly recognized. Clause 7.2.4.5 Electrical installations and outbuildings. This clause explains that where a switch for safety services is installed on a switchboard in an outbuilding, that switch is regarded as a main switch for the purposes of this clause. It also explains that a safety service main switch installed in an outbuilding must be clearly identified in accordance with Clause 7.2.4.4. The clause further explains that any switch located remote from an outbuilding, or operating in the supply circuit to a safety service main switch installed in the outbuilding, must also be clearly identified with the required markings. Clause 7.2.4.6 Fire-separated portions of a building. This clause explains that where switches controlling safety services are installed in a fire-separated portion of a building and provided on the switchboard within that fire-separated portion, they are regarded as main switches and must be arranged in accordance with Clause 7.2.4. It explains that parts of a structure separated by a fire resistance level of at least 120/120/120 minutes may be treated as a separate building for this purpose. The clause also explains that any switch controlling safety services in such a fire-separated portion must be separated from switches used to control the general electrical installation and other safety services. Clause 7.2.5 Fire pumps and fire pump control equipment. This clause introduces the requirements for electrical installations supplying fire pumps and their control equipment. The intent is to ensure that these systems remain reliable during emergency conditions. Clause 7.2.5.1 General. This clause explains that fire pumps and fire pump control equipment include items such as fire hydrant booster pumps, pumps for automatic sprinkler or spray or deluge systems, pumps for fire hose reels where they are the sole means of fire protection, fire pump control equipment and wiring systems, and fire pump rooms. It also explains that there may be other fire and smoke control equipment not listed. An exception is explained, stating that the requirements of Clause 7.2 do not apply to electrical equipment where failure would not affect the operation of safety services. Clause 7.2.5.2 Wiring system supplying fire pumps and fire pump control equipment. This clause explains that wiring systems supplying fire pumps and their control equipment must comply with ASNZS 3013 and have the required wiring system classification specified by the relevant installation standard. It explains that where no wiring system classification is specified, the wiring must be capable of maintaining supply when exposed to fire or mechanical damage, or be protected so that supply can be maintained. It also explains exceptions where these protection requirements do not apply, such as wiring installed in locations that already provide protection, or wiring for electric-driven fire pumps that are part of a pump set with a standby fuel-driven pump. Clause 7.2.5.2.2 Segregation of cables. This clause explains that conductors supplying fire pumps and fire pump control equipment must not be enclosed with conductors of different safety services or with conductors of any other wiring system. It explains how effective segregation can be achieved using separate channels, compliant wiring systems, physical separation within switchboards, and by ensuring that conductors of different safety services are not combined within the same multi-core cable. Clause 7.2.5.3 Switchgear for fire pumps and fire pump control equipment. This clause explains that where emergency equipment is required by building codes, switchboards supplying that equipment must be constructed so that the emergency equipment switchgear is separated from other switchgear by metal partitions. The intent is to reduce the risk of a fault spreading from general switchgear to emergency switchgear. Clause 7.2.5.4 Interposing switches for fire pumps and fire pump control equipment. This clause explains that no switch is permitted to be installed between a main switch and downstream switchboards that supply fire pumps and fire pump control equipment. The purpose is to avoid any unintended interruption of supply. Clause 7.2.5.5 Pump rooms for fire pumps and fire pump control equipment. This clause explains that in rooms used mainly to house fire pumps, lighting equipment and socket outlets may be supplied as a final subcircuit from the pump supply, provided that the circuit is protected against overcurrent, protected by an RCD not exceeding 30 mA, and that the wiring system between the pump circuit and the final subcircuit protective device meets the current carrying capacity, installation, type and segregation requirements of the relevant clauses. An exception is explained for lighting and socket outlets in pump rooms where certain wiring system requirements do not need to apply. Clause 7.2.5.6 Fire pump motors. This clause introduces the requirements that apply specifically to motors used to drive fire pumps. Clause 7.2.5.6.1 Isolating switches for fire pump motors. This clause explains that where fire pump motors are automatically controlled, a manually operated isolating switch must be installed on the supply side of the pump motor. It explains that this isolating switch must meet the requirements of the relevant clauses, be installed adjacent to the motor, and be provided with a device that allows the switch to be locked in the closed position. Clause 7.2.5.6.2 Overcurrent protection for fire pump motors. This clause explains that overcurrent protective devices for fire pump motors must have inverse time characteristics. It explains that circuit breakers must be rated to carry 125% of the full load motor current continuously, and must not open the circuit in less than 20 seconds at 600% of full load current. It also explains that no other overload protective device may be installed between the motor controller and the motor. Where more than one motor is supplied from the same circuit, the protection must be set to carry 125% of the combined full load current and meet the same minimum opening time requirement based on the largest motor. Clause 7.2.5.6.3 Over-temperature protection for fire pump motors. This clause explains that over-temperature protective devices must not be provided on fire pump motors where their operation could reduce the operating time of the equipment during emergency conditions. Clause 7.2.5.6.4 Control circuits for fire pump motors. This clause explains that control circuits for fire pump motors must be directly connected between the active and neutral conductors of the pump circuit, which means transformers are not permitted. It explains that the active conductor of the control circuit must be directly connected to the operating coil within the starter, and that no overload protective devices are allowed in the control circuit other than those provided for the pump motor circuit. It also explains that this arrangement requires a switch to be installed in the neutral conductor of the control circuit for the fire pump motor. Clause 7.2.6 Fire and smoke detection equipment and fire alarm systems. This clause introduces the requirements for electrical installations supplying fire and smoke detection and alarm systems. The intent is to ensure these systems remain reliable so they can detect fire, warn occupants, and support emergency response when required. Clause 7.2.6.1 General. This clause explains that fire and smoke detection and alarm systems include fire and smoke detection equipment, fire indicator panels, fire and smoke alarm systems, and warning and intercom systems. The key idea is that all of these elements together form the safety service responsible for detecting fire and alerting people. Clause 7.2.6.2 Wiring systems for fire detection and alarm systems. This clause introduces the requirements for wiring systems that supply fire detection and alarm systems, focusing on maintaining supply and system integrity under emergency conditions. Clause 7.2.6.2.1 Types of wiring systems for fire detection and alarm systems. This clause explains that wiring systems supplying fire detection and alarm systems must comply with ASNZS 3013 and use a wiring system classification specified by the relevant installation standard. Where no wiring system classification is specified, the wiring must be capable of maintaining supply when exposed to fire or mechanical damage, or must maintain supply when exposed to fire while also being protected against mechanical damage. This protection may be achieved by installing the wiring in an effective enclosure or locating it where mechanical damage will not occur. The clause then explains that these fire and mechanical protection requirements do not apply where the wiring is already installed in a location or enclosure that provides protection, or where circuits provide the primary power source to fire detection and alarm systems that have compliant battery backup up to the control and indicating panel, or for circuits supplying emergency warning systems beyond the main equipment panel when they comply with the relevant standards. Clause 7.2.6.2.2 Segregation of cables for fire detection and alarm systems. This clause explains that conductors for fire detection and alarm systems must not be enclosed with conductors of different safety services or with conductors of any other wiring system. It explains that effective segregation may be achieved by dividing ducts or trunking into separate channels with continuous barriers, by physically separating wiring systems from all others by at least 50 mm or using effective barriers, and by ensuring conductors of different fire and smoke detection and alarm systems are not combined together or mixed with other wiring systems within the same multi-core cable. Clause 7.2.6.3 Interposing switches for fire detection and alarm systems. This clause explains that no switch is permitted to be installed between a main switch and downstream switchboard supplying fire and smoke detection and fire alarm systems, so that supply cannot be accidentally interrupted. Clause 7.2.7 Air handling systems. This clause introduces air handling systems that are intended to exhaust and control the spread of fire and smoke, and confirms that these systems are treated as safety services. Clause 7.2.7.1 General. This clause explains that air handling systems used to control fire and smoke movement are safety services and must therefore meet the requirements that ensure reliable operation during emergencies. Clause 7.2.7.2 Wiring systems for air handling systems. This clause introduces the wiring requirements for air handling systems used for fire and smoke control. Clause 7.2.7.2.1 Types of wiring system for air handling systems. This clause explains that wiring systems supplying air handling systems must comply with ASNZS 3013 and use the wiring system classification specified by the relevant installation standard. Where no wiring system classification is specified, the wiring must be capable of maintaining supply when exposed to fire or mechanical damage, or must maintain supply when exposed to fire while being protected against mechanical damage, either through an effective enclosure or by location. It also explains that these protection requirements do not apply where the wiring is already installed in an enclosure or location that provides adequate fire and mechanical protection. Clause 7.2.7.2.2 Segregation of cables for air handling systems. This clause explains that conductors supplying air handling systems must not be enclosed with conductors of different safety services or with conductors of any other wiring system. It explains that segregation may be achieved using divided ducts or trunking with continuous barriers, physical separation of at least 50 mm or effective barriers, and by ensuring conductors of different safety services are not combined within the same multi-core cable. Clause 7.2.7.3 Interposing switches for air handling systems. This clause explains that no switch is permitted to be installed between a main switch and downstream switchboards supplying air handling systems, to prevent unintended loss of supply. Clause 7.2.8 Evacuation equipment. This clause introduces evacuation equipment used during emergencies to assist people to leave a building safely. Clause 7.2.8.1 General. This clause explains that evacuation equipment includes sound systems and intercom systems used for emergency purposes that comply with AS 1670.4. It also notes that emergency evacuation lighting requirements are addressed by building codes. Clause 7.2.8.2 Wiring systems for evacuation equipment. This clause introduces wiring system requirements for evacuation equipment. Clause 7.2.8.2.1 Types of wiring system for evacuation equipment. This clause explains that wiring systems supplying evacuation equipment must comply with ASNZS 3013 and use a wiring system classification specified by AS 1670.4. Clause 7.2.8.2.2 Segregation of cables for evacuation equipment. This clause explains that conductors supplying evacuation equipment must not be enclosed with conductors of different safety services or with conductors of any other wiring system. It explains that effective segregation can be achieved using divided ducts or trunking, physical separation of at least 50 mm or effective barriers, and by ensuring conductors of different safety services are not combined within the same multi-core cable. Clause 7.2.8.3 Interposing switches for evacuation equipment. This clause explains that no switch is permitted to be installed between a main switch and downstream switchboards supplying evacuation equipment. Clause 7.2.9 Emergency lifts. This clause introduces requirements for lifts that are required to operate for firefighting or other emergency purposes and are treated as safety services in New Zealand. Clause 7.2.9.1 General. This clause explains that in New Zealand, lifts required to operate for firefighting or other emergency purposes are safety services and must comply with the requirements of this section. Clause 7.2.9.2 Control and protection. This clause explains that each emergency lift, or group of emergency lifts, must be controlled and protected independently of all other lifts. It explains that main switches controlling lifts must be arranged in accordance with Clause 7.2.4 and clearly identified so they are distinguishable from switches controlling other lifts. Clause 7.2.9.3 Wiring systems for emergency lifts. This clause introduces wiring requirements for emergency lifts. Clause 7.2.9.3.1 Types of wiring system for emergency lifts. This clause explains that wiring systems supplying emergency lifts must comply with ASNZS 3013 and use the wiring system classification specified by the relevant installation standard. Where no wiring system classification is specified, the wiring must be capable of maintaining supply when exposed to fire or mechanical damage, or must maintain supply when exposed to fire while being protected against mechanical damage, either by effective enclosure or by suitable location. It also explains that these protection requirements do not apply where wiring is already installed in a protected enclosure or location, or for circuits supplying lifts beyond the terminals of a circuit breaker in the lift machine room used for control and protection of the lift installation. Clause 7.2.9.3.2 Segregation of cables. This clause explains that conductors supplying lifts must not be enclosed with conductors of different safety services or with conductors of any other wiring system. Clause 7.2.9.4 Interposing switches. This clause explains that no switch is permitted to be installed between a main switch for lifts and downstream lift switchboards, except where an alternative supply system is provided or where switches are located remote from the building being supplied. Clause 7.2.9.5 Switchgear. This clause explains that where emergency equipment is required by building codes, switchboards supplying that equipment must be constructed so that emergency switchgear is separated from other switchgear by metal partitions to limit the spread of faults. Clause 7.2.10 Emergency motor room-less lifts. This clause introduces additional requirements for emergency motor room-less lifts, also known as MRL lifts. Clause 7.2.10.1 General. This clause explains that motor room-less lifts do not require a traditional lift motor room due to their design. It explains that an MRL switchboard must comply with Clause 2.10, and that MRL lifts fitted for emergency evacuation, firefighting activities, or designated as emergency lifts must meet the additional requirements of this clause. Clause 7.2.10.2 Switchboards. This clause explains that an MRL switchboard must not be located in the lift shaft. It also explains that switchboards located remote from the main switchboard and dedicated to supplying individual MRL switchboards must be readily accessible and enclosed in a fire-rated room or enclosure. Clause 7.2.10.3 Switchgear. This clause explains that an MRL switchboard must be located in a readily accessible position, and that where the switchboard penetrates into the lift shaft, the fire rating must be maintained in accordance with the relevant clause. Clause 7.2.10.4 Wiring systems. This clause introduces wiring system requirements for MRL lifts. Clause 7.2.10.4.1 Types of wiring systems for MRL lifts. This clause explains that wiring systems supplying MRL lifts must comply with ASNZS 3013 and use the wiring system classification specified by the relevant installation standard. Where no wiring system classification is specified, the wiring must be capable of maintaining supply when exposed to fire or mechanical damage, or must maintain supply when exposed to fire while being protected against mechanical damage, either through effective enclosure or suitable location. It also explains that these protection requirements do not apply where wiring is installed in a protected enclosure or location. Clause 7.2.10.4.2 Segregation of cables. This clause explains that conductors supplying MRL lifts must not be enclosed with conductors of different safety services or with conductors of any other wiring system, and that effective segregation may be achieved using divided enclosures, compliant wiring systems, or by ensuring conductors of different safety services are not combined within the same multi-core cable. Clause 7.3 Electricity generation systems. This clause introduces the requirements for electricity generation systems that are connected to electrical installations. It explains that these requirements add to or modify the rules in sections 2 to 7 of ASNZS 3000 when a generation system is used to supply all or part of an installation, whether it operates continuously or only at certain times, including systems that operate alongside other supplies. Clause 7.3.1 General. This clause explains that electricity generation systems may take several forms. It explains that an alternative or supplementary supply may be provided by a generator set, typically driven by a combustion engine, which may supply an alternative or standby alternating current supply when the normal supply fails, may act as the primary power supply to an installation, or may be used as part of a standalone power system. It also explains that a standalone power system is not connected to a network provider's distribution system and may be supplied from sources such as photovoltaic arrays, wind turbines or mini hydro turbines, or engine-driven generator sets that provide either alternating current or direct current. The clause then explains that an inverter system may supply alternating current using an interactive inverter powered by renewable energy sources such as photovoltaic, wind or mini hydro systems. Where renewable energy output exceeds the installation load, any approved surplus energy may be exported into the distribution system, and where renewable output is insufficient, energy is imported from the network. It also explains that the interactive inverter controls both exporting and importing of energy. The clause further explains that a battery system may be used to store energy from sources such as generators, photovoltaic arrays, wind turbines or mini hydro turbines in order to supply alternating current to an electrical installation. Clause 7.3.2 Selection and installation of system. This clause explains that the selection, installation and control of electrical equipment forming part of an electricity generation system must comply with the relevant standards for the type of system being installed. It explains that engine-driven generating sets, standalone power systems, battery systems, photovoltaic array systems and inverter systems each have specific standards that must be followed so that the system operates safely and correctly. Clause 7.3.3 Control. This clause explains that an electricity generation system must be controlled by a main switch or switches located at the installation switchboard where the system connects to the installation. It explains that suitable switches or devices must be provided for starting and stopping the generation system, and where more than one control device is used they must be grouped together and clearly identified. It also explains that the system must be arranged so it cannot supply energy upstream of the point of connection to the installation, either directly or indirectly, unless a formal agreement exists with the electricity distributor. The clause notes that conditions for grid-connected and cogeneration systems operating in parallel with the network are outside the scope of this standard. Clause 7.3.3.1 Basic Protection and Fault Protection. This clause explains that all necessary connections for basic and fault protection, including the MEN connection, must remain intact when supply is available from the electricity generation system. The intent is to ensure that protective measures continue to operate correctly regardless of whether power is coming from the network or the generator. Clause 7.3.4 Isolation. This clause introduces the isolation requirements for electricity generation systems so that equipment can be safely disconnected when required. Clause 7.3.4.1 General. This clause explains that an inverter or regenerative supply source must not be connected downstream of a generating set changeover device, unless control systems prevent backfeed to the generator. It explains that every electricity generation system must be provided with an isolating switch in accordance with the relevant clause. The isolating switch must be installed adjacent to or on the generation system so the operator has a clear view of anyone working on the system, or it must have a means of securing it in the isolated position that requires a deliberate action to operate. It explains that the isolating switch may be combined with overcurrent protection where permitted, must comply with the relevant motor isolation requirements where an electric motor is involved, must be under manual control only, and must not be capable of being overridden or bypassed by programmable control systems. It also explains that isolation location requirements may be varied by other related standards. Clause 7.3.4.2 Electricity generation systems incorporating batteries. This clause explains that where batteries are included in an electricity generation system, a switch capable of interrupting the battery supply must be installed adjacent to the batteries and must be clearly identified to indicate its purpose. It also explains that a single switch incorporating both alternating current and direct current switching functions may be used where permitted. Clause 7.3.5 Overcurrent protection. This clause introduces the requirements for overcurrent protection in electricity generation systems. Clause 7.3.5.1 Electricity generation system protection. This clause explains that electricity generation systems must be provided with overcurrent protection in accordance with the applicable standards for the particular system. Where no specific requirement is given, it explains that overcurrent protective devices must be located as close as practicable to the output terminals of the generation system so that unprotected interconnecting conductors are as short as possible and never exceed 15 meters. It also explains that unprotected interconnecting conductors must be completely enclosed by non-combustible material or installed underground. The clause explains that overcurrent protection may be provided by protective devices within the generation system itself, or by the characteristics of the system that limit fault current. It further explains that where systems operate in parallel, circulating harmonic currents must be limited so conductor current carrying capacity is not exceeded, and it outlines practical methods for achieving this. Clause 7.3.5.2 Circuit protection. This clause introduces requirements for protecting individual circuits supplied from electricity generation systems. Clause 7.3.5.2.1 General. This clause explains that prospective short-circuit current and prospective earth fault current must be assessed for each electricity generation system or combination of systems supplying an installation. It explains that the short-circuit rating of protective devices must not be exceeded under any intended operating condition. It also explains that where electronic overcurrent protection is fitted within a generation system, such as in inverters, the system may automatically limit output current and may prevent the operation of external protective devices during fault conditions. The clause explains that every outgoing circuit must be individually protected and include additional earth leakage protection where required. It also explains when a circuit may be considered protected against prospective short-circuit earth fault currents due to the limited output capability of the generation system. Clause 7.3.5.2.2 RCDs. This clause explains that the waveform of fault current to earth from electricity generation systems can affect the operation of RCDs and must be considered when selecting the RCD type. Where an inverter is used, the RCD must be suitable for the earth fault waveform produced by that inverter and must be installed in accordance with the manufacturer's instructions. Clause 7.3.6 Earthing. This clause explains that protective earthing in the electrical installation must use an MEN system in accordance with Section 5. It explains that any exposed conductive parts of the electricity generation system must be earthed by connection to the main earthing conductor at the main switchboard. Clause 7.3.7 Connected electrical equipment. This clause explains that any accessory, conductor, insulation or other component connected to the output side of an electricity generation system must be suitable for the voltage, current and frequency produced by the system. Clause 7.3.8 Connection to electrical installation. This clause introduces requirements for how electricity generation systems are connected to electrical installations. Clause 7.3.8.1 Alternative supplies. This clause introduces requirements for alternative or standby supplies connected to installations. Clause 7.3.8.1.1 General. This clause explains that the incoming neutral to AMEN switchboard must not be switched when connecting an alternative supply. It explains that the neutral earth connection must be made within the installation at the main switchboard, and this may require disconnection of any neutral earth link within a generation system such as an engine-driven generator. It explains that this applies to any switchboard fitted with a MEN connection, including switchboards in outbuildings regarded as main switchboards for earthing purposes. It also explains that neutral and earth conductors must not operate in parallel, and sets out the New Zealand specific requirement that where a generating set is connected to a switchboard without a neutral earth link and the installation operates from the alternative supply, a neutral earth connection and connection to the mass of earth must be made in the distribution switchboard in accordance with ASNZS 3010. Clause 7.3.8.1.2 Switching. This clause explains that the changeover device for an alternative supply must be selected to maintain the function of, and prevent damage to, the electrical installation. It explains that this includes maintaining continuity of the neutral conductor, correct operation of ACDs, and continued uninterrupted power supplies. It explains that the changeover device must open all active conductors of the normal supply when the alternative supply is connected, and that automatic switching must be clearly marked. It also explains that switching arrangements complying with ASNZS 3010 are acceptable. Clause 7.3.8.2 Grid-connected inverter systems. This clause introduces requirements for inverter systems connected to the electricity network. Clause 7.3.8.2.1 General. This clause explains that connection of a grid-connected system is subject to formal agreement with the electricity distributor. Clause 7.3.8.2.2 Switching. This clause explains that a main switch must be provided to allow isolation of the inverter output from the switchboard to which it is connected, and that all switches must be clearly identified according to their function. Clause 7.3.8.2.3 Connection. This clause explains that grid-connected inverter systems must be connected in accordance with the ASNZS 4777 series and the requirements of the electricity distributor. It explains that the generation system must not impose a voltage on the installation outside permitted limits at the point of supply. Clause 7.3.8.3 Standalone power systems. This clause introduces requirements for standalone systems that are not connected to the electricity network. Clause 7.3.8.3.1 General. This clause explains that the consumer mains of the electrical installation must be connected to the output of the electricity generating system. Clause 7.3.8.3.2 Switching. This clause explains that control of the electrical installation supplied by a standalone system must be arranged in accordance with Clause 2.3. Clause 7.3.8.3.3 Connection. This clause explains that the method of connection for a standalone system must comply with the ASNZS 4509 series, and that typical arrangements include a local MEN connection at the switchboard. Clause 7.4 Protection by electrical separation isolated supply. This clause explains protection by electrical separation, which has the same meaning as isolated supply. The idea is to reduce the risk of electric shock by separating the supply so that dangerous touch voltages cannot occur under fault conditions. Clause 7.4.1 General. This clause explains that Clause 7.4 provides protection against electric shock from indirect contact and is recognized as complying with Clause 1.5.5. It explains that electrical separation is an alternative protection method and is intended, within an individual circuit, to prevent shock current flowing through exposed conductive parts that could become energized by a fault. It explains that protection by electrical separation is achieved by complying with clauses 7.4.2 to 7.4.4, together with clause 7.4.5 where a single item of equipment is supplied, or clause 7.4.6 where more than one item of equipment is supplied. Clause 7.4.2 Source of supply. This clause explains that a separated circuit must be supplied from a suitable source. The source may be an isolating transformer complying with ASNZS 61558 so that the output is separated from the input by double insulation or an equivalent method. It explains that higher transformer ratings are permitted where the relevant construction and verification provisions are applied. It also explains that a generator output may be used where the output is separated from the generator frame, or an isolated inverter complying with ASNZS 4763 may be used. The clause explains that fitting in RCD or additional bonding conductors to the generator output does not provide the required output separation. It also explains that the rated output of separated transformers or generators should be limited to suitable values to ensure safe operation. Clause 7.4.3 Arrangement of circuits. This clause explains that separated circuits must meet specific arrangement requirements. It explains that circuit voltage must not exceed 500 volts, and that all live parts of a separated circuit must be effectively separated from all other circuits and from earth. It explains that this requirement also applies to live parts of relays, contactors and similar equipment within the separated circuit. It further explains that exposed conductive parts supplied by a separated circuit must not be connected to protective earthing conductors, exposed conductive parts of other circuits, or the exposed conductive parts of the source of supply. It explains that cables and flexible cords must be protected against mechanical damage or arranged so any damage is readily visible. Clause 7.4.4 Switching devices. This clause explains that switching devices must operate in all live conductors of a separated circuit. It explains that switching the active conductor on the primary of an isolating transformer, in accordance with the relevant clause, is an acceptable method of control and disconnection. Clause 7.4.5 Supply to single item of electrical equipment. This clause explains that where a separated circuit supplies a single item of electrical equipment, any exposed conductive parts of that equipment must not be connected to exposed conductive parts of any other circuit, including other separated circuits, or to earth. Clause 7.4.6 Supply to multiple items of electrical equipment. This clause explains that where a separated circuit supplies more than one item of electrical equipment, all exposed conductive parts of the separated circuit must be connected together by an insulated equipotential bonding conductor that is not connected to earth, protective earthing conductors, exposed conductive parts of other circuits, or extraneous conductive parts. It explains that socket outlet earth contacts must be connected to this equipotential bonding conductor, and that any designated protective earthing conductor and supply cables or flexible cords to equipment, other than Class II equipment, must also be connected to the equipotential bonding conductor. It explains that exposed conductive parts of the source of supply that are earthed must not be simultaneously accessible with exposed conductive parts of the separated circuit. It also explains that a protective device must disconnect the separated circuit automatically if two faults result in exposed conductive parts becoming connected to live parts of different polarity. Clause 7.4.7 Variable Speed Drive VSD-EMI Filters. This clause explains that where a variable speed drive uses an EMI filter, the filter must not reference the frame of the system. It explains that only one EMI filter should be used on an isolated supply where multiple drives are used, and that filters referencing the frame can create harmful capacitive coupled currents. Clause 7.4.8 Testing. This clause introduces the testing requirements for separated circuits. Clause 7.4.8.1 General. This clause explains that in addition to Section 8 testing, the separation of each separated circuit must be individually confirmed. It explains that separation is verified by measuring insulation resistance between the separated circuit and the transformer primary winding where applicable, other wiring, other separated circuits, and earth. It explains that insulation resistance must not be less than 1 megohm when tested at 500 volts direct current. Clause 7.4.8.2 Single items of electrical equipment. This clause explains that where a single item of equipment is supplied from a separated circuit, separation must be verified by testing in accordance with the general testing clause and by measuring insulation resistance between earth and the exposed conductive parts, or the earth contact of a socket outlet. Clause 7.4.8.3 Multiple items of electrical equipment. This clause explains that where more than one item of equipment is supplied from a separated circuit, separation must be verified by testing in accordance with the general testing clause and by measuring insulation resistance between the separated circuit and the equipotential bonding conductor, between the equipotential bonding conductor and earth, and between the equipotential bonding conductor and any equipotential bonding conductor associated with another separated circuit. Clause 7.4.8.4, Bonding Conductor Continuity. This clause explains that the resistance of an equipotential bonding conductor for socket outlet earth contacts or exposed conductive parts connected to the same separated circuit must not exceed 0.5 ohms. Clause 7.5, Extra low voltage electrical installations. This clause introduces extra low voltage electrical installations and explains that they are considered to comply with basic and fault protection requirements by the use of extra low voltage. Clause 7.5.1, Scope. This clause explains that Clause 7.5 applies to installations operating at extra low voltage and that compliance with this clause is taken as compliance with basic and fault protection requirements. Clause 7.5.2, Application. This clause explains that extra low voltage installations must be either SELV or PELV systems. It explains that the requirements of this clause supplement or replace other section requirements, and that where an installation operates at extra low voltage but does not meet SELV or PELV requirements, it is treated as low voltage and must comply with other relevant sections. Clause 7.5.3, Sources of supply to SELV and PELV systems. This clause explains that SELV and PELV systems must be supplied from approved sources. These include a safety isolating transformer complying with AS NZS 61558, an independent source such as an engine-driven generator or battery, a separated source such as a motor generator set with electrically separate windings, or certain electronic devices designed so that output voltage cannot exceed extra low voltage under fault conditions. Clause 7.5.4, Separation requirements for SELV and PELV circuits. This clause explains that live parts of SELV and PELV circuits must be electrically separated from each other and from higher voltage circuits. It explains that separation must be equivalent to that provided by a safety isolating transformer, and that conductors must be segregated from other circuits. It also explains that live parts must be arranged so that short-circuiting or arcing will not occur under normal service conditions. Clause 7.5.5, Arrangement of SELV circuits. This clause explains that live parts of SELV circuits must not be connected to earth, protective earthing conductors, exposed conductive parts of other systems, or extraneous conductive parts. It explains limited exceptions where connection to extraneous conductive parts is inherently required and voltage cannot exceed SELV limits. It also explains that where SELV circuits may come into contact with other exposed conductive parts, protection against electric shock may depend on the protection applied to those other parts. It explains that where nominal voltage exceeds specified values, basic protection must be provided by barriers, enclosures, or insulation capable of withstanding specified test voltages. Clause 7.5.6, Arrangement of PELV circuits. This clause explains that for PELV circuits where one output conductor is earth, basic protection must be provided by barriers or enclosures of suitable IP rating, or by insulation capable of withstanding specified test voltages. It explains exceptions where basic protection may be unnecessary under defined low voltage and dry conditions, and notes requirements relating to earthing and insulation performance. Clause 7.5.7, Voltage drop in conductors. This clause explains that voltage drop in extra low voltage installations must not exceed 10% of nominal voltage when conductors are carrying operating current. It explains that information on voltage drop is provided in AS NZS 3008.1, and that this requirement does not apply where equipment is designed to operate with a higher voltage drop, such as during motor starting or similar transient conditions. Clause 7.5.8, Control of an electrical installation. This clause explains that an extra low voltage electrical installation must be controlled by one or more main switches that operate in all unearthed conductors. The purpose is to ensure the supply can be safely disconnected when required. It also explains that this requirement does not apply where the extra low voltage installation is supplied from part of a higher voltage installation and switching the higher voltage main switch disconnects the supply to the extra low voltage system. Clause 7.5.8.1 Main switches. This clause clarifies that the control of supply to an extra low voltage installation must be achieved using main switches that operate in all unearthed conductors, ensuring complete disconnection of the supply when operated. Clause 7.5.8.2 Other switches. This clause explains that switches used within an extra low voltage installation must be suitable for the system arrangement. Where the extra low voltage supply is earthed at the point of supply, such as PELV, the switch must operate in all unearthed conductors. Where the system is SELV, switches may operate in one fewer conductor than the total number of conductors in the circuit. Clause 7.5.9 Overcurrent protection. This clause introduces the requirement for protection against overload and short-circuit currents in extra-low voltage circuits to prevent damage in unsafe conditions. Clause 7.5.9.1 General. This clause explains that every extra-low voltage circuit must be individually protected at its origin against overload and short-circuit currents using a suitable protective device. The protection must comply with the general requirements for protection against overcurrent. It also explains that where the extra low voltage supply is earthed at the point of supply, protective devices must be installed in all unearthed conductors. Certain circuits arranged under specific conditions may not require overcurrent protection. Clause 7.5.9.2 Emission of overcurrent protection. This clause explains that overcurrent protection may be emitted where interrupting the supply would create a greater danger than the overcurrent itself, or where the rated output of the source does not exceed the rating of the circuit. It describes acceptable sources, including short-circuit-proof transformers with limited output current, or batteries with high internal resistance such as primary cells. Clause 7.5.10 Connecting devices. This clause explains that plugs and socket outlet devices used for SELV and PELV systems must be designed so they cannot be interchanged with devices of other voltage systems. It also explains that socket outlets must not accept plugs from other voltage systems and must not include a contact for a protective earthing conductor. Clause 7.5.11 Wiring systems. This clause introduces requirements for wiring systems used in extra-low voltage installations, focusing on suitability and protection based on installation conditions. Clause 7.5.11.1 General. This clause explains that conductors and cable insulation for extra-low voltage installations must be suitable for their intended purpose and normally do not require additional protection unless installation conditions demand it. Attention is drawn to segregation requirements where extra protection may be needed in certain situations. Clause 7.5.11.2 Aerial conductors. This clause explains that aerial conductors used in extra-low voltage installations must be installed in accordance with the relevant requirements for overhead wiring. It also explains that certain clearance requirements may not apply if alternative protective measures are satisfied, and that bare conductors may be used where permitted for insulated conductors. Clause 7.5.11.3 Underground conductors. This clause explains that there are no specific burial depth requirements for extra-low voltage cables from a safety perspective, but careful consideration must be given to the risk of mechanical damage. Clause 7.5.12 Testing. This clause introduces the testing requirements that confirm the separation and safety of extra-low voltage circuits. Clause 7.5.12.1 General. This clause explains that the separation of extra-low voltage circuits must be verified by insulation resistance testing. It clarifies that different verification methods apply depending on whether protection is achieved by SELV or PELV. Clause 7.5.12.2 Protection by SELV. This clause explains that, for SELV systems, separation of live parts from other circuits and from earth must be confirmed by measuring insulation resistance. Clause 7.5.12.3 Protection by PELV. This clause explains that, for PELV systems, separation of live parts from other circuits must also be confirmed by insulation resistance measurement. Clause 7.9, Supplies for electric vehicles. This clause introduces additional requirements that apply to electrical installations intended for charging electric vehicles in New Zealand. Clause 7.9.1, Scope. This clause explains that the requirements apply to parts of electrical installations used for charging electric vehicles in New Zealand. It also highlights that electric vehicle charging can affect maximum demand and may require notification to the electricity distributor. Clause 7.9.2 Supply. This clause introduces requirements for how the supply to electric vehicle charging installations must be arranged. Clause 7.9.2.1 Source of supply. This clause explains that the supply for electric vehicle charging must not be taken from a switchboard located in an outbuilding that has a separate MEN earthing system. Clause 7.9.3 Domestic electrical installations. This clause introduces specific requirements for domestic installations in New Zealand that provide facilities for charging electric vehicles. Clause 7.9.3.1 Facilities for other than Mode 1 charging. This clause explains that new domestic electrical installations with an enclosed garage or similar space intended to accommodate a motor vehicle must include a facility to enable electric vehicle charging, using approved charging modes. Clause 7.9.3.2 Facilities for Mode 2 charging. This clause explains that Mode 2 charging facilities must meet requirements for minimum circuit capacity, dedicated final subcircuits, compliant socket outlets, minimum installation height, and appropriate switching and protection. Clause 7.9.3.3 Facilities for Mode 3 and Mode 4 charging. This clause explains that higher mode charging systems must comply with requirements for circuit capacity, dedicated final subcircuits, suitable RCD protection, direct connection of equipment, provision of an isolating switch, and minimum installation heights for outlets or cables. Clause 7.9.4 Other electrical installations. This clause explains that electrical installations associated with electric vehicle charging, other than those specifically covered, must be protected by a separate RCD of the appropriate type and rating, ensuring protection of all live conductors and safe operation of the charging system. That brings us to the end of Section 7, Special Electrical Installations. You should now have a clear understanding of how electrical safety is managed when installations fall outside normal conditions, and why extra requirements are applied in these situations. Always remember that these special rules work alongside the general requirements of ASNZS 3000, not instead of them. Correct design, selection, installation, control, protection, and verification are essential to keep people, property, and equipment safe. For any installation that falls into these categories, always refer back to the relevant clauses and supporting standards before carrying out work. Hi everyone, my name is Aria, and I work alongside Whit Roy as an electrical tutor. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 3000, 2018. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for EWRB exam. What this audiobook does is take the key ideas from the standard and explain them in simple, spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real installations. So think of this as a learning companion, not a replacement for the actual standard. Alright, let's get started. Hello everyone. In this section we are moving into Section 8, which is all about verification. Verification is the final check that confirms an electrical installation is safe, compliant, and ready to be energized. In this section we will walk through visual inspection, mandatory testing, earth fault loop impedance, RCD operation, and verification records. Everything is explained in simple spoken language to help you understand not just what needs to be done, but why these checks matter in real electrical work. Clause 8.1 General. This clause introduces Section 8 and explains that this part of the standard is about verification. Verification means checking an electrical installation to make sure it meets the basic safety principles required by Part 1 of this standard. The focus is on inspection and testing so the installation can be confirmed as safe and fit for use. Clause 8.1.1 Application. This clause explains that Section 8 sets the minimum requirements for inspection and testing. These checks are required to confirm that an electrical installation meets the fundamental safety principles of this standard. In simple terms, it tells us that verification is a key step to prove the installation is safe before it is used. Clause 8.1.2 General Requirements. This clause explains that before an electrical installation, or any part of it, is put into service after construction, alteration, or repair, it must be verified as far as is practical. Verification is done to make sure the installation is safe to energize and will operate in line with the requirements of this standard. It also explains that once the work is finished and before the installation is put into service, the installation must be inspected in line with Clause 8.1.3 and Clause 8.2 as far as is practical, and it must be tested in line with Clause 8.3. The clause also reminds us that safety precautions must be taken during inspection and testing to protect people, property, and electrical equipment. Where work involves an alteration or repair to an existing installation, verification is required to confirm that the work complies with this standard and does not reduce the safety of the existing installation. The notes explain that extra inspection and testing may be needed for certain types of installations, and that in New Zealand, special attention is required for wiring and fittings located near conductive thermal insulation, as covered by NZ-ECP 55. Clause 8.1.3 Periodic Inspection and Testing. This clause explains that electrical installations must also undergo periodic inspection and testing, not just checks at completion. These ongoing checks are required to confirm that the installation remains safe over time. The clause states that this inspection and testing must be carried out in line with the requirements set by the regulatory authority, and also by the owner or occupier of the premises. The note explains that recommended arrangements for periodic testing are provided in as NZS 3019. Clause 8.2 Visual Inspection. This clause explains that visual inspection is a required part of verification. A visual inspection must be carried out once work on an electrical installation has been completed. The purpose is to confirm that the completed work meets the requirements of this standard. The inspection is normally done before testing or together with testing, and where practical it should be completed before the relevant part of the installation is placed into service. The clause also explains that if a visual inspection of part of the installation is not practical at the completion of the work, for example because it is enclosed within the building structure, consideration should be given to inspecting that part during the course of the installation instead. Clause 8.2.1 General. This clause reinforces that visual inspection is a mandatory step after work is completed. The inspection is carried out to verify compliance with this standard and to make sure the installation is suitable to be put into service. It highlights that visual inspection forms a key part of the overall verification process and works together with testing. Clause 8.2.2 Checklist. This clause explains that during a visual inspection, certain matters must be checked where they apply, to confirm that the relevant requirements of this standard have been met. It begins with general matters, including checking that basic protection is in place to prevent direct contact with live parts, such as correct insulation and enclosures. It also includes checking fault protection, to ensure protection against indirect contact with exposed conductive parts, for example through automatic disconnection of supply, double insulation, or isolating transformers. The inspection must also confirm protection against hazardous parts, such as guarding or enclosure of hot surfaces, flammable materials, or parts that could cause physical injury. Protection against the spread of fire is checked, including the integrity of fire barriers. The general condition of electrical equipment is assessed to identify signs of damage that could affect safe operation and to confirm that unused electrical equipment has been disconnected. The clause then moves to consumer mains. These checks include confirming that the current carrying capacity is adequate, that voltage drop is appropriate for the size of the conductors, and that underground installations have suitable enclosure, burial depth, and mechanical protection. Burial installation conditions are checked, along with the correctness of wiring connections and protection against external influences. For switchboards, the inspection includes checking the location to ensure safe access and egress. Protective devices are reviewed to confirm correct selection and settings so they comply with overcurrent protection, arc fault protection, and discrimination requirements. Isolating devices such as main switches are checked, along with connecting devices like neutral bars, earth bars, and active links. The inspection confirms that wiring and switchgear are properly connected and fixed, that equipment is clearly identified and labeled, and that protection against external influences is provided. For wiring systems, the inspection checks that conductor sizes are suitable for current carrying capacity and voltage drop, that cable cores are correctly identified, and that there is adequate support in fixing. Connections and enclosures are checked, along with particular installation conditions such as underground, aerial, or safety services. The inspection also confirms segregation from other services and electrical installations, and protection against external influences such as enclosure. For electrical equipment, the inspection includes checking isolation and switching devices used to protect against injury from mechanical movement, such as motors. It also includes checking isolation and switching devices used for protection against thermal effects, such as motors, room heaters, and water heaters. Switching devices for particular equipment, such as socket outlets and water heaters, are reviewed. The inspection confirms that special installation conditions are met, including locations affected by water, explosive atmospheres, extra low voltage, or high voltage. Compliance with the required standard is confirmed, along with correct connection, support, and fixing. Protection against external influences, including ingress of moisture where required, is checked, and the suitability of equipment for the intended voltage, current, and frequency is confirmed. The clause then covers earthing. The inspection checks the main connection, the earth electrode, and earthing conductors for correct size and identification. Equipotential bonding conductors are checked for size and identification, along with connections, joints, and terminations. Protection against external influences is confirmed, and connections to earthing arrangements for other systems are reviewed. The inspection also considers whether the creation of an earth situation may require additional earthing of electrical equipment. Clause 8.3 Testing. This clause introduces testing as the next stage of verification following visual inspection. Testing is carried out to confirm that the electrical installation complies with the requirements of this standard and is suitable for its intended use. Clause 8.3.1 General. This clause explains that after completion of the work, or in association with the visual inspection, tests must be carried out on the electrical installation in accordance with Clause 8.3.3. The purpose of these tests is to verify compliance with this standard and confirm that the installation is fit for use. The clause also allows for additional tests to be carried out if they are necessary. Clause 8.3.2 Test Methods. This clause explains that as NZS 3017 sets out common test methods that may be used to verify, by testing, that a low-voltage electrical installation complies with this standard. It also includes minimum safety standards for test instruments. Testing must be carried out in a way that ensures the safety of the operator and other people nearby, and that test equipment is not placed at risk. The clause notes that the test methods given are reference methods, and other methods may be used provided they give equally valid results. Clause 8.3.2.2 Recording of results. This clause explains that it is recommended the results of tests are recorded and maintained, especially where the results provide values used for verification. Keeping records helps demonstrate compliance and supports future inspection and testing. Clause 8.3.3 Mandatory tests. This clause explains that certain tests are mandatory and must be carried out on parts of electrical installations designed to operate at low voltage. These tests include continuity of the earthing system, insulation resistance, polarity, correct circuit connections, verification of impedance required for automatic disconnection of supply, and operation of RCDs. The clause includes an exception that verification of earth fault loop impedance may be omitted where automatic disconnection of supply is not the method used to provide fault protection. The notes explain that some tests require the supply to be available, and that additional tests for isolated supplies are detailed elsewhere in the standard. Clause 8.3.3.1, Low voltage. This clause specifically applies the mandatory test to low voltage installations and confirms the scope of testing required for these systems. Clause 8.3.3.2, Extra low voltage. This clause explains that testing must also be carried out on parts of electrical installations designed to operate at extra low voltage. The required tests include continuity of the earthing system for PELV circuits, insulation resistance, polarity, and correct circuit connections, all in accordance with the relevant clauses referenced. Clause 8.3.3.3, Test failures. This clause explains that if any part of the electrical installation fails a test, that test and any earlier tests that may have been affected by the fault must be repeated after the fault has been corrected. This ensures that the installation is fully compliant after rectification. Clause 8.3.4, Sequence of tests. This clause explains that testing must follow a defined sequence. The testing sequence is shown in the standard, and the intention is to ensure tests are carried out in a logical order so results are valid and safety is maintained. Clause 8.3.5, Continuity of the earthing system. This clause explains that testing is required to prove continuity of the earthing system. This includes the main earthing conductor, protective earthing conductors, combined protective earthing and neutral conductors, and bonding conductors. The purpose is to ensure the earthing system is installed so that protective devices will operate if a fault occurs between live parts, other than the neutral, and the mass of earth. An effective earthing system prevents exposed conductive parts from reaching dangerous voltages under fault conditions. Where a PEN submain is installed in accordance with the reference clause, testing must confirm that the earth terminal or bar of the subboard is connected through the PEN conductor to the earth terminal or bar of the main switchboard. Clause 8.3.5.1 General. This clause reinforces the purpose of earthing continuity testing and explains how it supports correct operation of protective devices and overall electrical safety. Clause 8.3.5.2 Results. This clause explains that the resistance of protective earthing conductors must be low enough to allow sufficient current to flow to operate overcurrent protective devices, and consistent with the length, cross-sectional area, and type of conductor material. It also states that the resistance of the main earthing conductor or any equipotential bonding conductor must not exceed 0.5 ohms. With notes explaining how resistance values relate to protective devices and circuit characteristics. Clause 8.3.6, Insulation resistance. This clause explains that insulation resistance testing is carried out to ensure insulation between live conductors and earth, or between live parts and earth, is adequate to maintain insulation integrity. The purpose is to prevent electric shock hazards, fire hazards from short circuits, and equipment damage. It also explains that insulation resistance testing between conductors is necessary for consumer mains and submains to reduce the risk of injury or property damage due to insulation breakdown. Clause 8.3.6.1 General. This clause explains the safety purpose of insulation resistance testing and why it is critical for preventing shock, fire, and damage. Clause 8.3.6.2 Method. This clause explains that insulation integrity is tested by applying a direct current test voltage, typically 500 volts for low voltage circuits. It also explains exceptions where equipment may need to be disconnected or switched off before testing to avoid damage, or where a reduced test voltage may be used for particular circuits. Clause 8.3.6.3 Results. This clause explains that insulation resistance values must not be less than 1 megohm between conductors of consumer mains and submains, and between live and earthed parts of an electrical installation. It also explains acceptable lower values for specific situations, such as sheathed heating elements, RCDs with functional earth connections, or values permitted by the relevant equipment standard. Notes explain how insulation resistance varies with cable length, material temperature, and type. Clause 8.3.7, Polarity and correct circuit connections. This clause explains that polarity and correct connection testing is carried out to prevent unsafe conditions. These include transposition of active and neutral conductors, incorrect combinations of active, neutral, and earthing connections that could energize exposed conductive parts, incorrect operation of switches or protective devices, and short circuits between conductors. Clause 8.3.7.1 General. This clause explains the safety reasons for polarity and connection testing, including preventing installations from becoming energized in unsafe ways and ensuring correct operation of equipment and protective devices. Clause 8.3.7.2 Results. This clause explains that testing must show that all active, neutral, and protective earthing conductors are correctly connected to the corresponding terminals of electrical equipment. It confirms that there is no dangerous transposition of conductors, that switches and protective devices operate in the correct conductors, that phase sequence is consistent where required, that no protective earthing conductor is connected in parallel with a neutral conductor, that there are no short circuits between conductors, and that there are no unintended interconnections between different circuits. It also clarifies that any MEN or ESA connection is not regarded as a short circuit. Clause 8.3.9, Verification of earth fault loop impedance, spoken as EFLI. This clause explains the requirements for verifying earth fault loop impedance. The purpose of EFLI verification is to confirm that, if an earth fault occurs, the fault current will be high enough to cause the protective device to disconnect the supply within the required time. This helps prevent electric shock and fire risk by ensuring automatic disconnection of supply works as intended. Clause 8.3.9.1, Low voltage socket outlet circuits. This clause explains that EFLI testing must be carried out for certain low voltage socket outlet circuits. These are circuits where fault protection is provided by automatic disconnection of supply, where the circuit supplies one or more socket outlets, and where those socket outlets are not protected by an RCD with a rated residual current of 30 mA or less. The notes explain that the testing method verifies that the protective device will disconnect an earth fault current within the required time and touch voltage limits. They also explain that EFLI testing is not required for RCD-protected socket outlets because the operating time of the RCD provides additional protection. The notes further explain that EFLI testing is generally not required for circuits supplying equipment other than socket outlets, and that for other circuits the maximum trip time requirement must still be met, even if the EFLI testing itself is not required. Clause 8.3.9.2 Methods. This clause introduces the methods used for verifying earth fault loop impedance. It explains that one of the specified methods must be used, depending on whether supply is available at the time of testing. Clause 8.3.9.2.1 General. This clause explains that the choice of test method depends on the availability of supply. The methods described in the following clauses provide acceptable ways to verify earth fault loop impedance. Clause 8.3.9.2.2 Supply available. This clause explains that where supply is available, the earth fault loop impedance for each branch of each final subcircuit is measured using an earth fault loop impedance tester. The test is carried out at the socket outlet that is furthest from the supply on each branch of the final subcircuit. The clause also states that the MEN connection must be left intact during this testing. Clause 8.3.9.2.3 No supply available. This clause explains the method used when supply is not available. In this case, the total resistance of the active and protective earthing conductors of the circuit is measured using an ohmmeter. Each active conductor and the protective earthing conductor are connected together at the origin of the circuit, usually at the protective device. The resistance of each active and protective earthing conductor pair is then measured at the furthest point of each branch of the circuit. The notes explain that when supply is available, earth fault loop impedance testing is preferred because it verifies the complete earth fault loop, including the integrity of the MEN connection and the supply neutral or PEN conductors. Where supply is not available, the resistance method establishes the contribution of the final subcircuit to the total earth fault loop impedance. Clause 8.3.9.3 Results. This clause explains that the values obtained from EFLI verification must satisfy the requirements of Clause 5.7.4. The requirement is considered satisfied if the measured earth fault loop impedance does not exceed the maximum value for the applicable protective device, or if the measured total resistance of the active and protective earthing conductors does not exceed the maximum value for the applicable circuit protection and required disconnection time. The notes explain how the reference values used for these limits were calculated and the assumptions used for conductor resistance and temperature. Clause 8.3.10 Operation of RCDs. This clause explains that to verify correct installation, tests must be carried out on all RCDs. The function of the RCD must be verified either by operating the integral test device or by using suitable test equipment. The clause also explains that after an RCD has operated to disconnect the designated circuit, isolation of all switched poles must be verified. This can be done by voltage tests or by continuity checks after removing supply. The notes explain that operating the integral test device confirms correct functioning of the RCD and the integrity of its tripping mechanism, but it does not check earthing continuity, earth electrodes, or other parts of the earthing system. The notes also explain that there is no requirement to test the operating time of RCDs, and that suitable tests may be carried out using a test plug with a resistor between the active and earth pins. Clause 8.4 Verification Records. This clause explains that the date of initial certification of an installation must be available on site. This can be provided by permanent, indelible marking on or at the main switchboard. The note explains that knowing the details of the original verification is necessary to allow future re-verification and to support the operation of an ongoing verification regime when required. That brings us to the end of Section 8 on verification. At this point, the installation has been inspected, tested, and confirmed as safe to use. These steps are critical because they prove the work has been done correctly and that protective measures will operate when needed. Always remember that verification is not just a paperwork step, it is a key safety responsibility for every electrician. For legal and technical detail, always refer back to the official ASNZS 3000 standard. Hi everyone, my name is Aria, and I work alongside Whit Roy as an electrical tutor. Before we begin, I want to make something clear about this audiobook. This is not a word-for-word reading of ASNZS 3000, 2018. The standard itself must always be read and followed exactly when you are doing electrical work or preparing for EWRB exam. What this audiobook does is take the key ideas from the standard and explain them in simple, spoken language, the kind of language you can listen to while driving, working, or revising. It helps you understand what the clauses mean, why the rules exist, and how they apply in real installations. So think of this as a learning companion, not a replacement for the actual standard. Alright, let's get started. Appendix C, Circuit Arrangements. This appendix gives guidance about how circuits are arranged in an electrical installation. It explains how circuit current is worked out for consumer mains, submains, and final sub-circuits, how cables are chosen based on their current carrying capacity and voltage drop, how cable ratings are coordinated with protective devices, how an installation is divided into circuits to supply single items or multiple items of equipment so the installation performs as intended, and how cables are installed. All of these factors together determine how circuits are arranged so the installation meets the design, equipment selection, and installation requirements of this standard. Clause C1, Scope. This clause explains that the appendix is informative guidance rather than mandatory rules. It focuses on helping the designer understand how to decide circuit currents, how to select cables correctly, how to match cable ratings with protective devices, how to divide an installation into suitable circuits, and how cable installation affects performance. The aim is to support good design decisions so the overall installation works safely and reliably. Clause C2. Maximum demand. This clause introduces the idea of maximum demand, which is the highest current that is expected to flow under normal operating conditions, rather than simply adding up every connected load at full rating. It recognizes that not all equipment operates at the same time or at full load. Clause C2.1. After diversity maximum demand. This clause explains that circuit current must not exceed the rating of the protective device, and the protective device must not exceed the current carrying capacity of the conductors. For a single item of equipment, the circuit current is simply the load current of that equipment. When more than one item is connected, adding all loads together would be safe but overly conservative. In real installations, equipment usually does not operate all at once or at full load for long periods. Under these conditions, the expected current is estimated using diversity, and this estimated value is called the after diversity maximum demand. Clause C2.2. Calculation of maximum demand in consumer mains and submains. This clause explains that maximum demand may be determined by calculation, assessment, measurement, or limitation. The appendix then focuses on calculation methods for consumer mains and submains, providing guidance on how designers estimate realistic demand rather than worst-case totals. Clause C2.3. Domestic installations. This clause introduces the approach used for domestic installations. It explains that loads are grouped by type, the demand for each group is assessed, and the contributions from each group are added together to determine the maximum demand for the installation or part of the installation. Clause C2.3.1. Method. This clause explains that an allocation of load is made for different types of equipment connected to consumer mains or submains in single or multiple domestic installations. Each load group contributes a calculated current, and these contributions are added together. The purpose is to arrive at a realistic maximum demand that reflects normal household usage rather than every appliance running at full power at the same time. Clause C2.3.2. Examples of calculation. This clause introduces worked examples that show how the calculation method is applied in practice, assuming a stated supply voltage and equipment ratings. Clause C2.3.2.1. Example 1. This example explains how to determine the maximum demand of a single domestic installation supplied at single phase. Different types of loads such as lighting, socket outlets, fixed appliances, heating, and special loads are grouped and assessed using the diversity approach. The individual group demands are then added together to give the total maximum demand for the installation. Clause C2.3.2.2. Example 2. This example explains how to determine the maximum demand of the heaviest loaded phase in a domestic installation supplied from a three-phase system. Loads are arranged across phases, and the demand on each phase is calculated. The phase carrying the highest current is identified as the heaviest loaded phase, and this value is used for design purposes. Clause C2.3.2.3. Example 3. This example explains how to determine the maximum demand of the heaviest loaded phase for a block of multiple units supplied by a three-phase system. It shows how individual unit loads and communal services are assessed, how loads are spread across phases as evenly as practicable, and how the demands from individual units and communal services are combined to find the maximum demand on the most heavily loaded phase. Clause C2.4. Non-domestic installations. This clause explains that non-domestic installations use a similar overall approach to domestic work, but the types of loads, operating patterns, and diversity assumptions are different. The maximum demand is determined by assessing the likely operating conditions of lighting, socket outlets, motors, heating, cooling, and specialized equipment used in commercial, industrial, and institutional environments. Clause C2.4.1. Method. This clause explains that load is allocated to different types of equipment connected to consumer mains or submains in a non-domestic installation. The load current is calculated for each equipment load group in the installation, or in the affected part of the installation, and the individual contributions are then added together to obtain the maximum demand. The accompanying guidance clarifies how different load types are treated and how the calculations are carried out in practice. Clause C 2.4.2 Examples of calculation. This clause introduces worked examples that show how maximum demand is determined for non-domestic installations supplied by three-phase systems. The examples demonstrate how loads are grouped, how diversity is applied, how loads are shared across phases, and how the heaviest loaded phase is identified for design purposes. Clause C 2.4.2.1 Example 4. This example explains how to determine the maximum demand of the heaviest loaded phase for a multi-unit motel complex supplied by three-phase. Lighting, socket outlets, exhaust fans, cooking appliances, motors, pumps, and heating equipment are assessed according to their load groups. The loads are arranged across the three phases. Each group is calculated using the appropriate demand rules, and the phase carrying the highest total current is identified as the heaviest loaded phase. Clause C 2.4.2.2 Example 5. This example explains how to determine the maximum demand of the heaviest loaded phase for a factory installation supplied by three-phase. Lighting, socket outlets, air conditioning, motors, welding equipment, water heating, and specialized machinery are assessed. The method shows how full load current, reduced load for additional machines, and duty cycle effects are taken into account. The loads are balanced across phases as far as practicable, and the maximum demand is taken from the most heavily loaded phase. Clause C 2.4.3 Alternative calculation method for commercial and light industrial applications. This clause introduces an alternative method based on energy demand rather than detailed equipment listing. It explains that this method may be used where experience and energy consumption data are available for similar occupancies. The approach converts typical energy demand per square meter into an equivalent electrical demand. Clause C 2.4.3.1 General. This clause explains that the alternative method uses typical energy demand values that depend on factors such as climate, hours of occupancy, energy management systems, and how evenly equipment is distributed. These values are used to estimate demand current for commercial and light industrial installations. Clause C 2.4.3.2 Example 6. This example explains how the alternative energy demand method is applied to an office tenancy. General lighting and power demand, along with air conditioning demand, are combined to give a total apparent power demand. This value is then converted to current using the operating voltage, providing an estimated maximum demand for the installation. Clause C 2.4.4 Alternative method using switchboard diversity. This clause explains that for switchboards conforming with the ASNZS 6143 series, maximum demand may be determined by applying a diversity factor to the sum of the circuit protective device ratings. The diversity factor depends on the number of downstream circuits and reflects the reduced likelihood of all circuits operating at full load at the same time. Clause C 2.5 Maximum demand in final subcircuits. This clause explains that maximum demand in final subcircuits is determined differently from consumer mains and submains. For a single item of equipment, the demand is based on the connected load. For multiple items of equipment, the demand may be limited by the rating of the circuit breaker protecting the subcircuit. Clause C 2.5.1 General. This clause explains that diversity may be applied in some final subcircuits where equipment does not operate continuously at full load. Examples include welding machines, domestic cooking appliances, and interlocked equipment, where operating conditions naturally limit simultaneous loading. Clause C 2.5.2 Welding machines. This clause explains how maximum demand is determined for welding machines, recognizing that welding loads are intermittent and often operate at less than continuous full load. Clause C 2.5.2.1 Definitions. This clause explains key terms used for welding machines. Rated primary current is the current marked on the equipment nameplate or derived from rated kilovolt amperes. Actual primary current is the current drawn during welding operation at a particular setting. Duty cycle is the proportion of time, expressed as a percentage, that welding current flows during a standard 1-minute period. Clause C 2.5.2.2 Arc welding machines. This clause explains that for an individual arc welding machine, the maximum demand is taken as the full rated primary current. For groups of machines, the demand is calculated by applying full load to the two largest machines, reduced percentages to the next largest machines, and a lower percentage to all remaining machines. This reflects the reduced likelihood that all welders will operate at maximum output at the same time. Clause C 2.5.2.3 Resistance welding machines. This clause explains how maximum demand is determined for resistance welding machines. For individual machines, the demand depends on whether the operation is varying or specific. Where duty cycle is known, a multiplier is applied to the actual primary current. For groups of machines, the largest machine is taken at full assessed value, with reduced values applied to the remaining machines. Clause C 2.5.3 Domestic cooking appliances. This clause explains that the maximum demand for a final subcircuit supplying domestic cooking appliances may be less than the full connected load. Assessed maximum demand values are applied based on the total connected energy rating of the appliances. Clause C 2.5.4 Interlocked equipment. This clause explains that where multiple items of equipment are connected to the same final subcircuit but are interlocked so that only a limited number can operate at one time, the maximum demand is assessed from the combination that produces the highest simultaneous load. Clause C3 Simplified protective device selection. This clause explains that simplified guidance is provided for selecting protective device ratings to suit common cable sizes and installation conditions. The intent is to assist designers and electricians with typical installations without requiring detailed calculations in every case. Clause C4 Simplified voltage drop. This clause introduces simplified methods for assessing voltage drop in cables. Clause C4.1 Background. This clause explains that voltage drop may be determined using methods from the ASNZS 3008.1 series. These methods account for cable type, conductor size, route length, operating temperature, and installation conditions. Clause C4.2 Examples. This clause explains how the simplified voltage drop method is applied. One example shows how to determine the minimum cable size needed to carry a given current over a specified route length while limiting voltage drop to a set percentage. Another example shows how to calculate the percentage voltage drop for a given cable size, current, and route length by comparing the required ampere meters with tabulated values. Clause C5 Number of points connected to circuits. This clause explains how to decide how many points may be connected to circuits so that circuits are safe, practical, and reliable in normal use. Clause C5.1 Number of circuits. This clause explains that any item of equipment with a current rating greater than 20 amps per phase must be connected to its own separate and distinct circuit. Where more than one item of equipment is to be connected to the same circuit, careful consideration is required. This includes how many points are supplied together, and what type they are, such as lighting, socket outlets, or appliances. It also includes how the equipment operates, recognizing that some loads vary during the day or by season. The expected circuit current must be suitable for the cable size and the protective device so the risk of overload is minimized. The effects of an overload must also be considered, especially where loss of supply could affect safety systems, emergency functions, medical equipment, or critical information and telecommunications services. Clause C5.2 Final subcircuits. This clause explains that guidance on the number of socket outlets, lighting points, and appliances that may be connected to a final subcircuit is provided to help designers and electricians achieve safe and workable installations. The method has been used over many editions of the standard and is suitable for typical installations, provided unusual loads are properly assessed. Clause C6 Guide to maximum number of cables installed in conduits. This clause explains how to determine how many cables may be installed in conduits or other wiring enclosures without causing damage during installation or service. Clause C6.1 General. This clause explains that the information is intended as guidance only. It helps determine how many cables and circuits may be installed in conduits and similar enclosures without exceeding physical or mechanical limits. Clause C6.2 Basis of calculations. This clause explains that the number of cables that may be installed in a circular enclosure is determined by comparing the internal cross-sectional area of the enclosure with the cross-sectional area of the cables, and then applying a space factor. The space factor allows for the way cables pack together and recognizes that cables and enclosures are circular rather than square. Different space factors are used depending on whether one cable, two cables, or three or more cables are installed together. The calculation method is demonstrated using common conduit and cable combinations. Clause C6.3 Application Notes. This clause explains that the cable types and sizes used are based on standard catalogue sizes for cables and conduits commonly used in New Zealand installations. It explains that the method may also be applied to other combinations of enclosures and cable types, provided they are compatible. The method assumes that conduits are reasonably short, clear of obstructions, and have minimal bends. Where this is not the case, the number of cables should be reduced to avoid excessive pulling tension or bending stress. This clause also explains that the calculation does not take account of grouping effects on current carrying capacity, temperature rise, or voltage drop, and that derating factors from ASNZS 3008 must be considered separately when assessing circuit suitability. Clause C6.4, Tables C10 to C12. This clause explains that guidance tables are provided to show the maximum number of cables that may be installed in conduits for common cable sizes, cable types, and conduit sizes. The tables cover single core, 2-core and earth, and 4-core and earth cables under typical installation conditions, using the calculation principles already described. That brings us to the end of Appendix C. We have worked through how maximum demand is assessed for domestic and non-domestic installations, how final subcircuits are treated, how points are allocated to circuits, how many cables may be installed in conduits, and how simplified methods are used for protective device selection and voltage drop. Taken together, this guidance supports sound circuit design, helps manage loading and diversity, and ensures installations are practical, safe, and reliable throughout their service life. This brings us to the end of the full audiobook for ASNZS 3000, 2018. What you have listened to is a learning companion created to support understanding of the wiring rules through clear, spoken explanations and practical teaching language. It is designed to help apprentices, students, and working electricians connect the clauses together and see how the standard operates as a complete system in real New Zealand installations. This audiobook is not a replacement for the official published standard, and it must not be used as the authoritative document during design, installation, inspection, certification, or compliance work. The official version of ASNZS 3000 remains the only legally recognized reference and must always be consulted when making technical or legal decisions. Use this audiobook as a guide for learning, revision, and exam preparation, and as a way to build confidence in understanding the intent behind the rules. Always confirm details against the current authorized standard and any applicable New Zealand regulations. Thank you for listening, and I wish you all the best in your study, your exams, and your ongoing work in the New Zealand electrical industry.